我咁彪教授。
Ladies and gentlemen, welcome to the Future Science Prize Week. The symposium will begin shortly. Please be seated. Kindly remember to turn your mobile devices to silent mode or turn it off. Thank you for your cooperation. Stay tuned and see you in a bit. Ladies and gentlemen, welcome to the 2025 Future Science Prize Week and the second day of the Science Symposium. It is my great pleasure to be the MC today. I'm Yoi Lang. Hello everyone, good morning. Good morning, good morning. We're so thrilled to be here with many great minds of the year. The Future Science Prize Week aims to promote scientific spirit and pay tributes to scientists, leading the public to explore the forefront of world science with a forward-looking perspective. This year, our program committee sets the agenda and invites domestic and international speakers to ensure the high level of academic content and extensive global perspective of the conference. We're delighted to have Dr. Harry Shum, Council Chairman, the Hong Kong University of Science and Technology, Council Member, the Future Forum, Co-Chair, Program Committee of the Future Science Prize Week 2025 to deliver a welcome remarks. Let's welcome Dr. Shum.
Good morning, distinguished guests, fellow scientists, and the students. It's a great honor to join Professor Dennis Lo as co-chair in organizing this science symposium for the Future Science Prize Week 2025 in Hong Kong. Over the past few months, we have worked diligently on every detail, from designing the program to inviting speakers, all with the aim of creating an inspiring academic event that truly reflects the spirit of scientific excellence and innovation. The 2025 Future Science Prize Week Science Symposium places a great emphasis on internationalization and diversity, presenting a high-level global academic forum. This year's summit brings together past laureates of the Future Science Prize, Nobel laureates, scientists from both Hong Kong and Chinese mainland, as well as distinguished senior scholars and young rising stars across many disciplines. For the first time, we have 20 laureates gathered in one place, the largest assembly in the prize's 10-year history, making this a truly historic moment. Today, as we gather here in Hong Kong to mark the 10th anniversary of the Future Science Prize, as the former rotating chair of the forum, I'm filled with excitement and gratitude. A decade is not only a milestone, but also a new beginning. The Future Science Prize is more than an award. It's a platform that connects brilliant minds around the world and drives innovation forward. We have watched it grow from a visionary idea into a globally recognized celebration of science. None of this would have been possible without the sustained support of so many scientists entrepreneurs, government leaders, and the friends from all sectors. On behalf of the organizing committee, I extend my deepest appreciation and thanks to all of you. The achievements and the groundbreaking discoveries of the Future Science Prize laureates represent the highest level of the scientific and the technological progress today. Their work not only promotes national development and the social progress, but also embodies the spirit of tackling humanity's most pressing challenges, offering immense value to the global community. I'm especially delighted to see that scientists from the Greater China region are receiving increasing recognition internationally, highlighting China's important contributions to the global science. Founded 10 years ago with a focus on the Greater China region, the Future Science Prize set a model for private support of fundamental research. 10 years on, we are now looking into the future. This year, our vision extends across Asia and ultimately to the world, providing young scientists with unrestricted research funding and the support for their careers. Young researchers are the most enthusiastic and innovative. And through this initiative, we hope to encourage them to explore the unknown, tackle scientific no man's land, and venture into new frontiers. The sessions yesterday on life science, mathematics, and chemistry were truly inspiring. Today, we look forward to equally stimulating discussing in physics, computer science, and a very special 10th anniversary session. We are honored to host 4 Nobel laureates, 20 Future Science Prize laureates, and the members of prestigious academies, including the Chinese Academy of Sciences, the US National Academy of Sciences, the US Academy of Engineering, and the European Academy of Sciences. Their presence is a testament to the stature of the prize and Hong Kong's role as an international hub for science and innovation. As our chief executive, John Lee, said recently, Hong Kong is becoming a city of science. A highlight of this year's program is the special 10th anniversary session, which we explore how to build a successful science prize. Representatives from the Nobel Prize, Abel Prize, Wolf Prize, Tam Prize, and IEEE awards will share their insights and experiences. This cross-disciplinary and cross-border dialogue promises to spark new ideas and inspiration. In addition, this year's Prize Week features a rich array of events, including forums on artificial intelligence, sessions dedicated to nurturing young scientists, and thematic summits led by laureates. We hope these diverse activities will not only showcase cutting-edge science, but also create an immersive experience for meaningful dialogue among scientists of all ages and backgrounds. Science, after all, is not only about discovering truth. It's also about connecting people and illuminating our common path forward. May these 2 days be filled with vibrant exchange, curiosity, and collective inspiration as we contribute to the next decade of scientific advancement. Finally, I would like to thank everyone who has traveled from afar to be here, and all the teams working very hard behind the scene to make this event possible. Enjoy the symposium and enjoy Hong Kong. Thank you very much.
Thank you so much, Dr. Sherman. Please be seated. Thank you for your sharing. The upcoming section will be physical science section, microscopy and macroscopy world. I would like to introduce with you Professor Kung-Pil Look, IS Policy W2, Professor, the Hong Kong University of Science and Technology, Distinguished Professor of Graduate School, University of California, Berkeley. Member, the Hong Kong Academy of Sciences, 2019 Future Science Prize, Physical Science Prize Laureate. Member, Program Committee of the Future Science Prize Week 2025. As this session convener, let's give him a big round of applause to Professor Look.
Oh, thank you for the introduction, and good morning, everyone. It is my great pleasure to serve as the convener of the physical science section, and I would like to warmly welcome you here. As you know, the theme of this section is microscopic and macroscopic world. So through observations and theoretical guidance, physicists have discovered numerous connections between the very small and also the very large from subatomic particles to the grandness of the cosmos. Today, we have the privilege to hear from 5 exceptional scientists who will guide us through the most exciting development in modern physics. So each speaker will have approximately 25 minutes. After the presentation, we will invite the speaker back to the stage to have a panel discussion. If we have time left, then we will open the floor for a couple questions from the audience. So now let me introduce the distinguished speakers. So our first speaker is Professor David Gross, 2004 Nobel laureate in physics and Chancellor Chair Professors of Theoretical Physics at the Kavli Institute for Theoretical Physics, the University of California at Santa Barbara. Now, the title of his talk is The Frontiers of Fundamental Physics. So let's welcome the Professor Gross.
Well, it's a great pleasure to be back in Hong Kong and at this 10th anniversary of this great Future of Science Prize. It's very impressive, and I'm delighted to start off this session on the physical sciences discussing the frontiers of fundamental physics. We've learned so much in the last 50 years. It's truly amazing to look back and realize how little we knew 50 years ago. Many of you were not born 50 years ago. We've, for example, discovered in experiments and understood by theory the basic building blocks of most of matter and the forces that act on them. We've finally constructed an extremely successful theory of the fundamental constituents of matter and how they interact. Furthermore, we have mapped almost the entire universe from its beginning, whatever that is, and reconstructed most of its history. And in addition, we have achieved exquisite understanding. We celebrate this year 100 years of quantum mechanics, which has revealed the workings of microscopic matter. in all of its phases, we now can control ordinary matter and are now constructing new forms of matter down to the nanoscale of atoms. But I like to say that the most important product of knowledge, in addition to the many applications that drive our economies, is ignorance, namely new questions that can be answered by observation, by experiment, and by theory. In other words, by the scientific method. It is these questions that define the frontiers of science, and especially of fundamental science. We live in a sea of ignorance, are aware of the ignorance on the boundaries of our knowledge. And that is what defines, in my opinion, the frontiers of physics. The fundamental questions we ask about the universe around us. So I'm going to discuss 4 basic areas of fundamental questions, the frontiers of physics, which range over 60 orders of magnitude, remarkably. The largest, of course, being the size of the universe itself, 10 to the 25 meters, where we explore the history of the universe as a whole, its origin and its future. At a smaller scale of the order of the size of the Earth or the Sun, the frontiers are partly in the discovery and observation and trying to understand the properties of black holes. We're lucky to have Richard here, who will tell us the story of the black hole in the center of our galaxy. Going down by another 17 orders of magnitude to ordinary matter that makes up the objects around us, atoms, molecules. We are now in a revolutionary expansion of our understanding and control over the quantum properties of ordinary matter, with exciting applications to computation. Another 17 orders of magnitude, the smallest scale we can contemplate, the so-called Planck scale. Theorists are exploring the possibility of unifying the forces of nature, explaining and even understanding in a deep sense what space-time is made out of, the structure of space-time itself. This covers remarkably 60 orders of magnitude, from the very largest scale to the very smallest scale, and remarkably, some of the methods we use and some of the connections we have discovered unite these different scales in a fascinating and largely still a mysterious way. So let's start briefly with the origin of the universe. We have, as I said, over the last 50, 60 years, really mapped out the history of the universe from its early beginning, some kind of beginning, which I'll come to, an inflationary period. We have, of course, a marvelous picture of the universe very early on, a rather featureless black body of radiation and matter with small fluctuations, which have been mapped out by the cosmic microwave background. And we understand now how those fluctuations condense to form strands of matter, and eventually the galaxies and planets and stars we see around us. And in addition, we have a theory that has emerged an incredibly successful and simple theoretical description of the evolution of the universe from very early on till today, and perhaps beyond, which consists of an expansion, indeed an accelerated expansion. But at the very beginning, all of our equations and all of our approaches break down, and we are completely in the dark as to how the whole thing began. So one of the most fundamental questions we are beginning to ask as scientists and not as philosophers or religious figures is, how did the universe begin? This is now a scientific question. Only recently has it become a scientific question, which we can now explore by observation. And it's still unclear how far back we can probe. It's hard to do that with photons, but gravitons allow us to go even farther. Can we, in fact, determine the initial condition? Can we understand the principles that produce the initial state of the universe? This is conceptually an enormous challenge for physics, which has never had to deal with such a question before. It's not even sure we can answer this kind of question. It's the beginning, the origin of the universe, in some sense, is the beginning of time, time as we know it today, and it raises many issues. Was there a time before the Big Bang? What does it mean for time to begin? Is the universe cyclic? We are totally ignorant of the answer. But this is one of the great driving forces of cosmology and astrophysics. We've also learned in explaining the universe from its beginning till now, we've learned that most of the energy, and indeed most of the matter in the universe, is not the stuff we are made out of or were aware of 50 years ago. Most of the energy is in a form of dark energy, negative pressure, Einstein's cosmological constant, perhaps. Most of the matter astronomers have discovered and mapped out is made out of a kind of matter that is not present on Earth, and we haven't been able to produce it, and is one of the main driving forces of astrophysics and particle physics. So, what is the nature of the dark matter that pervades the universe that we sit among? What is the true nature of the dark energy that fills the universe and is responsible for the accelerated expansion? Dark matter was a form of matter throughout the universe that astronomers discovered. And luckily, Hitoshi Moriyama is here and will explain the issue, and I'm sure in great detail. We understand now that ordinary galaxies sit in a potential in the middle of dark matter. Dark matter is not directly observable. It does not interact strongly, perhaps not at all, with the ordinary matter and with light. But it can be detected indirectly through its gravitational pull, as all matter pulls all other matter on stars. And it has been mapped using gravitational lensing, the gravitational effects of dark matter throughout the universe. So we know an enormous amount about the distribution of dark matter throughout the universe, and it is an essential ingredient of the standard model of cosmology, lambda CDM, which requires the inclusion of this dark matter in the dynamics of the universe. But what is the nature of dark matter is a mystery. It could be a heavy particle. We look desperately for signs, direct signs of its interactions throughout the universe. For example, dark matter annihilation. We try to produce it directly in the laboratory in particle accelerators, where with enough energy you can produce anything. Dark matter is all around us, flowing through us all the time. Can we detect dark matter? The dark matter wind flowing through ourselves or our laboratories. So far, remarkably, we have no conclusive answer to this question, even though it has been a central question in particle physics for the last 30 years. It's very surprising. I was completely convinced that by now we would have identified and measured the properties of dark matter. But of course, you know, when you have fundamental questions like this, negative results are as informative, perhaps even more in the end, than positive results. And so our theoretical friends, which I'm sure Hitoshi will discuss in great deal, have let their imagination flow and now have many, many fascinating possibilities that were unimagined before. Okay, the nature of dark energy is even more mysterious. It's not fundamentally mysterious. It was introduced by Einstein. It's a natural possibility in the dynamical theory of space and time, general relativity. But its size is extraordinarily small in natural units. It is responsible for the accelerated expansion of the universe. It seems to be, at first sight, with the crude experimental measurements we have to date, constant, as Einstein perhaps suggested. But there's recent evidence that it might be changing in time, which would truly challenge our standard model of cosmology and provide very interesting clues as to the ultimate fate of the universe. For example, will the universe continue to accelerate? And in addition to the how did the universe begin, in my opinion, an equally important and difficult to answer question is, how will the universe end? So now going from the size of the universe as a whole to solar system sizes, one of the fundamental questions that we face in physics is the nature and properties of black holes. Black holes, as we know, are abundant throughout the universe. There's a black hole in the center of our galaxy, and Professor Genzo will explain how that was confirmed. But they're also the source of gamma ray bursts and violent phenomena throughout the universe, which have finally been observed directly by LIGO collaboration, who almost a little more than 10 years ago observed in this beautiful interferometer the gravitational waves that were created and whose mathematical form is understood precisely, at least at the classical level, by Einstein's equations, and allow us to see the the gravitational waves produced billions of years ago by the collision of two black holes. And more recently, colliding neutron stars equally produce gravitational waves and electromagnetic signals, which have allowed us to not just understand properties of gravitational waves and black holes, but also the history of heavy element production in the universe. So black holes, remarkably, are now visible and provide a remarkable new astronomical tool, in addition to electromagnetic radiation, gravitational radiation, to explore the universe and perhaps to get information about what happened at the very beginning. I'll come back to black holes in a minute because they also raise very deep conceptual theoretical problems which are challenging us theorists. Going now down again by another 17 orders of magnitude, we arrive at the atomic scale, the size of ordinary. I have 10 more minutes, 15 more minutes, I see. I have a stopwatch. Atomic scale, the size of ordinary atoms and molecules, where the basic physics was unraveled 100 years ago in the attempt to understand atoms, which led to quantum mechanics, and has dominated microscopic, indeed all of physics, for the last 100 years. But we are now entering a totally new era in atomic, molecular, quantum mechanics, where we can understand, manipulate, and control matter at the atomic scale. And this raises enormous possibilities. Many applications are envisaged. We can create new forms of matter. Here we see graphene. And the enormous excitement, which you're all aware of in the last decade or two, about this development is that as quantum mechanics, the understanding of atomic and molecular physics has produced modern technology, the ability to control matter at the quantum level might produce applications that we can only dream of. This year's Nobel Prize, which we're very proud of at Santa Barbara, two of the awardees are, and at Berkeley, was for an experiment that showed 40 years ago that you could actually construct macroscopic quantum atoms, in a sense. And it was perhaps the beginning of the dream of constructing systems which are coherent quantum mechanically, and where the strange but true features of the quantum world can be utilized for sensors, measurements, wonderful applications in the laboratory, but also perhaps quantum computing. Computing, which we'll hear a bit about later, I gather today, is more and more dominating our ability to do experiments and to do theory. And, but we're sort of reaching the end of the rapid development over the last 40 years of ordinary classical computers. The hope is that with new materials we might keep Moore's law going, and by constructing quantum computers. So quantum computers, of course, are based on replacing the classical bits of information, the zeros and ones from which one can construct the most general Turing machine, by quantum computers. Classical 0 and 1 might be the states of an object with up and down possibilities, but the quantum computer, the quantum bits are, for example, the states of a spin 1/2 particle, like the electron. If you measure it in some direction, it can be up and down, but the general state, of course, is a coherent superposition of up and down, which maps out a sphere. There are many more states available to a qubit than to a 0 or 1 register. And if you put these qubits together in a way that preserves the quantum coherence, you can store, access a vast space, Hilbert space, the quantum phase space of physics. And it has been shown, and this is an area of intense theoretical development in physics and computer science, use that to solve problems rapidly that classically would be impossible. Trouble is, of course, that the environment destroys that coherence easily, and one has to protect against that. And so the name of the game in quantum computing is an enormous challenge at both the hardware level of constructing coherent quantum computers, which can correct their faults, fault tolerant, but also on the theoretical level of understanding, trying to understand the nature of the enormous possibility of quantum states, which in a protected environment are vast and offer many opportunities. In my opinion, the prospects in this direction for the discovery of new matter, a quantum computer, by the way, is a kind of new matter that one is constructing, macroscopic new matter in the laboratory. Creation of new forms of old matter, new phases of ordinary atoms and electrons. And the prospects of doing this, I believe, are very exciting and mostly unknown. I don't think we can even predict, have a good sense of what is yet possible as we explore the quantum world. Let's go down now. I have very little time. Oops, maybe I'm wrong about the time. Yes, I see I am. Very little time. By another 9 so-called orders of magnitude to subatomic physics, nuclear physics, and the fundamental structure of matter itself. And here, as you know, we have, over 40 years ago, come up with a comprehensive theory, the standard model of elementary particle physics. We've discovered that all earthly matter is made out of quarks, up and down quarks in ordinary nuclei, and leptons, neutrinos and electrons, and 3 families, all the same kind of particles. And most importantly, we've discovered and understood in great detail the forces that act on this particle, which remarkably all turn out to be generalizations of Maxwell's theory of electromagnetism. So the first force is E&M, which we're well aware of for almost 200 years. That's a theory of particles with one kind of charge, the electric charge. And it turns out that the other forces that act within the nucleus, the strong nuclear force that holds nuclei together and the weak nuclear force responsible for radioactivity and the transmutation of elements, are generalizations, Yang and Mills generalized Maxwell's theory to theories with more than one kind of charge. There's the weak nuclear force, which is the situation where there are 2 charges, up and down. We call that flavor or electron neutrino, 2 charges. That's a weak force inside the nucleus, which is screened by the Higgs mechanism. And then there's the strong nuclear force that holds the quarks together, permanently confined inside the nucleus, which is a situation where there are 3 charges. For the quarks, each quark has a charge label, we call it color, 3 of them. And so remarkably, all these forces in the standard model are simply like at the bottom, fundamentally, like electromagnetism, although richer and more interesting and more complicated, based on 1, 2, 3 charges. In addition, of course, the weak interactions require a mechanism for breaking, screening the charges, those charges. That's the Higgs mechanism, invented 55 years ago, and recently one of its characteristic features was confirmed by LHC at CERN, completing the Standard Model, which is absolutely a remarkable theory. After 2,000 years of looking for a theory of matter, we have one which so far shows no signs of breakdown. It has to, we know from experimental observation, for example, of dark matter. But aside from that, there's no sign that it breaks down until we get to distances of the Planck scale, and it works throughout the universe. Remarkable. My favorite one, of course, is the strong force, mediated by this chromodynamic field, much like the electromagnetic field, but it's sourced by the color charge of the quarks, and it doesn't give rise to an inverse square law like electromagnetic interactions, is rather squeezed by the vacuum, the flux between the quarks. The chromodynamic flux is squeezed to a thin tube. That's property of asymptotic freedom. Quarks interact weakly at short distances, but at large distances, this phenomena of, which is illustrated here in solving using numerical methods, the equations of QCD, produces a flux tube between the quarks. And of course, that means that the energy to separate the quarks increases linearly, and quarks are permanently confined in nuclear matter. This theory has been, this is the case of the proton, which has 3 quarks. And this theory has been now tested in literally thousands of experiments at particle accelerators with enormous accuracy, and shows absolutely no sign of any problem. For a theorist, for me, the most gratifying feature, theoretical success of this theory, is that we can now calculate the mass of all of the elementary particles that are bound states of quarks, including the proton, the neutron, the strange K-mesons, the pion, all of them, with enormous accuracy approaching now 1%. This is a remarkable achievement of computational physics. And remarkably, if you look at the 40-year history of calculating the spectrum of elementary particles, it required 2 things to happen, both of which happened in the last 40 years. A factor of 1 billion in the power of ordinary computers, Moore's law, but also a factor of 1 billion in developing the theoretical understanding of QCD and of how to do careful and controllable calculations. Remarkable. But, you know, there are many, many questions still evident which tell us that beyond the Standard Model, there have to be physics not contained within the Standard Model. That we know now there are neutrons have masses. The universe is full of baryons, and there are very few anti-baryons. Dark matter, of course. Those are experimental indications that we have to go beyond the Standard Model, the existence of dark energy as well. And there are theoretical motivations of unifying the forces that fit together so nicely, understanding the Higgs mechanism in greater detail. these quarks and leptons have a totally bizarre and strange spectrum of masses, which we see no reason for so far. And of course, the conceptual problems of cosmology. So we are driven to try to unify all the forces, and remarkably, just taking the standard model and extrapolating forward, assuming nothing new happens, which is undoubtedly incorrect. But at this level, the forces do seem to come together at a very high energy, close to the Planck scale, where gravity itself becomes a quantum phenomenon. So gravity is a very weak force at low energies, but at high energies, since it is produced, sourced by energy, it is a very strong force. And that has led a large part of the theoretical community to consider string theory, which beautifully unifies gravity and the forces of the standard model. So string theory imagines that a particle like these mesons are actually a representation, a kind of crude representation of a string theory. So in this approach, one that is being strongly pursued as a way of understanding quantum chromodynamics when the quarks are far apart and the forces are strong, the remarkable phenomena is that a theory like this, where the mesons are strings, when these strings are closed loops with no quarks at the end, it looks like gravity. So string theory is the first existence proof that one can have a theory that unifies standard model-like forces and gravity, and also produce a theory of gravity, which, unlike Einstein's theory, where when you look at space-time, the dynamics of space-time, which Einstein understood was the origin of gravity, undergoes violent fluctuations and is uncontrollable. And so physics has known, actually since the earliest days of quantum mechanics, that something has to go wrong at the Planck scale. We definitely need to modify perhaps what we mean by space and time itself. So a good part of theoretical challenge nowadays is to try to understand space and time. String theory reminded us that whether there are only 3 dimensions of space-time is an experimental question. There could be more hidden because the extra dimensions are very small and invisible unless you have a very good microscope. And indeed, in the simplest solutions, string theory-like constructions, there are 6 extra dimensions of space and time, which determine the nature of the forces, the form of matter, the value of the masses of quarks and leptons, say, which are all then determined by the shape, the geometry of the hidden, very small dimensions. 40 years ago, this was an exciting possibility that this theory, which seems to have no non-dynamical parameters, could produce an explanation of the properties of the standard model that we don't understand, and perhaps much more. Unfortunately, we discovered, although there only seems to be one theory in some sense, there are many vacua. There's a landscape of enormous number of possible solutions of whatever this theory fundamentally is, which we don't yet know. And so, to a large extent, the work in this field of fundamental physics has shifted to trying to understand the nature of space and time. Black holes, which we know now exist and we can see and study, have produced an enormous motivation because there clearly one needs to understand gravity way beyond Einstein's theory and deal with the possibility raised by Hawking that black holes or gravitational physics in general would violate quantum mechanics. And he was concerned that black holes, from which classically nothing can emerge but quantum mechanically appear to radiate like a hot object, would destroy information and unitary time development of quantum mechanics. Well, that has proved an enormous motivation for theorists. You have the two pillars of physics currently are, if you want quantum mechanical, quantum field theory description of ordinary matter and forces, and general relativity, which explains the universe and the structure of the geometry of space and time. Are those consistent? And recently, a remarkable discovery in string theory of the duality between open strings and closed strings, or gravitational physics, or string theory in a bigger space-time, to an ordinary quantum mechanical system, like the standard model, has been established in a very special case of negatively curved geometry. It's sort of putting space and time in a box. And there are two descriptions of the physics which we have enormous evidence are completely equivalent. Which are completely equivalent. One is string theory, still very mysterious in the bulk, and then on the boundary of the box, ordinary quantum mechanical systems like the standard model. This gives us an incredibly powerful tool which has dominated theoretical research for the last few decades of using Einsteinian gravity, general relativity, to explain very subtle and powerful properties of ordinary quantum mechanical systems, even superconductors, and on the other hand, using our knowledge of ordinary quantum mechanical systems to understand quantum gravity. It seems to have resolved the black hole paradox, which Hawking argued violated quantum mechanics, by constructing these dual descriptions of black holes. On the one hand, a black hole in anti-de Sitter space, this curved space. On the other hand, something we're very familiar with and observe in the laboratory at CERN and at Brookhaven, the quark-gluon fireball, where one has a dense system of nuclear matter, and the quarks deconfine and create something which is dual in this picture of fireball, a black hole, proving that since in this case, clearly quantum mechanics hold, information is conserved, that's also true in this case. And in recent decades, we've understood in great detail how that can happen, and with very important implications as to what space-time really is. In this dual picture, we can understand space-time as an emergent thing. And from the point of view of string theory, that is essential, because in string theory, most of the classical notions of space-time to some extent break down. Smooth manifolds need not be smooth, as they are classically. Topology can change, which is not allowed classically. And even the number of dimensions of space-time depends on the question one is asking. So we're in a situation where we truly believe that space-time is an emergent concept, and it eventually will be understood as emerging from some deeper quantum mechanical description. And that, of course, means that gravity is an emergent force, in a sense. But this raises enormous conceptual problems. How do you do physics without space-time? What we have discovered is remarkably a deep, deep connection between the structure of the quantum states that correspond to different geometries, the dual space-time. And going back to the great advances in quantum mechanics, macroscopic quantum mechanics, quantum computing, it is truly remarkable that tools like quantum coding plays a big role in trying to understand the emergence of space-time in these dual systems. There's a, yeah, I'm sort of at the end. This, I think, our deep understanding of the nature of space-time is going to be necessary to explain the questions that I started with, the universe as a whole. If you want to have a fundamental theory of gravity, quantum gravity, the theory has to come up with a solution that describes the universe as a whole. The universe is its space-time history, and that's the object of a theory of gravity and matter. That includes an understanding, as I remarked at the beginning, perhaps what happens at the boundary of space-time as a boundary, and certainly what happens at the end. And here, we really don't know what the rules are, but they clearly involve the nature of space-time itself, as evident from thinking about the beginning of time. It also, I think, is fundamental for the deep questions of particle physics. Particle physics, we're driven at this fundamental level by unification. The forces of nature we know of cry out to be unified, but we also would like to address the problem of uniqueness. What picks the particular standard model with its 19 or 27 parameters that we measure but can't calculate? In string theory, there are many, too many possibilities. What picks particular theory out of the all possibilities? My opinion, that could very well be related to what picks the initial state of the universe, which, among the rest, must describe the particular theory of matter. And it's clear to me that those questions are crucially rely on understanding at the beginning of the universe and the nature of quantum gravity at the nature of space-time itself. So these deepest questions, remarkably, are all connected, and even more remarkably connected to the growing push to understand in a deep way the nature of quantum states that drives the quantum effort, quantum computing and such. These are difficult questions. We desperately need new experiments. The new experiments are being planned in astrophysics and in particle physics, new accelerators, new telescopes. But we also need theoretical breakthroughs. I'm optimistic. We've had an unbelievable 100 years since the beginning of quantum mechanics, and I truly believe that once a fundamental question, like some of the ones I've raised, becomes a well-formulated scientific question, which means that it's approachable by experiment, by observation, and by mathematical theory, it will be answered in your lifetime, not necessarily mine. As far as the theory goes, the kind of speculation that many of us are engaged in without enough experimental guidance. I'm always reassured by Einstein's encouragement and warning that the successful attempt to derive delicate laws of nature along a mental path, following a belief in the formal unity, which remarkably becomes clearer and clearer over the years, of the structure of reality, encourages continuation in this speculative direction, the dangers of which everyone vividly must keep in sight who dares to follow it. So with that, I come to the end. Thank you. Sorry. It's yours.
Well, thank you very much, Professor Croes, for giving us a very exciting grand tour of physics, from the universe through quantum science, to particle physics. So now I'm going to introduce our second speaker, Professor Reinhard Genzel. Reinhard is the director of the Max Planck Institute for Extraterrestrial Physics, and he is the 2020 Nobel laureate in physics. He is going to tell us his story. The title of his talk is A 40-Year Journey. So let's welcome Professor Genzel.
So how do I move? How do I move? No, how do I move the slides? How do I move the slides? All right. Well, wow. David, you have given us an incredible and awesome view of science and physics. And I hope that the young people here see that this is not just, fake news. This is really very deep thinking together with experiment. And experiment and theory here come together because indeed you can fool yourself with a theory, but you have to prove it. So I'm now going one level down from the overview of the countryside down to testing indeed one of these things that David talked about, and that is black holes. And why did I write 40-Year Journey? This describes indeed, and that is true for many of these fundamental things, these are not experiments which you do in one day. And sometimes you really have to stay at it. And you will see how that is possible. Now, in the case of these black holes, the kind of experiment which you want are machines which use electromagnetic radiation as well as gravitational waves and get very, very high angular resolution, because it turns out these black holes, even if they are massive, but they are far away, are extremely small. The region within which light cannot escape, that's what you would call the event horizon, are extremely small. In the case of the sun, that would be a very small region. In the case of the galactic center, it's about a few centimeters. So that's why we need technology to get to very high resolution. And it's really rather funny that in two different forms of modern astronomy and gravitational wave experiments, there's one technique which is sort of common to all nowadays, and that was invented by Albert Michelson. It's the interference of radiation, and thereby using from the interference pattern the shape of the source. You can do this in astronomy most easily along radio waves. So radio interferometry was invented already in the 1940s, 50s. Then the gravitational waves, that was a very long story, more than 40 years until people were able to put together a machine which had a chance to see something. And then finally, at about the same time, the same could happen now also in the optical and near-infrared. So we are rather in an unusual situation that all of a sudden we have a weapon in our hands, so to speak, which you can apply to all these questions at a long distance and see in great detail what's happening there. Now, of course, in the case of gravity, and that's one of the forces which Dave talked about, the story, in a way, is a few hundred years old, right? Because humanity, with Galileo and Copernicus and Newton, tried very much to understand what holds us together. We all know what gravity is. If I jump up, which I can't, I will come down. You too. Gravity is pretty obvious to us human beings. But Einstein, in his work, first the so-called special relativity, and then in the general relativity, he tried to cast this Newtonian theory in a new way. And that entails the fact that light, in the form of photons, because it's matter and energy are equivalent, also sees gravity. So once you say that, once you understand that, then you will say, hey, if a photon sees gravity, it may also not jump up and get away. So if you have strong enough gravity, then there may be a critical mass radius of an object where photons get stuck. That's a black hole. So that's the theory. And many, many people worked on the theory in the region, in the time frame between it was first invented 109 years ago, and now people like Schwarzschild up on top found the first solution of a specific form of symmetry, the spherically symmetric situation. Then there was Kerr, who showed that there is another property these black holes have, not only mass, also spin. And Roger Penrose showed that the outcome, the theoretical outcomes, don't really depend on these symmetries, as many people feared, but it's very, very characteristic of just the curvature of space-time. And then, of course, the question of going beyond classical theory, and there is, of course, Stephen Hawking, who was the first one to begin this story, and it's not ended at all. And Dave showed some of the things. And there is a problem. Whilst for other forces, it is always possible to build a bigger accelerator, say, and get higher resolution and therefore more information. In the case of black holes, you can join me on a rocket and fly into a black hole. I don't recommend it, but you could. We won't have much fun. And we won't be able to escape. And no Nature paper written on Nobel Prize also is not in sight. Okay, so that's the problem, that the inside of the event horizon is not accessible. Maybe it's accessible to the topic of the information which is stored, the quantum information, but these are dreams of the future. So, general relativity. Now, the first instances in which general relativity and black holes showed up in observational astronomy was in the 1960s in two ways. Once in X-ray binaries, and the more famous one are these objects, so-called quasars. These are very bright radio sources, and then when you look there, you see sort of a flimsy little star-like object. Okay, but once you look in the spectra of optical spectra of these quasars, you see that the lines which tell you something about the wavelength of where something was emitted are all redshifted. And so where does that redshift come from? Well, there was a long discussion. In the end, the conclusion was it's due to the fact that the universe is expanding. You heard about that. The universe is expanding, and therefore something further away is redshifted more. So if you take the redshift, which you see here, which is 16% in this particular object, which at the time was a sensation, this object is 2.4 billion light years away. Wow, that's a factor of 100 more than at that time anyone dared looking out in the universe. If that is the case, what looks like a meager little star is enormously powerful, produces about 1,000 times as much energy as the entire Milky Way. And all of this from a region which is a mere few light years across. How can that be? Now, these gentlemen down there and a number of others thought about this for about a decade, and then they came up with a rather, how should I say, unbelievable answer: black holes. Oh, you would say, well, why that? Cannot be. You told me, that, the property of a black hole is that light cannot escape. Now, all of a sudden, you tell us that you produce light, lots of light. Well, I said there's an event horizon, and inside of that event horizon, so to speak, no light can escape. But outside of the event horizon, the light is redshifted when it comes out, so it loses energy, but it still can come out. And vice versa, the gravity of a black hole, if it's very massive, is so strong that if you dump energy in form of matter onto this, and you see down there a little sketch of such a disk of material spiraling into a black hole, enormous energy densities can be radiated away. About 1,000 times as much as fusion in the sun. So that was a proposal made in the late 60s, early 70s. But now, that's a good thing to have a story, but how do you prove it? Well, you want to show if there's gravity, and then of course you can do the same as Newton and the Babylonians and the Greeks did in the case of the solar system. You have the sun and you have the planets, and then you find that the planets move in orbits around the sun, and the orbits are more or less circular, and the speed of motion decreases to the outside very, very regularly, called the Kepler laws. So if you could do the same thing here, that you had planets around a black hole, you measure the orbital motion, then as you go in, it should go up, and from that you could measure the mass. Well, okay, planets is not going to cut it. But Lynden-Bell and Rees wrote a very famous paper in '71 saying, look, guys, if these black holes really are radiating, if these objects are really radiating black holes, go to the nearest object, because if there are these distant quasars, which are very bright, maybe there are other black holes, not so much accreting, and then you could maybe see something around them. What's the nearest object which is really massive? Us, our Milky Way. So that's what Lynden-Bell and Rees did, and since then, since the 1971, the hunt started, so to speak. The experimental hunt started, and then over time led to successes. The success I'm associated with are the motions of gas and stars around the central object, and again using basically these techniques, and if you like, the Kepler laws, although now modified by general relativity, to prove that there is a mass and how compact it is and say whether something else than a black hole is it. Now, the next technique are gravitational waves. David mentioned that if you have two black holes, for instance, they see each other, they rotate around each other, and if they're close enough, there's another form of energy, which is gravitational waves they can emit, and they lose energy. That means they move together ever closer until the event horizons merge. And you have one object, one bigger black hole. So that technique, gravitational wave, also is now one which is possible. And finally, remember radio astronomy? There are now experiments by using telescopes across the entire globe, thereby getting very, very high angular resolution and looking at objects. So with these techniques, we can actually start hunting in a very serious fashion. And the first cases were these quasars, and one found that, broadly speaking, there are central masses there. And then the next case was the galactic center. In this case, Professor Charles Towns, the inventor of the maser and the laser in Berkeley, knew how to build infrared equipment, because you cannot look into the galactic center in the optical. There's too much dust between us and the galactic center. And so he and his students, and later on postdocs, I was one of them, started measuring the lines, as you see, from very well-known atoms and ions, and mapped it out and showed that they were actually streaming around. This is this green and pink stuff, and they rotate, they move around not in circles, but in ellipses around the central source, which is a radio source. So that was the second way to go at it. So here we are having a little trip into the galactic center. That's the central star cluster, about 1 million stars in the center. Some of them remarkably heavy, actually, much heavier than the sun. And then in the middle of all of this mess is the radio source, which you hardly see here. And then you do this again and again and again, year for year, with ever better resolution and techniques. I won't describe to you what we all had to do over time to get ever higher definition of the orbits, but you can track the motions. Initially motions and then orbits. Today, with the interferometric technique, which I showed to you in the beginning, we can see in a given year how, say, two stars move at about 8,000 kilometers per second. That's almost relativistic motion in parabolic orbits around the radio source Sagittarius A star. From that, we can measure the mass. And depending on the orbit of the star, that gives us the mass enclosed within different radii, and that is sort of a way to ask the question. So we've done this with telescopes in Chile, the so-called Paranal Observatory with 4 8-meter class telescopes. And Andrea Guess and her colleagues at UCLA used the 2 Keck telescopes. So that's become a bit of a race between the two groups. But the interesting thing was, and that's another feature of course, of fake news versus real news, is the onlookers could see whether our results agreed with each other, and they did. So that's a very good sign, not so much for the people doing the work, but those who are looking, because they can say, that's maybe believable. And so that's how we then started getting not only motions, but actually whole orbits, in this case of this star, with a 16-year orbital time scale. Sag A star is in the bottom part, this this dot, and we can see the motion on the sky. We can also measure the motion along the line of sight through spectroscopy and the so-called Doppler effect. So with that, we can reconstruct in great detail the orbital parameters of that star, and therefore also the mass. We can measure the mass of the central radio source to about 0.1%. It's not shabby at all for astronomy to be that accurate. Okay, so with these techniques then, as I mentioned to you, we are able to really get down into the central region and determine the mass distribution. But then there's another question here, which is we have been using general relativity and so forth to interpret our data, but is GR really truly correct? That is a fair enough question, and we have to test that. So we have to test, is general relativity applicable? So the first test we do is we look when the star moves by the central object, and we look at its spectra. Then, when the star is very close to a Sagittarius star, there is stronger gravity than when it's far away. And that means that at the bottom, when the star is very close to Sagittarius star, the emission line velocity is redshifted by quite a bit, a few hundred kilometers per second. Whilst when it's further away, that redshift is essentially negligible. So that follows exactly the red curve, which is general relativity. The next thing is, in Newton, we know that if you have a planet on a circular orbit, say around the sun, then if there's nothing else around, then that circular orbit stays there for all time. Not so in general relativity. In general relativity, there are precessions. In-plane precessions, it's called the Schwarzschild precession, and then also precessions if there is a spin of the black hole. And so in terms of residuals from the Newton orbit, down below you see the X and Y residual patterns you would see in Newton, that's that black point, namely no residuals, and that what general relativity would predict are these loops, these red loops, and the data are pretty good. They show general relativity is right also in this test. And the next tests, of course, are can we get closer? These stars move at about 1,000 times the event horizon radius. We would like to get closer because, it could be that there is a concentration of dark matter, it could be a concentration of stellar black holes. But in order to really, truly show that this is a single black hole, we want to get very, very close. And there are two techniques. One is here, we are using very hot gas, which from time to time erupts near Sagittarius star, and then it orbits the central point. These are the green points there, and they move, believe it or not, at about a third the speed of light. And the radius of that loop there is about 5-6 times the event horizon size. So that's truly the relativistic limit, and we are seeing, so to speak, thunderstorms, magnetic thunderstorms as a way to measure the gas motions in the center. Now then, the radio astronomers use light bending. Gravitational theory tells you that if you look at an object and there's a star behind, then of course our classical rays, if they go by the star, do not bend, they go in a straight line, but not in general relativity. They get bent towards the observer, and if they're very close, they never make it to us. Okay, so you expect a pattern like this. In the inside, it's black because the rays don't get out, and then there's sort of a minimum radius which you can measure, and that tells you something about the mass of the black hole. But we know the mass of the black hole. So we can predict what that radius should be, and it should be 51 microarc seconds. And what do the observers measure? 51 microarc seconds. So that's sort of one of these things physicists love a lot, that you have a prediction, and then you can actually prove that this was proposed is correct. And from this, you can, again, also measure the mass. So we know that 4 million solar masses, which we knew from the stellar motions, is also true within a few event horizons sizes. So over time, over these 40 years, we started at a large distance, relatively speaking, of about a light year away from the center. On the vertical scale is the mass. On the horizontal scale is the distance from the center. And then over time, we use these stars to move ever closer. And you see what happens is, at some point, the mass stays always the same, all the way to the event horizon, all the way to the event horizon. So that tells us it is really, for all practical purpose, a point source, so to speak, or could be a black hole. Now, there are other discussions, namely how much of that dark matter, which David mentioned, could be hiding there. It turns out, in order to be dark matter to be located there, it has to be very high energy. Unlikely, very unlikely. We cannot exclude it, but it's very unlikely. So we now know in the galactic center the case is pretty damn good. We don't know the spin yet. That will be one of our next cases. Future prospects, well, we now have a star observed, which is in the top left there, which has 10 times smaller radius of approach, 100 Schwarzschild radii. And so there we believe we can see not only the Schwarzschild precession that we've already seen because it's 2 degrees, it's not a few arc minutes, but also the lens steering precession due to the spin. The radio astronomer on the right side, if they have better measurements of this ring structure, they might see photons which are coming around the black hole once or twice, and that's a very sharp, it's very sensitive to spin and other properties. Next, there will be a big telescope, a new telescope in the Atacama Desert in about 3 years, a 40-meter telescope. And with that, we hope to use spectroscopy to get still closer. And then finally, the dream, maybe of your generation, is gravitational waves at in a distant galaxy where a stellar black hole spirals inward to a big black hole. We call this an EMRI, extreme mass ratio in spiral, and that's extremely sensitive to the space-time right at the event horizon. So I put my money on all of this, but like David, not in my lifetime. That will be you guys if you go on. Sometimes people ask that question. This is fine, black holes, but what is it good for? Thank you.
Well, thank you very much, Professor Genso, for giving us a very interesting talk, and also the very inspiring the discussion about how precision measurement can reveal fundamental physics at the center of our galaxy. So now we come to the third speaker, which is Professor. Sorry, I have something wrong with my... You know my name. I know, but I have to introduce you, right? Yeah, well, so we're going to introduce, Professor Hitoshi Murayama. He is, the McAdam Professor of Physics at the University of California at Berkeley. And he is also the Hamamatsu Professor of the Kafri IPMU University of Tokyo. So he is going to talk about, dark matter. So let's welcome Professor Murayama.
Okay, thank you so much, Kambu. And it's a great honor to be able to speak here in this venue in Hong Kong. And I also like to thank the organizers for giving me this incredible challenging task for following on 2 Nobel laureates. So that was really inspiring, and I'm certainly not a Nobel laureate, so it's going to be a very difficult challenge anyway. So I'd like to actually zoom in on one subject, which David already touched on, the dark matter of the universe. And that is a subject where I truly believe that the theme of this physics session, where microscopic world of small and macroscopic world of the universe actually come together. So that's the subject I'd like to talk about. So just to review a little bit about why we are talking about dark matter at all. So this is a picture of the Milky Way galaxy we live in. So our sun is actually in a suburb in Milky Way, 28,000 light years away from the center. And we are actually moving very fast. The solar system is actually moving at the speed of 220 kilometers per second. And so once you actually hear about this incredible speed, you wonder, why are we not getting out of the Milky Way galaxy? Something has to be pulling us to stay inside. And if you actually think about how things can actually stay glued in a location, like in the solar system, or the planets are moving about the sun, and what we know from the Kepler's law is that if you actually move away from the sun, gravity becomes weaker, so the planets have to move more slowly to stay in the orbit. But if you look at the galaxy instead, that doesn't seem to be the case. No matter how far away you go from the center of the galaxy, the stars seem to be moving at about the same speed. So what that means is that the mass in the Milky Way galaxy is not concentrated at the center, but is distributed in such a way that if you move away from the center of the galaxy, you are supposed to see more and more matter coming out. But we don't get to see that kind of mass in a telescope, and hence we are talking about something dark. Namely matter, because it actually leaves the gravity, but it has to be dark because we don't see them in telescopes. So that's the idea of dark matter. And evidence for dark matter not only exists in our own galaxy, but also away from that. So our galaxy is supposed to look something like this. So what we used to think that galaxies made of stars is only a small minority, which is embedded inside this ocean of dark matter, which goes on and on for a much longer distance. And this is a picture of the first picture reported from the James Webb Space Telescope, and that was released by, back then, the US President Joe Biden. And I don't know if he was aware that the picture he was showing was another evidence for dark matter. So if you look at this picture, what you see is that some of the galaxies look extremely distorted and elongated. So no galaxy should have a shape like that one, but you see that this is actually extremely long and stretched. The way we understand it now is that this is actually a trick played by dark matter on you. So that galaxy has a regular shape, but being behind this cluster of galaxies, and when you think of the faraway galaxy to be sort of moving like a river here, then only when the galaxy happens to be behind this cluster of galaxies, the strong gravity due to dark matter would actually stretch it, so it would look stretched, but nothing actually happened to the galaxy. So this is the way we can understand the picture we have seen on a previous slide. And most dramatic example is what is called the bullet cluster in this picture. So this is a beautiful picture of the universe, which is about 4 billion light years away from us. And what's painted in pink is actually a gas made of hydrogen and helium, which got heated up to many tens of thousands of degrees and shining in X-ray. And what is actually painted in blue here is that something you can figure out by looking at this bending of the shapes of the stars and galaxies where dark matter is supposed to be. And one thing which is very peculiar about this picture is that where dark matter is and where the gas is seem to be separated from each other. And that can't be true, right? Because I told you dark matter is holding stars and galaxies together, but here somehow they're separated. And this is one cluster of galaxies. This is another cluster of galaxies. In both cases, the gas and dark matter are separated. And after studying this in great detail, people actually could understand this. This is a collision of two clusters of galaxies at 4,500 kilometers per second. It's an incredible speed. And with this speed, the two clusters of galaxies actually pass through each other. And ordinary gas in the galaxies, cluster of galaxies, would hit each other. Because atoms have finite size, they got heated up, there's a friction, and slow down. But the dark matter just keeps moving as if nothing has happened, and the gas is being dragged along by the gravitational pull of the dark matter that's moving forward in front of them. So this is how we know that even the cluster of galaxies, which is the largest astronomical object in the universe today, is actually mostly made of dark matter, not the ordinary atoms. So that's how we came to the conclusion that much of the matter in the universe today is not made of atoms we are made of, but something totally different, which we call dark matter. And evidence for dark matter even exists on the cosmological scale. And we actually managed to take a picture of the Big Bang that shows tiny variation in densities from here and there, which is the impact of the sound that was propagating in early hot dense gas. And just like listening to musical instruments, if you actually look at the structure of these overtones, you can tell if the music's being played by violin or flute or clarinet. In the same way, looking at this sound wave propagating in the early universe, looking at the overtones, you can tell what the universe is made of. And that again tells you that about 80% of the matter in the universe is actually not atoms, but it's actually made of the dark matter. So that's how we know that dark matter actually is a major component of the universe today. But in addition to being major, the dark matter is actually important for us to exist. So this is the computer simulation starting up from this initial picture of the Big Bang, how universe has evolved since, in 13.8 billion years later. And where the dark matter is a little bit dense, it has a force of gravity that pulls more dark matter in, becomes denser, gravity becomes stronger, pulls more dark matter in, gets even more dense, and so on and so forth. So at the end of the day, you see this contrast between dense part of the universe and kind of empty part of the universe. And in dense portion of the universe, the ordinary gas gets pulled in by the force of gravity. They would interact with each other just like the animation I showed you a minute ago. And then gas interact, emits light, gets cooled down, eventually coalesces to form stars and galaxies, and hence us. But in a computer simulation, you can also study the universe which does not have dark matter in it. And even 13.8 billion years later, there's nothing. No stars, no galaxies, and hence no us. So this simulation demonstrates that dark matter made us. And especially when I give public lectures, I always tell the audience that I regard dark matter to be my mom, because she's the reason why we exist today. So that's something we really would like to understand, eventually meet her and thank her, and that's what research on dark matter is really about. And this is the picture which we actually managed to take in a team by using the telescope named Subaru telescope that sits up of Mauna Kea on the big island of Hawaii. And by looking at these images, which show distortion of the shapes of galaxies, you can create a three-dimensional map of dark matter. And what you see here is 8 billion light years deep, 1 billion light years across, and showing where dark matter is in these contours. And you can compare this distribution of dark matter to where the galaxies are, and you can really see that where dark matter is, you are bound to find galaxies. Where dark matter is, you're bound to find galaxies. So this really shows that dark matter is really the original structure of the universe, namely dark matter really made us, stars and galaxies, and hence us. So one of the best ideas people talked about, what dark matter may be, is the idea called WIMPs. And WIMPs, of course, is just a joke, but it's meant to be small elementary particles that are so weakly interacting that can pass through our planet very easily. And so WIMP actually is meant to stand for weakly interacting massive particle, stable elementary heavy particles that were produced in the early universe. And if this idea is right, millions of these WIMP particles are going through your body every second. Does any of you feel this? The dark matter is going through your body? No? Whenever I ask this question in Berkeley, always some students raise their hand. I guess people in Hong Kong are more serious than people in Berkeley. But anyway, so that has been one of the major paradigms. And to look for these WIMP particles, one thing people have been doing is to go underground, which is very strange. Trying to understand how the universe works, the best place to go is to go underground. In the United States, there is actually a site, which is an abandoned old gold mine in South Dakota, and people actually did go underground and build major instruments down there and looking for dark matter coming into underground location and produces a little kick you might be able to listen to, which doesn't happen very often, but something you can actually look for. And this is the way people have been looking for dark matter. And there are many, many experiments of this type being done. And what you can see is that the experiments have made an incredible stride in looking for this dark matter with more and more weakly interacting nature. And since I got into the field back in grad school, the experiments have made more than 10 orders of magnitude of improvement in sensitivity, which is really mind-boggling. And I should also point out that one experiment in China named Panda X has been very, very competitive worldwide in the search for dark matter. And another thing people have been doing is trying to make dark matter, because it was supposed to have made by Big Bang anyway. So if you can provide enough energy, just like what was existing back in Big Bang, we may be able to actually make it. And for that purpose, people are building these powerful accelerators, the biggest one in Europe, called Large Hadron Collider, so that you can redo the Big Bang in the laboratory. You can't quite make a universe, of course, but you may be able to do a little bang instead of Big Bang, and then you might be able to produce dark matter in the laboratory. So this is an idea of circulating the particle called proton in one way and also in the other way, and smash them against each other to produce the condition which might have existed back in the Big Bang. So this is the inside the tunnel, which is filled with this high-tech machine. And this is the way you can detect particles coming out from this collision. And then what you can do is to look at this collision of protons, producing all kinds of new particles. That's a little band. And you have to make sure that you can capture all of them. And once you actually watch this to extent, you can see what movie they had in mind. And they are very serious people, so they go ahead and even produce this tell-up. So that's how serious they are. So the question, of course, is, can we really make dark matter? So the proton, they are colliding against each other, is not a very particularly heavy particle among all the microscopic particles we know today. So it is like a little tricycle. But what you try to do is really pedal hard and make it go to high speed, and eventually would like to meet them each other in a big collision. So even the tricycle is very light, because of so much kinetic energy after you pedal so hard, that energy can turn into matter, according to Einstein. So the collision of tricycles may be able to make airplane and tank. But if the tanker is actually dark matter, of course you don't see it. But given that there's an aircraft going the other direction, you can tell something is made also in this direction too. So then you know you managed to produce something invisible to you. So this is the way they have been also looking for dark matter. We haven't seen the sign of that so far, but maybe in the future we'll be able to actually detect dark matter this way. But what we know is that this idea called WIMP actually covers only a very small range of the mass, which is possible for dark matter. So if you actually look at the empirical constraints, very heavy one is like a black hole that Reinhardt talked about, but you can actually look for them and you can exclude that possibility. If the dark matter is really, really light, then it's so light that dark matter becomes so fluffy, it doesn't even fit inside the galaxy. So that is another thing that wouldn't work. And in between, there's a possibility that spans over something like 70 orders of magnitude. We know very little about where dark matter lies in these big scales. Another candidate people talked about is the particle called axion. That's a hypothesis at this moment. And even if you talk about some tiny particles, it may be lighter than WIMPs or heavier than WIMP. And an axion-like particle behaves like a wave instead of a particle. It looks like a classical wave instead. And things like a smaller black holes might still be a possibility. So you're talking about composite or macroscopic objects over here, and we have no clues where it actually is. But having no clue is not a desperation, because there are so many particles we have not been able to look for so far. So the minute you start looking, you might be able to actually hit the jackpot right away. So there's an enormous possibility of discovery. So that's something we're very, very excited about in this field. And one small hint we may have on the nature of dark matter is that it may actually be interacting with each other. By looking at the distribution of matter in small galaxies called dwarf galaxies, the computer simulation that tells you how the galaxies form would predict that the density of the dark matter towards the center of the galaxy is very steep. On the other hand, some observations suggest that it's actually not very steep towards the center of the galaxy. So this may be understood, that dark matter may be interacting with each other, they scatter against each other, so that they would disperse themselves to have a much more flatter profile towards the center. And this actually not only a possibility, if the dark matter is self-interacting, over time, it may actually rather collapse towards the center, and that might produce even steeper profile. And that kind of idea is called gravithermal collapse. And so that would actually lead to a much more variety of possibilities in how dark matter and stars are distributed in small galaxies. So this may also be taken as a sign that dark matter may be self-interacting, which means the dark matter is not the point-like elementary particle like WIMPs, but may have a finite size, so they can actually hit with each other. And if you're talking about this kind of the finite size object, that reminds us of the theory of strong interaction, which David Gross talked about earlier today. So it may be made of smaller constituents, namely, it may be dark quarks bound together by dark gluons, giving you a composite dark matter object so that they have a finite size and may interact with each other. So you can actually study what kind of the probability you need for the size of the dark matter, which remarkably turns out to be about the same of size of the proton and neutron, which is made of strong interaction. And we don't actually know if this is the right way to understand it, simply because we still have a lot of things to be understood about what the supernova explosion can blow off the dark matter distribution, so on and so forth. So it's still controversial, but at least it's entertaining to think about that kind of possibility. So I worked very hard together with this postdoc here in Hochberg. She's now a professor in Hebrew University. And so the idea, as I said already, is that dark matter actually has a size. They can hit each other to make the distribution of dark matter different from computer simulation to something that is a lot more flatter. And when people talked about WIMPs, the idea was that these are elementary particles. They may annihilate into the standard model particles in the early universe, and that will set the mass scale for the WIMP, which is about 300 GeV in the energy scale. But instead of having WIMP as an elementary particle, but strongly interacting massive particle, which has a finite size, there is a very interesting possibility called topological interaction, which has to do with the algebraic geometry and topology we heard about yesterday, which gives you this new interaction, which is the 5-point. so that you could have 3 dark matter coming in, annihilate into 2 dark matter, and so that is a self-annihilation process. And if this is the source of dark matter in the universe today, you would predict something like 1,000 times lighter dark matter than what WIMP theory suggested. So even the low energy colliders, like the BCP at Beijing, the EFAN we'll be talking about later today, I guess, may be able to actually look for this kind of light dark matter in the end. And it has to do with this 5-dimensional geometry, which is very weird. But anyway, that's something that works in the strong interaction physics. And this is the quantitative analysis that shows this 300 MeV is really the right energy scale for it. Another more recent idea I came up with, beyond WIMPs and SIMPs, is the idea that there's another topology that has to do with this theory of the bound states of the quarks inside. And that would give you what is called the skyrmion interaction. And this kind of topological interaction is very interested in condensed matter physics these days. And for example, for spintronics application, people actually did create the excitation called skyrmion in the ferromagnets, which may be used for very high density storage. And similar idea actually does work in the theory of strong interaction as well. And this kind of topological interaction leads to a different mechanism of producing dark matter in the early universe called semi-annihilation. So the possibilities are now wide and open. People came up with all kinds of different possibilities, which people haven't thought about before, and that would predict different mass range for dark matter, which had not been looked for before. And some of the colleagues in Berkeley is mounting a new experiment using superfluid liquid helium, looking for this kind of light range for dark matter masses in experiments today. So this is just showing the parameter space of that kind of theory. So the idea is that if you look at the early universe, and if you use a telescope, you can look far away, trying to observe what the universe was looking like early on. But what we know from data is that no matter how hard you look, there's a limit on how far you can look back into the beginning of the universe, which is actually given by this picture of the Big Bang called the cosmic micro background. In order to understand the earlier moments of the universe, you have to use other means, like using particle accelerators, and dark matter was born, presumably, at a much earlier moment than the picture we managed to take with any telescopes. So we would, this way, we like to understand how the universe was like, very, very close to the beginning of it, and then, of course, we like to understand the nature of dark matter as well. So again, putting in the forms of this poetic metaphor, if dark matter is our mom, we are trying to understand where our mom came from, and then we would like to understand what kind of village she actually came from, and this is the way we would like to understand towards the very beginning of the universe. So that's the research I'm doing. So one of my colleagues, unfortunately, who recently passed away, George Smoot, is the first person who managed to take the picture of the Big Bang. So after he received the Nobel Prize, he actually decided to reenact the Big Bang using the Carol Marching Band, which is the band that would actually celebrate the football teams. And this is a really interesting way of showing how a Big Bang looked like. So let me actually run this video for you.
They said we wanted to react to the Big Bang with the guys from your lab. I said, no way, I want the band. Okay, so now I got to tell you what the Big Bang is so you guys can do this before the sun goes down. Okay, so the idea is everything in the early universe was packed together very densely. It may have gone for infinite. We don't have infinite people, so we just have to use what we got. And everything stretched, right? Everything got bigger. And the further away you are, the faster you go. So we're going to want to start at the beginning with everybody packed dense and jostling around and playing high tempo rapid.
So it's the beginning of the universe.
Then at the mark,
it's hot.
Everybody moves apart.
It's expanding like crazy.
The people on the outside moving faster than the people on the inside. And there's a little bit of irregular motion.
Which is quantum fluctuations coming from inflation.
I know you can do this. Right? And then what happens is you're going to coalesce together in groups of 6. Right? So you have to find 6 buddies. And half of you are going to form spiral galaxies. 3 people facing one way, 3 the other, and you rotate slowly as you move out. And the other half form elliptical galaxies.
These are elliptical galaxies.
Round blobs that keep moving out.
Here's a spiral galaxy.
Now, there's a brass section out there called tubas. They make a really spectacular spiral galaxies, a really big one, like our own galaxy or like Andromeda. So you guys get to be near the middle, and you get to make a really cool, you don't have to run out so fast, but you get to be able to orient where half is facing the other way, and you get to rotate with a sort of twist up. And you're like the centerpiece of this whole thing. Go to it. Great, guys.
So I was very impressed when George told me that they didn't even rehearse once to get it done correctly. So that's amazing. But you do have to remember, though, that 80% of people here are invisible because they are dark matter. And George himself is sitting at the center of a Milky Way galaxy, which is supposed to be the supermassive black hole Reinhardt actually discovered. So you don't get to see most of it, but this is the way the universe was actually built. So, thank you.
Well, thank you, Professor Murayama, for telling us how say dark matter is challenging cosmology and particle physics. So our next speaker is Professor Steve Kahn. He is the Dean of Mathematical and Physical Sciences, and he is also a professor of physics and astronomy at the University of California, Berkeley. So he is going to tell us about the surveying the universe. So let's welcome Professor Kahn.
Advance the slides. Press this to advance. Okay. Thank you very much, and thanks so much to the organizing committee for inviting me to participate in this distinguished panel. My talk is entitled Surveying the Universe, and I think it will follow somewhat naturally from the excellent talks we had by David, Reinhardt, and Hitoshi so far. So in the past 10 to 20 years, there's actually been a revolution in astronomy and a change of the culture of astronomy, of what we're trying to do. So if you go, of course, astronomy is a very old discipline in science that goes back hundreds of years. And if you look at human history, mostly what we've done is to build larger and larger telescopes and to look with more detail at individual stars and galaxies and to try to figure out what's going on individual objects. So if you take all of the human history, we've actually only looked at a tiny, tiny fraction of most of the objects in the universe. And the reason for that is we're looking at objects largely, not entirely, but largely one at a time. And so about 20 years ago, there's a recognition that there's new information to be gathered by trying to get a holistic view of the whole universe. Let us try to sample everything in the universe, or as close as we can get to everything. That began in earnest with a project called the Sloan Digital Sky Survey, which was a pioneering project that was first took light in the early 2000s, and it's responsible for a remarkable number of discoveries that have revolutionized astronomy in the intervening 20 years or so. But this process will culminate in a new project, which has just come online, which I had the pleasure of directing for many years of its development, which is called the Vera C. Rubin Observatory. And as I hope you'll see, the data that we intend to acquire with the Rubin Observatory are likely to transform nearly all fields of astronomy, from our understanding of the formation of the solar system itself to the structure and evolution of the universe as a whole, as you've heard a little bit in the previous talks. Before talking in detail about this project, let me make a comment about its name. So the Vera Rubin Observatory is named after Vera Florence Cooper Rubin. Unfortunately, she passed away about 9 years ago in 2016. Vera was known primarily for a lot of the work you heard about in Hitoshi's recent talk. Her measurements provided some of the most definitive and convincing evidence for the existence of dark matter, primarily through the rotation curves of galaxies, the behavior of the velocity of stars as distance from the centers of galaxies. As you heard, dark matter is the dominant form of matter in the universe, but it's fundamentally distinct from all the matter that we're familiar with here on Earth, and it does not interact, as far as we know so far, with ordinary matter. And of course, as David first said, we only know of its existence because of the gravitational forces it appears to exert. We have no understanding in detail of what dark matter is, and it remains, and Hitoshi emphasized this, one of the greatest mysteries of modern physics. So despite her pioneering work, Vera was reasonably well recognized during her lifetime, but she never received the Nobel Prize. Many of us believe she richly deserved that honor. But we're very proud to say that the Vera C. Rubin Observatory is actually the first major US national scientific facility named after a woman scientist. And so we're very proud to have that distinction. Okay, so what is the Rubin Observatory? The idea behind this is actually quite simple. Build a big telescope that can take large format digital images of the sky very quickly so that the entire southern hemisphere of sky, half the sky, can be imaged in detail every few nights. And then do that repeatedly, night after night, for 10 years. So at the end of 10 years, we have roughly 1,000 pictures of every part of the entire southern sky. And you can imagine comparing those different pictures taken at different times. And when you do that, you measure everything that moves in the sky. So that includes all asteroids, comets, something called stellar parallax, which is the slight motion of stars as the Earth makes its orbit around the sun, and the intrinsic motion of stars themselves, which is called proper motion. By comparing the different images to one another, we also measure everything that varies in time in the sky. The sky is actually, we like to think of the cosmos as some constant, absolute place, but in fact, and Reinhard's talk indicated this, the cosmos is actually quite a dynamic place. There are many things that vary dramatically on short time scales as well as on longer time scales. Stars themselves can pulsate, they can explode. There are the phenomena of active galactic nuclei, which are the massive black holes at the centers of galaxies, which are quite dynamic in their light output. So all of that data we will acquire with this telescope. And then finally, you can take all those 1,000 exposures of every part of the sky and add them together. And then you get the most sensitive census of everything in the sky. So in particular, with the Rubin Observatory, we will detect and categorize 20 billion galaxies and a comparable number of stars, about 17 billion stars. 20 billion galaxies is actually a pretty interesting number. And the reason is that, and David talked about this, the observable universe, the universe that we have access to, is actually finite. The true universe could be infinite, but the part that we can interact with is finite. Because as you look further out in sky, you're looking further out in distance, you're looking further back in time. The universe is 13.9 billion years old, and eventually you get to the beginning of galaxies. So the number of galaxies in the observable universe is finite. The current estimates are about 100 billion to 200 billion. So this survey, our telescope, will catalog between 10 and 20% of everything in the universe. That's a phenomenal human accomplishment, I think. Aside from all the science that we'll get out of it, the reason that we should have built this billion-dollar facility is because we can. And we can catalog and measure everything in the universe, or a large fraction of everything in the universe. Okay, so what's unique about this? And it has to do with a quantity that opticians or telescope builders call the étendue of the telescope. It's a French term. The étendue is the product of the collecting area of the mirror times the field of view of the camera. So it has units of meters squared, degrees squared. Now, why is that the relevant statistic? Well, if you think about it, if you have a big field of view, but a small telescope, you can take a picture of a lot of the universe at a given time, but it takes you a long time to get that picture because you have a relatively small collecting area. Equivalently, if you have a very big collecting area, but a small field of view, you can take the picture pretty quickly, but you're only taking a picture of a small part of the sky at every given one, so it takes you many more pictures to cover the sky. So it's the product of the two that matters. Okay, the product of the two, the étendue, is the rate at which you can survey the sky and take images down to a certain depth. And this slide illustrates what's so powerful about the Rubin Observatory. So I'm comparing it here to a telescope called the Gemini South Telescope, which happens to be on the same mountain in Chile that we're located at. And on the left, in blue, with some arbitrary scale, is a depiction of the collecting area of the primary mirrors on the two facilities to the same scale. The Gemini telescope is not the biggest telescope in the world. It's a reasonably big telescope. It has an 8-meter diameter primary. And you can see the Rubin Observatory is similar. It's about 8.4 meters. It has a big hole in the middle, which I'll come to in a minute. So it's really, the collecting area is really an annulus. But in terms of collecting area, Rubin is not that impressive. But next to that, on the right, again with an arbitrary scale, is a depiction of the largest field of view of the camera, the largest camera on the Gemini Observatory, versus the field of view of the Rubin Observatory. And remember, the étendue is the product of two of these terms. So you can see that the Rubin Observatory is dramatically larger. In fact, it's about 10 times larger étendue, not only than any other telescope that exists on the Earth right now, but it's 10 times larger than any telescope that anybody's even talking about building. And there's a reason for that, because to go much larger étendue, it turns out you're looking so far back in space that the galaxies are so small they're starting to blend together. So there's no point. This is the ultimate project to map the universe from the ground. From space, you could do a little bit better. And I'm often asked, well, it's only half the sky. Why don't you build another version of it in the northern hemisphere? And my answer is, it's the square root of 2. That's all you'll get. When we're going this deep, the number of objects is so large, the science is statistical, and the southern hemisphere is just as good a representation of the universe as the northern hemisphere, and in fact of the total to within a factor of the square root of 2. Okay, this is actually a simulated image. I'll show you a real image at the end of the talk. This is a simulated image of one 15-second exposure with the Rubin Observatory, and it's only 1/200th of the field of view in that 15-second exposure. So look at this image and imagine a picture 200 times bigger with that level of detail, and we get that every 15 seconds. That gives you a concept of the amount of data that will be acquired here. And we'll have 2,000 such exposures of every part of the southern sky. So an enormous, enormous catalog, enormous content of information. And so what do you get from doing these deeper imaging over the whole sky? So believe it or not, these are two real pictures of the same part of the sky. The picture on the left was taken by the Sloan Digital Sky Survey. And this is the best survey we've had to date. And then the picture on the right was actually not taken by Rubin. It was taken by the Subaru telescope, which Hitoshi had a large role in. But it's taken at the same depth that 10 years of Rubin will be. So if you look hard, you can see that they are indeed the same picture. There's a bright galaxy at the center, which you can see on the left. You can also see on the right. And then there's a spiral galaxy a little bit to the lower right of that. But look at everything else that you get when you go much deeper. So the Sloan survey was a tremendous starting point in surveying the universe, but it was so far away from everything that's there. And the colors in the picture on the right are representative. These are colors that are taken by, taking the ratios of pictures in different color bands. You can see stars and galaxies come in enormous number of varieties with enormous number of spectra. Okay, so as I said, the idea is very simple. The implications are profound. Why had nobody done this before? And the answer is, it's hard. And it wasn't until the start of the 2000s and on into the 2010s that we really had the technical capability to envision a project this size. First off, just trivially, we needed to find a great site, one that had good atmospheric conditions so we got sharp images, but more importantly, was cloud-free, and cloud-free evenly distributed around the year. Most sites have periods of time when they're cloud-free, but there are other periods of time when there are a lot of clouds. And because we're trying to cover everything in the sky, and stars only come up at particular times, that would distort what we're going to get. And we chose an excellent site in Chile. We also needed to invent a new kind of optical system that could deliver this very large collecting area with a very large field of view. The field of view of the camera on the Rubin telescope is 10 square degrees, which is roughly 40 times the size of the full moon in the sky. So if you look up at the moon on a cloud-free night, the full moon, and imagine a circle in your mind which is 40 times bigger than the way the moon looks. That's one picture with Rubin. As I say, we get that every 15 seconds, and we do it repeatedly over the whole sky. And then, because we take these pictures pretty quickly, we need to constantly be hopping around the sky. So basically, every 30 seconds, we're moving this telescope. And we're not moving at a small distance because the field of view is big. So we're moving at a pretty big distance. And that doesn't work well for most telescopes. Most telescopes, particularly big telescopes, if you move them around, they kind of wobble a little bit, and you've got to wait for it to settle down before you can take the next picture. So we needed to invent a new kind of telescope mount, which capable of rapidly slewing to new points in the sky without wasting time settling after each motion. And our goal, which we've achieved, was to move to the new field within 5 seconds and be ready to take the next picture. And then finally, we needed to figure out, we needed to figure out how to build the largest, what turned out to be the largest digital camera ever constructed. So the camera on the Rubin telescope is 3.2 billion pixels in a single picture. You can't even display that picture on any kind of screen. You would need 1,500 of the world's highest definition TVs even to display that picture at the resolution we take. So that gives you some idea that we're not just sort of looking at these images, we're going to do most of this with computers. And then the amount of data that we collect is enormous. When we started this project, we thought this was actually the most challenging thing. The total data set for the Rubin Observatory will be of order 100 petabytes, which is 10 to the 17 bytes. When we started, we thought that would be the largest data set in the world. Now, as it's turned out, it's not. Big data has been perpetuated in many other domains. We're still up there, but we're nowhere near the largest data set in the world. But the statistic I like is that we're a few percent of all the selfie pictures ever taken with their phones of all the humans in the world. So just think about how many pictures that is. We're not all of it, but we're a few percent of it, which is still pretty impressive. It's an enormous amount of data, and we had to develop a system that could process those data quickly and put them in a usable form that scientists could work with. Now, I mentioned earlier that if you produce a data set like this, it's extremely broad scientifically. Everything from the solar system to the Milky Way to stars to galaxies to the universe as a whole. if you're used to building big projects, like I am and like Yifeng, is you know that you get nowhere unless you can't define hard requirements. So you have to start with requirements. What do I have to do, and how am I going to determine what to build and determine the cost of that? And so we chose 4 main scientific themes to kind of define the requirements on the telescope. The first is probing dark energy and dark matter, and you heard a lot about that already. I'll say a little bit more. The second was taking an inventory of moving objects in the solar system, cataloging all the small objects in the solar system. The third was exploring the transient optical sky. And the fourth was mapping the outer regions of the Milky Way. And I'll tell you a little bit about those and why they're important. So first, dark matter. You actually saw this slide in Hitoshi's presentation. This is an illustration of gravitational lensing by a cluster of galaxies. But I just want to make the point of how you actually make the map. So as Hitoshi mentioned, the light that goes around a massive concentration of dark matter is bent. And therefore, the dark matter concentration itself is like a lens. This is really no different than having a glass lens. So suppose you have a glass lens in your hand, and you want to see it. Now, it's glass, so it's transparent, so you look right through it. You don't see the glass. The easiest way to see the lens is to hold the lens up against a wall which has wallpaper on it. If the wall has wallpaper, you see the pattern of the wallpaper, and behind the lens, you're going to see big distortions of the wallpaper. The idea is exactly the same for dark matter. The wallpaper, in our case, are the dense field of background galaxies. And if you have a concentration of dark matter sitting in front of that, you'll see distortions on that field. This particular illustration is a big distortion that's called strong gravitational lensing. But even rather small distortions you can pick out statistically as differences between the correlations and the shapes of galaxies in the background field. And that allows us to make the map. And because we can associate the redshift of the galaxies, we can tell how far away there is, we actually can make a 3-dimensional map. Hitoshi showed an example of that from hypersupremcam over a small region of the sky. We will do this over half the sky. So it's not only a map of 20 billion galaxies, it's a map of Hitoshi's mother over the entire sky. Then dark energy. David mentioned dark energy. Dark energy refers to the even more mysterious phenomenon, the fact that the universe is not only expanding, it's accelerating. That was discovered in the late 1990s, and it resulted in the Nobel Prize in 2011 to Saul Perlmutter, Adam Rees, and Brian Schmidt. Now, that was a surprising result at the time. Many of us thought that can't be right, but it was later confirmed by other measurements. How is this acceleration of the universe compatible with the attractive force of gravity? You'd expect that if the universe is expanding, everything in the universe is attracting everything else, it should be slowing down, not speeding up. How is it speeding up? Well, it turns out Einstein's theory of general relativity is compatible with that behavior if the entire vacuum of space is filled with some kind of energy field that has negative pressure. And that's what we call dark energy, that negative energy field. As for dark matter, we really have no idea what dark energy is. It's another one of the major mysteries of modern physics. So how do we measure dark energy? Well, the only thing we know about it, to be honest, is that it's making the universe accelerate. So if we're going to try to characterize its properties more closely, we have to make more and more precise measurements of exactly how is the universe accelerating. And there are various methods of doing this. One method is to take an object we call a standard candle that you believe you know how intrinsically bright it is, and then to measure how apparently bright it is as a function of its redshift or how far away it is. That will give you an expansion for the universe. The standard candles we use are objects called type 1a supernovae. They're exploding stars. And for technical reasons I won't go into, we believe that the intrinsic brightness of those exploding stars is known, and we can calibrate it. Another method is to use something called the angular size of standard rulers in the sky. So this is a particular distance in the sky that we believe we know. And then you measure how big is that distance in angular coordinates as a function of redshift. That also tells you about the expansion. The distance, the ruler that we use in cosmology is something called baryon acoustic oscillations. And actually, Hitoshi showed this earlier. That refers to the propagation of the sound wave in the early universe from the instant of the universe until matter and radiation decoupled and the sound wave stopped. That's a fixed scale. Since it's a fixed scale, it's quantized. And you get particular patterns in galaxies and in the microwave background that exhibit that scale. And that scale is knowable from fundamental physics, so that's another thing we can measure. And finally, the technique that I personally like the best is called the growth of structures. And in fact, this was shown in, I think, David's talk about as the universe expands, it started out extremely homogeneous, but the universe is gravitationally unstable, so slight overconcentrations of matter collapsed into larger and larger concentrations. They gave rise to the initial stars, the initial galaxies, and clusters of galaxies, and eventually to life, to us. That process of gravitational collapse is really just governed by Newtonian physics. It's very simple to understand. We can describe it mathematically, but the universe is expanding underneath it. And so exactly how the universe is expanding underneath it controls exactly how fast that growth of structure occurs, and that's a precise measurement we can make. The nice thing about these three techniques is they all come from the exact same data set. These are not three separate experiments. One data set, many different analyses that can be done on it. A colleague of mine who's instrumental in the early phase of this project, Tony Tyson, described it as massively parallel astrophysics. That's what we're trying to do with this program. Now, let me talk a little bit about the solar system. So one of the things we'll detect millions and millions of are asteroids in the solar system. And this is a plot of asteroids that was actually made with the Sloan Sky Survey. And so on the horizontal axis, you're seeing essentially the size of the asteroid orbit. And in the vertical axis, you're seeing the inclination of that orbit with respect to the plane of the solar system. Every point on this diagram is an individual asteroid. And they have different colors because asteroids vary a little bit in their surface composition, they reflect sunlight differently. Now, the interesting thing is, if you take the green points, for every one of those green points, you know its orbit. So you can propagate that orbit forward in time, but you can also propagate it backward in time. And if you propagate it backward in time, you find all those green points coalesce at some point in the history of the solar system. Why is that? It's because they started out as one large object. And similarly, you can do that for the blue points and for the violet points and for the orange points. And you find these collection of objects that formed early in the history of the solar system. But what happened is they ran into each other. And they collided, they broke into many little pieces. Each little piece became its own asteroid and went happily into orbit around the sun. So the study of asteroids is a time machine that tells us about the history of the solar system from the formation of the first objects until its current structure. The other interesting thing about asteroids is they can hit the Earth. And so this is sort of a popular topic in science fiction. You know, maybe there's some killer asteroid out there that's about to run into the Earth and we'll all be doomed. So this is a plot of the number of asteroids as a function of their size. So on the horizontal axis here, the size is either in physical size, kilometers, or in brightness, which is related to their size. But actually, the horizontal top scale is the more interesting. So that's converting that size into the size of the explosion if an object of that size hit the Earth. And the units for that are in megatons of TNT. So if you look at the biggest asteroids on this plot, if they hit the Earth, they would be on the order of 100 million megaton bomb. That's pretty bad. That pretty much destroys the Earth. The good news is we know where most of these big asteroids are, and they're not going to hit the Earth, at least in the foreseeable future. At the left end of the scale, you're looking at the small objects. There are many, many more of these, so orders of magnitude more. So they're more likely to hit the Earth. But below a size of about 100 meters or so, objects of those sizes will burn up in the atmosphere before they hit the ground. So at the left end of the plot, you don't really care. They're out there, but they won't do very much. The red curve on this plot is our current knowledge of the asteroid population up to a certain point. As you can see, for the really big guys that are going to do the damage, we pretty much know where they are. At the very small end, we don't know at all where they are, but they don't do very much damage. But there's a sweet circle right around 100 meters, 10 meters to 100 meters. In that size range, they get through the atmosphere, they hit the Earth, and we don't know where they are. So that's what you're concerned about. And in fact, we only know about a few % of those objects. So surveying and determining those objects is a big part of the guidance. Now, what happens when the killer asteroid hits the Earth? The science fiction movies mostly show it hitting downtown Tokyo or maybe downtown Hong Kong or downtown Manhattan. As you can guess, that's extremely unlikely. What's most likely going to happen is that an asteroid of that size will fall in the ocean. But that's still large enough to create tsunamis all over the world. And because much of the human population is in coastal environments, it's still a very big issue for us to worry about. And the Rubin Observatory will measure those missing asteroids that are hazardous. Let's see, there we go. Okay, let me turn to exploring the transient optical sky. So as I mentioned, lots of things change in brightness in the sky. The horizontal axis is a characteristic time scale for the change, and the vertical axis is how big a change in light, how bright the objects were. And I just show this, that there's many different points on this plot. They have letters associated with. These are things we know about. Various kinds of supernovae, classical novae, other kinds, tidal disruption events, other kinds of events we already know about. But if you notice in this plot, we put the captions on the lower left. So the lower left, all you're seeing are what those acronyms mean. The reason we put the captions there is because there are no points there. There are no points there, not because there's no objects there. It's just we never had the sensitivity to see. So these are fainter objects on very short timescales. That's the new area of discovery space. Every time in astronomy we build a new project that's capable of looking in a way that we never looked before, we find new things. So this is really the discovery space that's quite exciting for this project. And then finally, let me comment briefly on the Milky Way. So the hardest thing in astronomy to measure is the distance to a star. We can measure its brightness, we can measure its spectrum, but it's hard to get a distance. One of the ways we get distances is from parallax, which I mentioned earlier. As the Earth moves around the sun, there's a slight angular shift in stars. That's easy to do for nearby stars. It's much harder as you go to distant stars, where you can use proper motion. Given the 1,000 different exposures we'll have of every star in the southern hemisphere, we can make these measurements much more accurately, which means we can get distances out to much greater distances. Now what that means, if you look up at a relatively blank part of the sky, you see a lot of stars, and you don't know which ones are close and which ones are far away. If you know the distances, you can eliminate the close ones. And then you start to see structure. The stars are not uniformly distributed. They appear in streaks across the sky. What are those streaks? The streaks come from the fact that the Milky Way, as it was forming, there were satellite, smaller galaxies that were in orbit around the Milky Way. And as they, over time, they fall into the Milky Way. As they fall into the Milky Way, the stars in those smaller objects are stretched out by tidal forces into a streak. So by detecting these tidal streams, and we know of some of them already from Sloan, you can map out the history of formation of the Milky Way. And you also map out the dark matter potential in the galaxy, which is very nice because these stars fall in orbits. Okay, so let me talk a little bit about what the Rubin Observatory is. That's some of the science motivation. It's actually a system. It's not really a single thing. It's an 8.4 meter telescope, a 3.2 billion pixel camera, and a very complex data management system. We spent more money on data handling on this project than any other project has ever spent on data system. Usually you build a big project and you spend the money on the hardware and you worry about the software later. We couldn't have that luxury because the software is so complicated. Many, many people involved in this. So let me talk about the mirror. I showed you that the primary mirror is an annulus. Actually, it's two surfaces in one. This is a three-mirror system, so the light comes in, reflects off the primary, onto a secondary, onto a tertiary, and then on into the camera. And so we built an optic that had two figures in it, two highly polished figures in it, an inner region, which was the tertiary, and an outer region, which was the primary. This had never been done before. It was very risky. Just to understand what's required, over 8.4 meters, we had to get those two surfaces concentric to within a millimeter. And we had to get them coaxial to within about an arc minute. So that's very fine control of the polishing. We didn't know whether it could be done, but we accomplished that successfully. And the mirror, it turns out, is not just a mirror or a piece of glass. It's a complex system. It's a highly actuated mirror. Behind this glass, there are around 150 actuators that can push gently on the mirror. Why do we do that? Because as you tilt the telescope, and as the temperature varies, that figure gets distorted. Subtly. It's a subtle distortion, but it's enough to perturb the images. So we have to actively correct for it. So this is a very active system. We're monitoring the focusing properties of the telescope and continuously adjusting for it. And then the telescope mount itself. So basically the mount is just trying to hold these three surfaces together in the same place. That takes a massive structure, 300 tons. It moves at 10 degrees per second and has accelerations of 10 degrees per second squared. To watch this thing move around is frightening, I will tell you. It's just such a large moving structure. This is the real telescope that was installed in the dome. This was completed about a year and a half ago, and we've been testing it since. Let me turn to the camera. I mentioned this is the largest digital camera ever built. It's about the size of a sport utility vehicle. Okay, so it's not sort of a small camera, very complex, many internal components. This is the completed camera on its test stand. We built it at the SLAC National Accelerator Laboratory in a dedicated clean room. And this is the camera that was mounted on the telescope, and it was only mounted this past March. So this was many, many years in development, but it's only finally come together this year. Let me just comment that the use of these data for the Rubin Observatory will be a worldwide phenomenon. We've created, because the data are so rich, we've created scientific collaborations of scientists all over the world that will work together to do the various kinds of analyses. These collaborations are federations of independent communities of scientists. There are already greater than 2,000 people involved, 2,500 different affiliations, more affiliations than people. That's because of people like Reinhard and Hitoshi who are at multiple institutions. And 33 countries, 6 continents, 8 teams. And these various different countries, this is a US project, but we have the data coming to many other parts of the world because they've made contributions, mostly in software or in various science analyses that allow us to use the data. After having worked on this project for 20-something years, the moment of first light is enthralling. This occurred on April 15th, 2005. We had many of the team, not all of the team, many of the team assembled in Chile to look at the first image coming off the camera, and you can see their expressions on their face. This is one of the most fun parts of experimental physics, is turning the thing on and seeing whether it worked. And this is a real picture taken from the Rubin Observatory. This is a picture of the Virgo cluster of galaxies, a well-studied part of the sky. If you look at the center of the picture, you can see a lot of individual galaxies which are clustered together. But what's particularly interesting here, when you have a telescope this big and this capable, it's sensitive to low surface brightness. So look at the triplet of interacting galaxies in the upper right side. You're actually seeing the distortions of one galaxy on another as the stars are stripped off and blend in. And there's many, many such examples of that. Okay, this is basically my summary slide, just to give you an idea of where we are. In last year, we shipped the camera to Chile. We coated the primary tertiary mirror. We installed the secondary mirror. We started with a commissioning camera on Sky. We installed the full camera into the telescope mount. First light was in April of this year. We held a press conference in June to show some of these images that I said. And right around now, as we speak, we're just about to start this 10-year survey. So thank you very much for your attention.
Well, thank you, Professor Kant, for this very informative talk. And also, you have convinced us that the future of astrophysics and also cosmology, as well as human, is bright. Thank you. So the last but not least, let me introduce the Professor Yifan Wang. He is the Professor of Particle Physics at the Institute of High Energy Physics in Beijing, Chinese Academy of Sciences. He is the 2019 Future Science Prize laureate in physical science. So he will highlight neutrinos in the Greater Bay Area. Let's welcome Professor Wang.
So thank you very much for the invitation. I'm just in between before the lunch. I try my best, but probably I will disappoint you. So I will talk about neutrinos in this Great Bay Area. Well, first of all, let me introduce you what is neutrinos. Well, it's the most fundamental elementary particles, which is very abundant in the universe. And you can see from this picture, from cosmic neutrinos all the way down to cosmogenic neutrinos. So they span over some 20 orders of magnitude in energy, and also more than 20 or 50 kind of orders of magnitude in flux, in which some of you are probably familiar with, let's say, the source of neutrinos from supernova, galaxy, sun, Earth, and also our body is actually a source of neutrinos, of course, proportional to your mass. On average, we generate about 340 million neutrinos per day, everybody in this room. And on top of it, you have neutrinos from reactors. Neutrinos from reactors is a good thing. It's very abundant and for free, so we can use these neutrinos to study properties of these neutrinos. So indeed, in this Great Bay Area, we have many, many nuclear power plants. You can see from Taishan, Yangjiang, from Daya Bay, Huizhou, and Lufeng, and so on. So there are many of them. So indeed, this is one of the best places you could do react neutrino experiment. So why neutrinos are interesting? Of course, it's very fundamental, as I said before, and it's the only particles with properties not consistent with the standard model. which need to be modified in a way we don't know yet. And also, it's extremely abundant, as I said before, that on average, it's about 300 per cubic meters in the whole universe. And so you can imagine if it has a tiny mass, has a huge impact to the cosmology. But on the other hand, if neutrino has mass, its mass eigenstate, if it's not the same as a weak eigenstate, then neutrino can oscillate from one type to another during the flight. So indeed, this is the most sensitive way to probe the neutrino mass. And you can see from this formula, if the mass is 0, there will be no oscillation. And if the mass is not 0, there is a possibility for the neutrino oscillation. So indeed, the neutrino oscillation was discovered in 1998 and 2002 for the atmospheric neutrino oscillations and also for the solar neutrino oscillations. And these two gentlemen actually obtained the Nobel Prize in 2015. So after this discovery, we end up a question to understand completely the neutrino oscillation. You can see where 3 mass eigenstate and the solar and the atmospheric neutrino has been measured their oscillation properties and the oscillation amplitude, but now we left over with another unknown parameter, which is called the theta 1,3. So the allowed region for theta 1,3 is here in this region, roughly, let's say, less than 0.1 the value of sine squared 2 theta 3, or very often you call it 10%. And then you look at the precision of the past experiment at reactors, they're typically at the range of 3 to 6%. Now, you see the allowed region is 10%, and you want to see something, say, meaningful, you want to go to a precision of 1%, which means that you have to improve the precision of your experiment by a factor of 10. So how to get this factor of 10 when you design your experiment? So there were a number of, say, ideas to get this reduction of the systematic uncertainties. One is to use the so-called near-fire scheme, so we can reduce reactor-related systematics by a big factor, all the way down to leftover of 0.1%. So you put your detectors very nearby the reactors. And indeed, the arrangement of reactors is so complicated, we have to put 2 near detectors here and there, and then we have fire detector. And then we came up with the idea to have multiple modules per site. So in this case, detector-related uncertainties can be reduced by a factor of 1 over square root of n, where n is the number of modules. So if you build all your detector modules near and far and at each site, you had advantages to have a reduction of systematics, and also it's cheaper because the smaller modules, easier, and you get a redundancy. If one of the modules fails, you still can move forward with your experiment. And of course, the systematics can be canceled out. So, and then we also have multiple muon vetoes to reduce the inefficiency for muons by roughly a factor of 10. So Diabase is actually a very large international collaboration. It is actually the largest China-US collaboration in basic science and the largest DOE investment for particle physics outside the US. And indeed, this is also the largest collaboration among the mainland, Taiwan, and Hong Kong for basic science. So indeed, this area played a very important role in neutrino physics, in particle physics. So we started the construction, the tunnel, about 3 kilometers, and 5 underground lab. And we had to be very, very careful to have a blasting very close to reactors. So you had to make sure vibration to the reactor is within the so-called safety limit set by the National Nuclear Safety Agency. And this is a picture of installation, assembly, and you see how it looks like. I'm not going through all the details, but in the end, after 5 years of construction, we managed to see that indeed neutrinos from reactors are disappeared on their way from the reactor to our detector. The loss is about 6%, and if you translate to sine squared 2 theta 1 3, this is about 9.2%. So it shows that indeed there's a large oscillation amplitude, and neutrino oscillate in this so-called theta 1 3 is actually very similar to other oscillation mode. So indeed, after this observation, neutrino oscillation picture is now completely known, and we managed to improve the precision from first time 20% to 2.8% right now. The most precise measurement ever. You see the size of the arrow compared to others. And the experiment had been stopped operation on December 12, 2020. And indeed, this experiment triggered the next generation experiments like Juno, Hyper-K, and Dune. Juno in China, Hyper-K in Japan, and Dune in the United States. So our next step after Diabase, Juno, this is actually a continuation of the react neutrino experiment and also using the same technology, the liquid scintillator. The goal of this experiment is trying to determine the neutrino mass hierarchy, or the sign of the datum square 3.2. The way we can do it is independent of the CP phase, independent matter effects, so it is very much complementary to other measurement, Hyper-K and Dune. So indeed, this is a unique kind of experiment to determine the mass hierarchy. And we decided to choose this site with equidistant to these two power plants, because by doing this, we can reduce the detector size by factor 2, because the source has been increased by factor 2. So the detector has to be put at the oscillation maximum of theta 1, 2, which is roughly 60 kilometers from the reactor. And of course, this distance made us to build the detector with a huge target mass. I'm going to talk about this later on. This experiment, located at this 60 kilometers from reactor, can actually do, the main motivation for the mass hierarchy, and also it can do a very precise oscillation parameter measurements. You can see that with 100 days of data, we can improve by factor 2 or 3, and with 6 years, we can actually improve by almost factor 10. So this is already the average of all the experiments. Individually, if you compare to every individual experiment, we can improve even more than factor 10. Oh, sorry. So in addition to the react neutrinos, we can study solar neutrinos, supernova neutrinos, geoneutrinos, and also search for proton decay. So this is actually a multi-purpose experiment with a lifetime we expect to be something like 30 years. And indeed, we can study the so-called terrestrial neutrinos at this particular area, the Great Bay Area. You see, this is our detector, and we can study the neutrinos emitted from crust and nearby, you can see. And indeed, this helps us to understand better the uranium concentration in this nearby area. And with the further studies, we would like to also study the mental contributions to the whole, let's say, heat rate of the Earth. Indeed, you can look at the prediction. There's huge difference, and this difference actually coming from different models, and our measurement could pin down the exact model for this understanding of the heat radiation from the Earth. So Juno is a large, again, international collaboration. The project was approved by Chinese Academy of Sciences in 2013 and by other countries the year after. The collaboration now has more than 700 collaborators from 74 institutions in 17 countries and regions. You can see the list, and most of them are European countries. This is a picture of roughly half of our collaborators, 350 roughly. And the civil construction started about 10 years ago, and we just finished the construction this year in August. So this is the illustration of the detect design and also the challenge. Because of the distance from the reactor, in order to have enough neutrino events, we had to have a very large target mass, which is almost a factor of 20 larger than the previous largest experiment, CAMLAN, by factor of 20. And also, we had to have more than factor 5 the number of photons, so that you could improve the energy resolution by a factor of 2, because the resolution is actually inversely proportional to number of photons squared. So how we can get this, let's say, numbers up to our target? So first of all, we have to build a very high, very huge underground cavern, roughly 49 meters over 70 meters height, and a largest acrylic tank which can host the 20 kiloton liquid scintillator, 35 meters in diameter, largest in the world, and the liquid scintillator, 20 kilotons, with a transparency of 20 meters, almost factor 2 better than what we have achieved at Daya Bay, which was already the best in the world at that time. And then we need to have a 20,000 phototubes, which has efficiency for photons by a factor 2 better, because we need this higher number of photons. So this is the design of the detector. You can see steel structure, acrylic, and so on. For the underground laboratory, this is 700 meters underground, so we have vertical shaft, a slope tunnel, and underground you see this complicated underground laboratory with every tunnel some purpose, you can summarize here. And indeed, it was 6 years effort to build this underground laboratory. And for the acrylic tank, which is also very hard and difficult, I'm not going through all the details of technologies, but you can see from this picture the acrylic tank supported by steel bar with a spring. There's a spring in it to make sure that the stress is controllable. And you see the phototube with the clearance between each other of 3 millimeters. And everything is supported by this stainless steel structure. When we finish the acrylic, we have to make sure that there are no defects on their surface. So we have our people going there inch by inch to look for defects. And for inner space, you have no place to stand for. So we have this Caesar type of structure to send people there to the surface of the acrylic to see if there's any kind of crack there and to remove it. And when we finish the acrylic, of course, we have to build the liquid scintillator of 20 kilotons of total mass. So we started from the storage tank, filtration, distillation, and then mixing plant over almost 2 kilometers of stainless steel pipe going down to underground, the water extraction, and the nitrogen stripping, and then we have a test of the background level, and then we load into the detector. So everything has been tested weekly and make sure everything is under control. In particular, the cleanness. The needed cleanness, roughly speaking, is a few tenths of milligrams per 20 kilotons. So this is a huge kind of complications and difficulties, but we managed in the end to overcome it. So this is a complete picture of a phototube. You see 20,000 phototubes of 20 inch, and also another 25,000 3-inch phototube in between this big bulb, clearance of 3 millimeters, so that we have the largest possible coverage of the photocathode. And 3/4 of phototubes are made by a Chinese company called NNVT, Beifang Yeshi. So we managed to increase this detection efficiency by roughly a factor of 2. So this is a video, so give you a better understanding how it looks like. So a lot of water. The largest was more than 500 tons per hour. So every day, some tens of kilotons of water we had to pump it out. These are the installation method, which was very complicated because we had to figure out where people stand in this kind of 40 meters height pit. Safety is very important and, of course, dangerous, and you had to find a way to do it.
Not afraid of the darkest times, our world goes on and on.
Through the hardship, her vision bold and mighty clears the road and lights her pathway. All these clouds will melt to nothing. Our hearts' compass will not waver.
Moon and stars shine, their later light, our rosy future, we all hope so. Our goal stands now, we all know. You train on.
This is to clean the inner surface because there are a lot of dust. So we wash it for almost 2 weeks to make sure that the dust are completely removed from the surface.
You're faced with dreams of more than we can count. We await the day your mystery falls apart.
Will your poetry joins our knowledge tapestry? Will you embrace the world that you know, let us see?
Tune her heads to another side, the brilliant human heart. Spread love from across the world, every member plays their part.
Seize the moment, see the voice in our mental, the time we call it. We will heed this urgent calling for the truths that we are searching.
Every new day will never shrink from challenges we strive to build tomorrow. Our goal stands now, we all know. Neutrino, neutrino. Seize the moment, seize the voice in our mind. All the time we're calling, we will heed this urgent calling for the truths that we are searching. Every new day will never shrink from challenges we strive to build tomorrow. Our goal stands now, we all know. Neutrino.
So the feeding was a very dangerous process. We had to make sure that the liquid level inside and outside has to be the same, and also the air pressure has to be same. You know that daily the air pressure changes because of the weather, so you had to make the sphere breathe with nitrogen, not air, because it's dirtied. So we have a huge storage tank of nitrogen as a buffer to brace for this sphere and for gas in and out. But in the end, anyway, you see this is the measurement of the stress on the supporting bars over time, and these are simulations. And they agree very well with each other, and we know that indeed the structure itself is safe. And these are the properties of water. So anyway, on August 22nd, we finished the water feeding, the liquid scintillator feeding. And then we started data taking on August 26. So the detector actually performing well up to now. The water cleanness is actually in a very good shape. You see the numbers. And indeed, this is a number, almost best number in the world. And for central detector, the background is actually very much agree with our design value, which means that there's no additional dust we introduced, because when we design, we have no idea how much dust we are going to introduce. So this shows that it's not there. We did not really have any problem. And look at the liquid scintillator. The background is in very good shape, -10 to 16, and the attenuation length is more than 20 meters. And if you look at the performance of the energy, the nonlinearity has been calibrated using different radiative sources. It is less than 1%. The energy uniformity using sources at different positions, less than 0.5%. And energy resolution, about 3%, or 2.9% at 0.92 MeV. And the light yield is more than 1,600. Our design was 1,200, so you see it's much better than what had been designed for. So in the future, we will continue to take data, and in the next few years, we're going to make a decision on the mass hierarchy. But we believe that in the next 10 years, oscillation will be fully understood, the mass hierarchy and the CP phase will be measured, and we should focus more on the neutrino-less double beta decays. And these are the current numbers, and neutrino-less double beta decay indeed could have the best sensitivity to the neutrino absolute mass. So the idea is to load isotopes into the detector with a balloon or without balloon using existing, let's say, technologies, enriched xenon or use natural tellurium. And by doing this, you can see the numbers here. Indeed, we are the best sensitive neutrino-less double beta experiment people ever talked about. I mean, not even, say, built. Up to now, nobody talked about the precision or the sensitivity up to this level. So in the end, the summary, you can see this is the size of the diabetic detector, the size of person, and this is a Juno detector and the size of person. That's the difference. Thank you.
Thank you so much, and please stay. Please remain on stage. Now we would like to invite the convener and speakers for this section to have a group photo together. May invite also Professor Kambu Look, Professor Rai Hodkinson, Professor David Cross, Professor Steve Khan, and Professor Hitoshi Murayama. Maybe we can have 2 steps to the left. We can have 2 steps to the left, please. Yes. May I invite one more step to the left to make sure we can have a balance, as we always say, balance. Yes. Then we can have the best photo. Is it okay? Okay. So please have a look to the center. Once again, I invite you all to give a big round of applause to our speakers. It's really insightful sharing. Please continue to have a look to the center. One more to go. And now is the finale of the section. We are about to have lunch for those who register for the lunching. Please follow the instruction to the venue from our helpers. We'll see you soon at 1:30 with different keynote speakers and different insightful topics. See you at 1:30. Thank you. And thank you so much, all the speakers. Please be seated.
你好，陸錦標教授。 你好，陸錦標教授。
Hello, ladies and gentlemen. Welcome back to our Science Symposium. The next session is about computer science, exploring the principles of artificial intelligence. Now, I would like to introduce with you Professor Ma Yi as this session's convener. He is Chair Professor in Artificial Intelligence, Inaugural Director of Institute of Data Science, IDS, Inaugural Director of the School of Computing and Data Science, the University of Hong Kong, Fellow, Association for Computing Machinery, ACM, Fellow, Institute of Electrical and Electronics Engineers, IEEE, Fellow, Society for Industrial and Applied Mathematics, SIAM, Member, Program Committee of the Future Science Prize Week 2025. Let's give a warm welcome to Professor Ma.
All right, welcome. Right, good afternoon, everyone. It is my actually great honor to serve as the moderator of this afternoon's computer science session, entitled "Exploring the Principles of Artificial Intelligence." I'm Ima, and warmly welcome you all to what promised to be a fascinating exploration into the foundation of artificial intelligence. So, as you know, artificial intelligence is reshaping our world in the past many years. Understanding its core principles is more important than ever now, right? There has been tremendous practices, advances in technology, but somehow understanding the core, the principles behind it, has been somewhat lagging. And today, we're very privileged and also honored to hear from 4 exceptional researchers who actually work on the very frontier of artificial intelligence and will guide us through some of the most profound and exciting development in this field. Each speaker will present for approximately 25 minutes. Following the presentations, we'll have a panel discussion and some quick Q&A sessions. Now, let me first introduce our distinguished speakers. Our first speaker is Professor Zhu Jun. He's a Bosch AI professor at Tsinghua University, AAAI Fellow, and Associate Dean of the Institute of Artificial Intelligence. He will share with us his talk, Generative AI from Visual to Physical World. Yeah, please welcome.
Okay, thank you, Professor Ma, for the invitation and the introduction. So it's my great honor to speak here to share some view and some development in my group on the generative AI. So I would like to start from this slide to briefly, to share the concept of generative AI. So from my view, the generative AI is essentially to estimate the density in high-dimensional space. So usually in machine learning, we have maybe million dimension for example, for natural images in the pixel space. So our goal is to build a model to approximate the unknown target we call data distribution. So we have sampled a few IID samples from the distribution. So we want to recover that. So this is a fundamental problem in statistics. So also hard challenge because of the cost of dimensionality issue. So if we look at the development trends, we can at least date back to 80s or 90s. So when we, at the very beginning, we tried to use a probabilistic model to fit the data. So that was usually in low dimensional, maybe just 10 or 100 samples. But in AI, we go further. So in last century, we have many developments on the how to represent the relationship among the features, like we call the graphic model or business net, for example, and also like a Boltzmann machine in the same period. And then we move on to go deeper to build the models that can learn the representation automatically from the data. So which are proven to be very effective to represent high dimension data. So then we go to larger scale. So you see many progress made on the different type of data. So here I just showed just a few examples here. So so if you look at that, so actually generative models is essentially a foundation model. So because the goal is to estimate the general distribution of the data, so which can be like a PX, so it's all just raw data, or you have some human labels you can put as PXY. So this is the paradigm essential. So it means that if you can train this model well for once, so you can use it for infinite. Although the training is usually very expensive nowadays, but if you amortize the cost, actually they're quite efficient. Maybe can serve as a foundation to benefit many tasks. So in this view, actually, so you can see the powerful generative AI models actually is reshaping. I mean, almost all the fields of the AI. So I just list the field and maybe give you some more detail later on. So first one is to generate data, to synthesize high quality data. So there can be different modality like a text, image, code, video, 3D graph, and so on. So there are many models have been developed to do the generation. So of course there are still a lot of issues to address, like to go to more controllable and maybe to generate the more physical, plausible kind of content. And the second one is that we can leverage this foundation model to improve our cover for pattern recognition, for example. So there have been a lot of efforts try to show that. So if you can leverage this joint model well, so you can to be more data efficient. So for example, you can save a lot of human labels when you generate, and also they are also more robust in the OOD scenario. So our distribution, so like adversary examples. And the third one I will talk about is that they can serve as a foundation for decision-making, control, and many other tasks. So I will use these three topics to highlight some progress here. First one is data generation. So I will use the diffuse model as one example to showcase how fast we developed in the area from the very beginning, maybe to generate low-dimensional data to nowadays controllable and highly consistent content. So diffuse model is one example that draws inspiration from physics, so from thermodynamics. They can so I use the figure from Song Yang, my former student. So they consider two process, so-called forward process. So which is like for image we impose noise on the image and gradually convert it to maybe total random noise. And the reverse process is try to denoise, try to generate the high quality data from a Gaussian noise model. So mathematically, we can characterize the process as a differential equation. So we have basically two versions. So one is the stochastic version, and another is the ordinary version. So they are equivalent in some sense that the marginal distribution are the same. So for this process, we introduce neural network to approximate the score function. So the network can be arbitrary essentially. So you can leverage the very powerful functional approximation ability of network to estimate the score function in the probability space. And then we can also develop some numerical algorithm to solve this differential equation for sampling, for generation. So this is a very quick overview of the principle of the diffuse model. So there are some issues, some basic issues need to address in order to make diffuse model to be scalable and to handle high dimension data. So at least three issues here we consider. The first one is the quality of the solution. So one issue of the diffuse model is that people usually fix the denoise noise, for example, to some manually selected value. But this apparently may lead to some suboptimal solution. Although the problem is simplified, so as I list here, so there is a gap between the heuristic value, the quality of the solution between the heuristic parameter and the optimal one. The second issue is that the diffusion process for denoising, you need maybe hundreds of steps to convert in order to have high quality generation. So this lead to like orders slower than the like a GAN or VAE model. So the third issue we consider scalability. So if we observe the development of the models, actually the scale actually didn't increase as expected in the language model. So one reason is that the backbone network actually not very scalable. So they were used to like try UNet, a convolution network for the backbone. So these are three issues we focus on. So this is just summarize some work in my group. Our goal is to try to scale up a diffusion model for efficient generation of high quality content in different space. So we start from the very beginning to analyze to show that actually the original problem has some analytical solution for the optimal variance. So that gives you we call training-free estimate of the optimal variance. And we also developed the efficient solver for the diffusion ODE. So we call DP1 solver, DP1 solver plus. Then we also developed the scalable architecture. So basically we unified the diffusion and the transformer architecture together. We call UVIT, and then we move on to the scalable training. So from the image to 3D and to videos. Actually, one interesting phenomenon we observe that we indeed observe the emergence kind of phenomena of the in the visual space actually. So for example, for the video model, so we observe that we don't need like some adapter or LoRa. So we can have the consistency for the character or subject or even multiple subject in just from the base model. So that's a quite impressive progress in our when we scale up the foundation model. So I show you one very recent version of our model that can actually can do some more controllable and can describe some subtle emotion for the visual content. So I just show you a clip of the content generated by the model. You can see the quality. So actually, all this happened in just last 1 year. So one single year to quickly evolve. Okay, so this is the latest version of the model we released. So it's quite impressive given the challenge of the high dimensionality of the density estimation. So just showcase one example that we can keep a high consistency of multi subjects. Like you can just write a very short prompt to add some subject you want to include in the video. And the second benefit, as I said, is that we can benefit from the generative model to actually redefine or serve as a foundation for the pattern recognition. So this is the very basic principle we learn from textbook, right? So if we know the true distribution of the data, actually we can get the optimal cover. But usually this although this paradigm is promising, but traditionally it's not preferred because in the old models, so we built a lot of human bias. Also, the capacity of the model is quite limited, so they're not preferred over the discriminative approach. But as I said, so given the faster development of the deep general models, so we can fit the high dimension, extremely high dimension data. Actually, we have a chance to revisit this paradigm. So there have been a lot of examples to show that actually if you using the generative approach to do the inference for classification, they have a lot of benefits, like to be very efficient in the human levels and more robust, and also have strong generalization across the task or domains. So this is the benefit we can track from a generative model. So the third benefit I focus on is on the go to the physical world. So I think this is a very important dimension to explore. So I just cited some quotes from Rich Sutton. So he hosted the talk at BAI in last June. So the full intelligent engine should require the learning from experience. So which is beyond the large language model, which just learn passively from the internet collection of data. So I give you one example that how the diffusion model, how the general model can come into the important part. So this is the problem for the we call the offline IO. So which learn from the human behavior, try to learn a policy. So which the pi star is the optimal target we want to learn. But the mu policy is from the behavior. We call it behavioral policy. So mu is a distribution, right? So it's from the state to the action. So this is the part where our powerful general model can come in. So like we can use diffusion model. So this is so-called like diffusion policy. So there are a lot of benefits for using the diffusion, the powerful general model in this case. So first one is that we can leverage the strong capacity of the model to handle the complex human behaviors, which can be multimodality. So like I highlight here for the bi-arm manipulation, you have multiple policies in order to finish the goal of the task. So traditional way may fit do some average of the policy, which can be maybe not the optimal policy of anyone. So by using the diffusion model, we can naturally fit the multimodal distribution, and also we can easily integrate with the development of the foundation model. I give you some example we developed. This is the one we call the robotic diffusion transformer (RDT). So the first version is that we built the billion level robotic diffusion foundation model based on the diffusion policy, try to scale up, and also we collect a larger pre-trained data set with so at that moment we clean up the data from an open source domain, and also we collect like 1 million human demonstration data. So for the model design, we need to unify the action space across the different embodiment, and also we need to do some update on the learning process in order to balance the different embodiments and to avoid the shortcut learning. And then we have a scalable training to handle the nonlinearity and also extreme value in the physical data. So I showcase some results. So they can build on the scalable foundation model. We can generalize to on-scene objects. So like you clean up the cup or to some on-scene scenes with different environment. And you can also using the cross-model inference to follow text instruction, for example. So the robots can controllable to pour like 1/3 water or 2/3 water to the cup. So they can understand your instruction and follow that. And they can even do dexterous operation, like control the dog to go in a straight way and straight forward. So they can do very precise control of the dog. So then a recent version also we just released 2 weeks ago is the second version of the RDT2. So for this version, we try to go further, try to test whether this architecture can scale up to like 7 billion. So in the current version, we tried 7 billion parameters. And in order to support that, actually, we do a lot of work to collect data. So we use a UMI device to collect data from the homes. So we collected hundreds of volunteers to collect data for us. Which is considered like maybe currently the largest UMI data set. We just scale up the RDT model with some technical improvements. And this basically shows quite strong zero-shot generalization on the on-scene embodiment. So I give you a quick demo. So this is from my student. You can see how it works.
We're introducing RTV2, the first foundation model for zero-shot deployment on any robot arms. No data collection, no fine-tuning, it's truly plug and play. And we optimize its speed to ultra-fast for highly dynamic tasks. You want to see the action? Let's get to it.
So this is how the model do the inference. It just do one sentence as a prompt. So the policy we learned it's quite efficient to have the almost real-time kind of response. This is another case to the high dynamic. So diffusion is usually slow. So but we have a technique to detail the policy, which can be even faster than compared to VRA policy. So this is the device we designed. So we collect data from the home. So we recruit hundreds of volunteers to help us. So this data set will be released publicly. Okay, so that's one example that we can scale up this process. There are many more demos here. I'll just quickly go over that. I think the last piece I want to share is that so we have built the video model. So the video model actually is the strong benefit that it's trained on the internet scale video content. So which naturally has a lot of information about the spatial and temporal dynamics. So that can be a rich prior we can leverage it for the robots. So here we just show a quick example that from the video generator, actually we go further by fine-tune on the embodied data for the manipulation. So they demonstrated a very strong generalization ability across the environment, across the tasks, and the things. Okay, so so this is the we call the data paradigms, the period. Sorry, data period we have. So we at a very low level we have a highly noisy the web data, and on top of that we may have like a heterogeneous robotic data we made from different embodiment, and on top of it the embodied human data. So we use a teleoperation to collect the human data. So using the video foundation model as the strong prior, actually we can dramatically reduce the requirement on the human demonstration, like 3 orders more efficient compared to the Pi.5 or our RDT, the first version, like 2 orders more efficient. So here some more results on the generalization ability. So I think from this the examples I showed that I think one lesson we learned is that we can do the scaling scale up in the visual domain. So we can also generalize from the across from the visual to the physical world. But by the key property that we learn in the visual field is that we can capture the high dynamic and spatial consistency in the world. So they very important to they're also important in the physical world. So that's the reason why we can generalize. We can across the boundary. Okay, so with that I'll stop here. Thank you.
All right. Thank you, Professor Zhu. Your work not only pushes the frontier of generative AI, and also shows how learning such distributions of real-world data can help us to do inferences and interacting with the physical world, paving the way for embodied intelligence and can perceive, reason, and act in complex environments. Next, we'll hear from Professor Sailing Xie Sailing, Assistant Professor of Computer Science at the Kurang Institute of Mathematical Sciences, New York University, and a research scientist at the Google DeepMind. His talk is entitled The Multimodal Future, Building Supersense for Superintelligence. Please welcome.
All right, okay, my name is Sailing Xie. Good afternoon, everyone. I'm from NYU, and today I'm going to talk about the multimodal future, building supersensing for superintelligence. All right, so let's start by zooming out a little bit, talking about like phylogeny of intelligence. We can talk about we can go always all the way back to maybe 540 million years ago, where it's like Cambrian period. But I'm gonna focus on this specific period of time where it's like only 50,000 to 150,000 years ago, where humans really developed this so-called behavioral modernity. Right? It's when language, abstract thinking, and symbolic behavior started emerging. So I want to, put it up here because I want to ask you this question, right? Or like I want to imagine, like in a 24-hour scale of, biological evolution, more than human intelligence appears in the final. Can you guess how much time? Yeah, the answer is like roughly 8 seconds, right? I want to give you this analogy for you to think about, right? Like, the period where we developed all this language and abstract thinking and reasoning, this is really just like a very short amount of time in the grand scheme of things. So I guess one question I want to ask, or like many people are very interested in nowadays, is how far are we from ASI, or artificial superintelligence? Hopefully after the talk, I could change your perception in this. But first, I want to quote my colleague and collaborator, Yang Kun. I disagree with many things he said, but these two quotes, I find it really compelling. I completely agree with it, right? So basically, he said most of human knowledge and almost all of the animal knowledge comes from our sensory experience of the physical world. And language is the icing on the cake, and we need the cake to support the icing, right? So, using this famous LeCun's cake analogy, right? There's a maybe sensory experience modeling will be the case body, and then on top of it, you can start talking about like language modeling, etc. All right, so what's the problem of focusing too much on language? I think there's actually a certain risk, right? If you work on multimodal research, you will notice relying too heavily and too early on language can actually act as a shortcut. It will compensate for the deficiencies in learning effective visual representations. So essentially, maybe you're facing models like this, right? Like, your favorite LMs will be just scratches, and your true kind of a sensory modeling actually is not very good. It's far from being perfect. So this might be okay if you're only dealing with internet distribution, data and living in the digital world. But once you want to, get into the real world, I think suddenly all this representation learning will become bottleneck. So my claim here is we actually need to build supersensing for AI if we really want AI to transform the real world. So I want to kind of popularly define this new concept. I call it kind of supersensing by the following kind of like hierarchy or progression. So towards supersensing, I think we're used to this linguistic-only understanding. So there's no multimodal intelligence. Reasoning is confined to text and symbols without any sensory grounding. And the current multimodal large language models have progressed already beyond this stage, yet they still retain traces of its bias. So, this is basically the ChatGPT interface that we use every day, right? Everybody, I think you'll have this on your laptop, on your phone. And moving after this, right, we're talking about like semantic perception. It's really about like parsing pixels into objects, attributes, and relations, right? This corresponds to the strong show and tell capabilities present in the current multimodal large language models. Again, this is something like people use every day, right? You upload one image to ChatGPT or like Gemini models, and then ask a question, and then there will be like responses from these models. All right, so people are working on the next step, which I think is about streaming event cognition. So this is about like processing live, unbounded streams while proactively interpreting and responding to ongoing events. So this is actually aligns with efforts to make multimodal large language models a real-time assistant. So yeah, like you can see all these demos from like maybe Gemini Live or ChatGPT 4.0, where you can just like open your camera and your voice, and then like ask arbitrary questions. But I want to claim that like this is really far from what's needed. Going to next step, I think one thing that's really important, but today's like models really remain limited, is spatial cognition. So this is really about like understanding video as a medium, but like we consider video as just like projection of the 3D reality. Right? So any kind of AI agents, they must know what is present, where, how things relate, how configurations change over time, etc. Instead of just looking at individual pixel frames. This is important because, again, like we do this as humans every day, right? Imagining you're going to a furniture store and trying to buy a sofa for your home, right? You're not really creating a very long verbal, kind of like, legible text. You're forming a mental model in your head and thinking about like whether if I buy this sofa, will it fit in my room, and etc. Right? Like all this is like very visual, and it's really about like implicit 3D spatial cognition. Finally, I want to have this mention this new concept. It's called like predictive word modeling. So this is to say, in order to achieve these super sensing capabilities, the AI agent need to anticipate the future states with an internal model that uses expectation and surprises to organize perception for memory and decision making. So, again, in human psychology, there's concept like unconscious inference and so on, right? But this is like largely absent in the current AI systems. But this is important because this is how we learn, right? When we kind of grow up. There's a kind of science paper from a couple of years ago and showing, oh, actually, if you're a kid, you're actually trying to predicting into the future, right? You are forming this self-updating word model. If you have a toy and that defies your kind of like expectation, you pay more attention to this toy, right? You find it more interesting, and that's how you learn intuitive physics. That's how you learn how the world works. But again, like this is not something that we have with the current kind of large language model-based systems. So, by creating this kind of progression, I want to say, we are moving towards a more task-driven approach to a more, word modeling type of approach, right? By task-driven approach, it means like, really just to, considering the large language models as an extension of basically a search engine, right? You need to ask something, expect feedback. But word modeling, that means like, maybe you'll have your word model inside your mind, and then like, a lot of things can be autopiloted, right? And you just need to pay attention to the surprising or, a form of violation of expectation when that happens. So towards super sensing, where are we now? This is another question. So I want to provide this kind of like pessimistic view or negative points. I feel like the evaluation is not ready, the data is not ready, the architecture is also not ready. But this is a great news, right, for the research that we care about. If everything is done, then like there's nothing to do anymore. But I would argue like there's so many opportunities lying ahead that people just like scratching the surface. So talking about evaluations, like benchmarking all this AI system is super important. We have done this in computer vision, in imperial sensing, in general for like the past 20 years. We started with like many controlled tasks, like just assigning labels to the data set, right? Like ImageNet and CFAR, and then we move on to like structured vision tasks, like for example, object scene level reasoning, detection and segmentation. And then recently, I think people started moving on to like visual question answering because this is like very flexible interface language actually unlock broad querying, but also introduces potential bias and shortcut risks. So, there's a trade-off between diversity and also the language bias. This is important, and I want to argue also, like, we're moving from static kind of like images, we're moving from language to static images, and ultimately, I think we need to kind of like go all in for videos because it's actually will be the ultimate medium. This is how humans perceive the world, right? And then like, a video sequence is not just like a sequence of frames. It's actually, like about the things behind the frames, right? Like for every single frame, you can evaluate the whole space, what's happening there, what's going on, like, the activities and so on. So this is like very important. But if you look at like current evaluations for video understanding tasks or video kind of foundation models, I would say like, people didn't realize not all videos are the same, right? So I would say like without the right benchmark, we risk taking the easy path instead of the right one. So on the right side, I'm showing like all these leading benchmarks for a Gemini model. I'm gonna say this is not enough because we actually did a lot of analysis, right? For all this kind of video benchmarks, there are like many of this, but a lot of them are actually about text recall, right? They have nothing to do with like truly perceiving the visual things or forming kind of like a predictive word model to solve the problem. You can just take like barely like a small amount of kind of visual context, and the language model is doing all the heavy lifting. So we're trying to build more benchmarks. This is like the first paper I'm going to talk about today. It's called Thinking in Space. This is about like how multi-model large language models see, remember, and recall spaces. So again, like I think there's a fundamental, I would even call it a crisis in the current video foundation model or large language model evaluation, because if you look at this, right, like in some leading benchmarks, the questions are like, this VFX thing and asking why the object's flying, or this NASA video and showing which feature of the astronauts' equipment indicates they can move freely in space, something like this. Like it's not easy for human to answer this. Right? But it's actually very simple for a large language model to answer this because they can just retrieve information, right, from the internet, and then like they have like capable skills to give you an answer based on purely text recall. So this is a Maravik paradox for video as well. So some of our benchmark examples are really extremely simple. We're gonna see like maybe here. So yeah, in the audience, maybe you can pay attention to this video. I'm going to play it. And the question is, how many chairs are there in the room? All right, we can stop here. Someone got an answer? Yeah, it's all 9, right? The ground truth is 9, but then Gemini model gives you answer 4, right? If you think about this, this is like very easy for human, right? You can answer immediately. But for Gemini model, it's actually tricky because for every single frame, you have to know, oh, this is the permanent object there. Even if you look at like the same chair multiple times because of the camera change, you still need to count it as one chair, not like 3 chairs, right? You shouldn't kind of like overcome things, etc. So this is actually very difficult for a machine. I have like another example. I'm not going to test you again, but this is about like, if you're imagining you're standing by the nightstand and facing the chair is the closet to the left or right of the chair. Again, like, in order to answer this question, you have to kind of see behind the pixels, right? And then you need to form this kind of word model of the space to be able to really kind of answer this quickly. So the ground truth here is left. Actually, this is a kind of like pretty long video. You're going to see the closet here in a second. But again, like, this is very challenging for Gemini model. It gives the answer like it will be right, which is wrong. So our focus here in this work is to say, oh, if you have all this, egocentric, human viral stream type of like videos, how do humans do this, right? By this I mean like real reasoning and spatial intelligence, and can model do the same, and how? So this is why we design all these tasks to form this evaluation benchmark. We have like multiple tasks like spatial temporal tasks, like appearance ordering, measurements, asking questions about object size, configuration tasks about like object count, relative direction, relative distance, and so on. So after we build this benchmark, we can actually look at like the performance. You can see like actually human can achieve very high performance. It's around like 80%. But for Gemini model, the leading state-of-the-art video understanding model, they can only achieve less than 50%. And for all the open source models, they perform even worse. So we did some like analysis by asking the model to do a form of kind of self-explanation. It's a kind of like indirect signal, but we can still have this error breakdown. And from all the 163 incorrect samples, we see actually 71% of these errors can be attributed to spatial reasoning errors. Right? It's not like the model cannot see individual object in the room. It's not about like, they don't have this good linguistic intelligence and say something wrong. It's really about like they just don't have a clue of the space, right? So, spatial reasoning is actually the main bottleneck for multimodal language models on VSI bench. So I'm going to talk about like new work. This is some of my students, sitting here in our building at NYU. We have this new work. It's not in the, like on archive yet, but we're going to release it next week. So here we're talking about like, how we build even more challenging benchmarks for spatial supersensing. So this is actually a new 2-part long horizon evaluation towards evaluating supersensing. It combines concatenated videos with online Q&A. I'll skip this. I'll just like tell you what we did. So we have like this very long form videos, right? It's not just like a short video for one space. We can concatenate arbitrary long, videos here and there. And then, we use leading general models like, ChatGPT-4o or Nano Banana to insert this really kind of out of context objects like a teddy bear somewhere in your room, right? They can, sit in the bathtub. They can be in the kitchen. And then you ask the model to look at this video and tell you like in which order the teddy bear appeared in the video. So we can put the Stitch and Hello Kitty in the thing. So this is like kind of a needle in a haystack evaluation, but it's also like very much aligned with the viral context. Another important benchmark, part of this benchmark is called like VSuper count. This is about like continual counting under changing viewpoints and things. So we already talked about this, right? Like, but we are actually making more challenging. Now like we're looking at not just like one thing, but multiple things. Just like human will walk from one space to another. If you can count one thing, you can count like to maybe 100 and 1,000, right, without a problem. Again, easy for humans, but extremely difficult for the current models. So when we test, like, again, the state-of-the-art model, Gemini 2.5, I'll skip some of this detail. Let me see if this works. So you can see this is basically Gemini model's prediction, right? So at the like high level, to summarize, Gemini model doesn't know how to count, right? They will count up to like maybe 20, 30, and they stop, right? They will never be able to count up to like maybe 100, despite like in ground truth video, you indeed see like 100 chairs. So this tells of a problem of generalization, right? If you train your models on IID distributed video data, then you are kind of confined to the distribution in your training data. If you have only seen like 30 chairs, there's no way for you to predict up to like 100 chairs. I think this is a very big problem that we have to kind of like raise awareness. So I'm going to quickly talk about like, data and architecture as well. For large language models, it's kind of like, we have a lot of data, but this is really the internet's great blessing, right? Like we kind of get them for free because like, for human civilization, we have the internet, we upload our knowledge there. It's kind of like free for everyone. But if you're really talking about spatial sensing or super sensing in real world, the data really remain underrepresented in today's data sets. This is why we also propose this large-scale spatial sensing data set. We have a whole construction pipeline. We utilize, a real data that's annotated, some simulated data, some unannotated real videos to have this large data set to really try to improve spatial sensing capabilities. For example, we also use like simulators, right? Like we try to see if we can use simulation data to improve kind of real-world understanding of the space. So the conclusion is like the real and synthetic data together provide sources that boost spatial understanding. It's like achieves plus 30% on the VSI bench. All right, but that's not the end. Because if you just like scale up your data, this is still like the previous paradigm. One thing we are truly interested in asking is our architecture design ready or not? By architecture, I mean like a neural network. So my argument here is it's not ready, it's far from ready. Because like spatial sensing or spatial super sensing is so unique, right? Imagine you are like actually wearing AI glasses. We don't have this right now, but in the future, maybe everyone will have this kind of AI glasses. And then it will be infinite tokens in, infinite tokens out, because it will be always on, right? You observe the world as you go, and then you try to kind of store all this information somewhere to help you with decision making. And of course, like for humans, our real world experience, it isn't meant to be processed token by token. To give you like some detailed information here, for human visual stream, it's really extremely high bandwidth, right? From retina to brain, it's like 10 million bits per second. All the sensory input, mostly vision, it's up to 1 billion bits per second. But, like from this perception to hit your consciousness, for this conscious awareness, it's actually very low bandwidth, right? Your brain only needs to process like 10 bits per second, and that's good enough. So most visual data is filtered and compressed before reaching perception. How, right? Like we don't have this for our large language models at all, right? Like right now, for all these video models, we just like upload individual frames and we call it a day. That's not enough. So we have a prototype of like predictive sensing. It's very simple. It's just like large language model. And then on top of it, we're training a small, you can call it a word model, but essentially it's a next latent frame prediction model ahead. And this is to say, now like, during model training, you want to actively predict what's going to happen next. And then you can compare your ground truth observation with your prediction, and then maybe you'll see some violation of expectation, right? Surprises. This is actually how humans regulate what information they take in. So, like if you look at this curve here, essentially, this is to say, at this spike locations, this is something happened, right? This is not something you observed during your training distribution. So here, like, you move to another thing. And here, you can say, actually, there's a novel object. Your model, by doing this training, they will predict into what's happening, and then they will compare this with a real observation. So why this is helpful? It can be used in two situations. So one is you can use this as a memory management for your model. You can actually compress heavily your non-surprising frames and allocate more computational resources to processing and storing surprising ones, right? You pay more attention if you see something that's more surprising. Another thing is you can use this for saying and event test segmentation. That means like your agent can utilize the surprise score to know where they are and tell the difference between just like a scene change or just like slight kind of camera movement. Right? This is super important for this kind of like continual counting paradigm. I'll just like go through some of these results briefly. So essentially, once we do this with a much worse language model, it's just like very small 7 billion model, but empowered with this kind of predictive sensing paradigm, we can actually outperform the leading kind of like large language models kind of like commercially available. So going back to the question, how far are we from SI? I want to mention one paper. It's actually a DeepSeek paper from last week. It went viral on social media and on news everywhere. I won't talk about details, but essentially, DeepSeek is trying to put like visual sensing the first-class citizen. So instead of looking at language tokens, they are looking at screenshots of language like text. Right? So Andrew Karpathy also talked about this. He really liked the paper because I'm gonna make a very strong argument here. Before long, the concept of large language models will disappear. Data will originate entirely from visual and sensory inputs, even for language. Right? It's just like how humans are reading books. We're now processes books into symbolic tokens. We're looking at pages of the book using our eyes. So this is a fundamental shift, and I think from large language model to multimodal intelligence, we must build artificial supersensing before artificial superintelligence. I'm sorry for this poor joke, but I think we are sitting on a very big opportunity here, literally. Thank you very much.
Yeah, thank you, Professor Shea. I think you really touch upon, right? So in the past few years, that the language models seems to capture people's imagination, and many actually believe that's all the intelligence, understanding, or even just capture statistics of text. We're marching to general intelligence, which is, obviously not quite the case. We all know, if anybody knows a little bit about how our brain works, right? We only have a tiny little bit on our frontal lobe that process language. The rest of the brain very much processing visual data, visual memory, and also, of course, small fraction of our brain is processing the motion memory, muscle memory, right? In Chinese, we 大脑, 小脑, right? The big brain and the small brain, and the language just the tip of the icing on the cake, right? Great analogy, right? So I think your work really has shown that only the scalable visual representation is actually the next frontier. It's probably the final frontier. A picture worth 1,000 words. And don't forget about that, right? And providing a foundational advance for truly the intelligence. And our third speaker is Professor Chu Qin, assistant professor in the electrical engineering and computer science department at the University of Michigan. He will speak on exploring parsimony in learning. Please.
So hi everyone, my name is Qing. I'm currently assistant professor in ECS, University of Michigan. So today I want to talk about a journey that we've been went through in the past few years, where we are trying to build mathematical foundations to understand generative AI. And our argument is that if we want to truly understand what this model generalizes and the model behaviors, we need to explore the parsimonious or the low rank, low dimensional, and linear structures in the data and model as well. So as a starting point, in the past decade, right, we have witnessed this tremendous growth of generative AI models. 3 years ago, we have witnessed this moment, ChatGPT moment, right, this language generation. And for region generation, this starts 12 years ago from variational autoencoder to GAN, and more recently to diffusion, right? So this enables both image generation and video generation. And we also see in the past 2 talks, right, this remarkable generation abilities. For example, you can do text-to-image generation where you can just put a model with a text prompt and can generate the content based on the user preference. And in language generation, right, we can use text prompt to generate languages. And more recently, we can do this kind of video generation that you give some text prompt, and it will generate some film-like video claims. This is Google's View model. And moreover, people are also leveraging generative models to do scientific discovery. Right? You can design proteins and discover drugs, and this really accelerates the scientific discovery. But however, despite these kind of remarkable generative capabilities, many challenges and questions opens. So I would argue that one of the most fundamental challenges is about generalization, right? So here our model is trained on finite number of samples. Why we can achieve this kind of remarkable generalization abilities that we can generate new samples and sensible samples, right? And moreover, there are other challenges regarding the efficiency and interpretability, right? So here, nowadays, we are training models with larger scale on larger and larger data set, right? And we argue there's an empirical scaling law, but if we follow the scaling law, right, so we're going to require a tremendous number of samples and model capacity, and this creates this tremendous challenge of training efficiency. And moreover, we are building this kind of black box models. How can we interpret and trust the output of these models? And my argument is that if you want to build a mathematical foundation, you need to explore the structures in the data and also the model. So here I want to use an example about generalization. So I want to try to build some mathematical foundation, try to understand why the model generalizes. And a generalization, in short, is a question about distribution learning. So C P theta is the distribution that learned by your model, where the theta is a parameter of your model. And the question about generalization is how close is the P theta to the true data distribution, right? And this is the most fundamental question, I would argue, in machine learning theory. But there are many challenges of answering this question. I think the challenge here is that we are learning our model on finite number of samples, right? We are constructing a data set, and based on the data set where we have a finite number of samples, and we are learning our model. And if our model has infinite capacity, then our model will be overfitting to the empirical distribution, right? And the question is that, is the empirical distribution truly reflecting the true data distribution, right? This is a question that's central to the generalization of these kind of models. And if you can understand such a question, it can help understand how we can scale our model, how the model works, and also it implies on the safety, privacy, and trustworthiness of these kind of models. So how to answer this question? So here I want to use an example of diffusion models. So as we show in the previous talks, right, diffusion models is the state of vision generative model. And the working mechanism of diffusion models is through denoising, right? So you want to reverse this diffusion process to the underlying distribution of your data. And to do this, the reverse process, essentially you need to learn the score function, where the gradient of the log likelihood of your underlying distribution of your data, right? And how to do this? We're going to approximate the score function using your neural network, right? And hypothetically, we are learning a black box model, and our goal is we want to minimize some training loss, something like this, right? And here, this loss, I'm describing it in the population with respect to the underlying distribution of our data, right? So and then we want to learn the network x theta to approximate the true distribution of our data. But however, because we don't know the underlying distribution of our data, right, we don't know p theta. And in practice, what we do is that we are not able to minimize a loss like this, right? So what we do in practice is that we draw finite number of samples, and then we minimize the empirical loss instead, right? What we're going to minimize is that we're going to minimize something on the finite number of samples. And then the question is that if we do something like this, does the model truly generalize, or they are just trying to approximate the empirical distribution of your data? To answer this question, actually we did a lot of experiments. We truly see that actually this generalization behavior depending on the model capacity and your training data set. So this is an experiment we did on a lot of data set, image data set, and then we made a fixed model capacity where we are changing the x-axis, we are changing the number of training samples divided by the intrinsic dimension of the data. And the y-axis is a generalization score. So this score is reflecting whether the model is memorizing or overfitting to the empirical distribution or is learning the true data distribution. So here what we find is that when we're growing the number of training samples, the model will exhibit a phase transition. So it will be we will have limited samples. The model will be memorizing or learning the empirical distribution. But when you're increasing the number of samples, the model will generalize. So specifically, when you have limited number of samples in the memorization regime, so this is, the first row is showing you how the generated samples by the model. And the second row I'm showing here is the nearest neighbor in your training data set, right? You can see that in the finite number sample regime or limited sample regime, your model is basically memorizing the empirical distribution of your data. But this is not a true distribution that the model is only memorizing. However, when you're increasing the number of training samples, you will see that actually the model will be starting to generalize. So again, the first row is showing you the generated sample by the model. And the second row is showing you the nearest neighbor in the training data set. Right? You can see that actually the model, when you're growing the number of samples, the model starts to generate new and sensible samples that are different from the training data set. And this is where the generalization happens. And how to understand generalization, right? So how can we provide a mathematical theory to explain this kind of a generalization phenomenon when we're growing the training data set? Well, a naive answer to this is that when we're growing the number of samples, right, so the model, the empirical distribution will be eventually interpolate the true data distribution, right? And this could be the simplest answer to this. But is this what happens in practice? Actually, this is not, because we are learning distribution in high dimension, right? And we are suffering curse of dimensionality if we just growing the number of samples to do interpolation. And in the worst case, you can show that actually the number of samples you need to approximate true distribution actually grows exponentially in the dimension of our data, right? Here, P is a number of, D is a number of pixels, right? The pixels can be very large. And then you will need trillions number of samples to make this happen. But if you look at this generalization curve, what do you see? The number of samples to enable generalization actually is much smaller. It's only around like 10,000 or something. It's much smaller than the worst theory predicts. So why there's a gap between theory and practice? What really happens to enable generalization? So my answer is that actually we are not learning arbitrary distributions when we are learning our machine learning models. And actually there's a low dimensionality in the data. And because of this, because the model is exploring this kind of low dimensionality, that enables generalization. So specifically, this is an experiment did by researchers 4 years ago, where they are trying to probe or to study the intrinsic dimension of all kinds of image data sets. And they find that even on ImageNet, the intrinsic dimension is less than 45 or something. And my argument is that to enable generalization, actually the number of samples you need is growing linearly with the intrinsic dimension rather than growing exponentially with the ambient dimension. And that's how the generalization happens. That's why we avoid this kind of a cursed dimensionality, and this blessing of dimensionality suggests that we can use much fewer samples to enable generalization. However, if we want to build a mathematical theory, there's still a lot of challenges. So the first thing is that we know that image distribution are very complicated, right? So they are lying on union of a low-dimensional manifold, which is highly nonlinear and highly complicated. It's very hard to build a mathematical theory just for this kind of a highly complicated distributions. So what we did is that we are trying to build a mathematical theory starting from simple models. And this is a so-called mixture of low-rank Gaussian distribution. So this distribution is simple enough, but it captures the intrinsic dimensionality of our data. So although this is a little bit complicated, but essentially the distribution is describing the data lying on union for low-dimensional subspaces, where for each subspace, the data is following a Gaussian characterized by the mean and the covariance. And this covariance matrix is a low-dimensional, where it can be factorized by UK and UK perp, where the UK is basically the basis of low-dimensional basis of each subspace. You may think that this distribution might be too simple, but actually, based on this distribution, you can analytically derive the optimal denoiser for the diffusion models. And we try to use analytically derived denoiser to generate images. And on this kind of simple data set, you can observe is that the performance of this kind of analytically derived denoiser through this mixture of Gaussian actually comparable to the practically trained neural network, which means that this model actually captures the essence of image data distribution, or at least the linear approximation locally of the image manifold. And based on that, we can develop some mathematical theory trying to characterize the phase transition and sample complexities. So where we parameterize our model simple enough, it's a linear model based on the optimal posture of the Gaussian distribution. And we can show surprisingly, essentially, where diffusion is doing in this simplified setting, where we only have one Gaussian mode. Actually, this is equivalent to the classical PCA problem, right? It's well studied in the statistic field. And for PCA, what we can show is that there's a phase transition. So where the global optimal solution can be attained, where the basis can be attained, only your sample is larger than the intrinsic dimension, right? This precisely captures this phase transition and how many samples we need to enable generalization. And numerically, we verify this on the mixture Gaussian data set, where by showing this kind of equivalence to the classical problem, we can precisely characterize the phase transition and a number of samples to enable generalization. And when K is larger than 2 multiple subspaces, actually we can show that this is equivalent to the subspace clustering problem, where again, the number of samples will be scaling linearly with the intrinsic dimension. And furthermore, this theoretical results has practical implications. So if we truly believe that a model can be linearly approximated, and if you perturb the generation through the low-dimensional basis approximated by the Jacobian of a denoiser, actually you can manipulate the generation in a disentangled way. So specifically, this kind of low-dimensional basis has semantic meanings. So you can manipulate the generation of different attributes through this low-dimensional basis. That in practice, those kind of low-dimensional bases can be derived based on the low-rank Jacobian. And you can see that actually different bases have different semantic meanings, gender, head, figure, etc., and they are disentangled. But you can manipulate different directions in a linear way. However, if you are arbitrary direction to do model steering, actually it doesn't change anything about the model. So which means that actually this kind of low-dimensional bases indeed are existing in the models. So far, we have only talked about linear models. How about nonlinearity, because for deep neural networks, nonlinear is a key. And further, we developed a theory based on a two-layer nonlinear network. We're trying to fully characterize a memorization and a generalization of diffusion models. And here we are considering a two-layer ReLU type of neural network. And we assume that our data is low-dimensional and sufficiently separated, and that our data follows this mixture low-rank Gaussian. So what we can show that the global solution of this mixture Gaussian, this nonlinear two-layer autoencoder actually have very nice properties. So when your model is highly over-parameterized, where you have a much more capacity than the training data set, so this is where the memorization happens. And it turns out, in this case, the model, the training data is stored in the weights. And this is now the case where the model is acting like a social memory, right? They're memorizing the training data and store it in the weight. And in comparison, when the model generalizes, actually the model is under-parameterized to the training data, but in this case, the model is learning the data statistics. So the mu's and the covariance matrices actually are stored in the model weights. And this can be visualized, right? So we run the experiment on this simple setting on the real data set. You will see that when the model is memorizing, so the training data actually indeed is storing in the model weights. And in comparison, when the model generalizes, so then the weights are actually capturing the data statistics. The means and the covariances are now learned in the model weights. Right? This enables the generalization. And moreover, when the model generalizes and memorizes, actually the representations of the model is also behaving in a principled way. So specifically, when we know that actually the weights are whether learning the training data or the data statistics, actually the corresponding representation is acting in a different way and a principled way as well. So what we find is that when your model memorizes, so when you are producing a training sample, the training sample actually will be represented by specific columns. And that's why the corresponding representation is very sparse and very spiky. Right? You have a very spiky representation when the model memorizes. And in comparison, when the model generalizes, they are leveraging the data statistics to represent the sample, right? And that's why actually the representation is dense and smoother. So based on this viewpoint, actually we can verify this on the modern deep learning models, where we are trying to plot a histogram of the representation. And you can see that when the model generalizes, so the representation you learn is much smoother and denser, where the model memorizes, right, the representation you learn is very spiky. When the model generalizes, in comparison, the representation is denser. And also we show this on the stable diffusion on the Lion data set. You can see a significant difference between the representation structures, the density and the spikiness. And this actually gives a way to do a very simple memorization detection. But you can just put a threshold between memorization and generalization representations, and you can detect the training samples, right? And this is the result we showed, where we do this kind of memorization detection by just putting a threshold on the representations between spikiness and the density. And actually our methods not only achieving this state-of-the-art performance, but it's very simple, training-free, prompt-free, and more importantly, this is a theoretical inspired and principal methods to do memorization detection of our models. Finally, I want to argue that the difference in memorization generalization is also reflecting how you're steering your models. And this is the example where we showed where we are trying to learn some concept vectors to steer the model output. And this is basically adding all your painting style to our data. And you are changing linearly of the strengths of steering. You can see that we're adding all your painting style, for the generalized model, right, there's a smooth change from the original data image to all your painted styled image, right? There's a smooth changing of the style. However, when you are steering a memorized model, you can see that actually when you do steering, there's almost no change using the same steering vector. And you further increasing the steering strength, the image will be significantly distorted. So there's a fundamental differences between memorization and generalization. And this provides some insights of how the model works. Finally, I want to conclude here is that this kind of a postmodern structure in data and model not only explains how the model generalizes, but also can provide ways to develop more efficient and more interpretable architectures and model. Specifically, I want just to quickly go through two examples. One example is that we are trying to understand the learning dynamics of when training our large models. And here we are plotting the singular value decomposition of the weights. And actually, you can find that when you're training our model on low-dimensional data, actually, the singular values sorted actually is very low rank, where the x-axis is showing you the training epochs, where the y-axis is showing you the sorted singular values. And you can see that actually the weights are staying within an invariant low-dimensional subspace. And this not only explains why popular techniques like low-rank adaptation works, but also helps us to build low-rank training methods to accelerate our training procedure. And moreover, this kind of low-dimensional structures in the model weights are actually reflected in the representations you learned in the deep learning model. And specifically, if you look at just this kind of a simple MLP type of neural networks, and you will see that when you're training your deep learning model, and if you look at the last layer representation, there's a phenomenon called neural collapse happens, where the time is showing you the learning dynamics. And when the training converges, you will see that the representation actually are collapsing to a very simple structures, which is low-dimensional and linearly separable. And if you look at the intermediate layers of the neural network, actually there's a geometric compression of information across the number of layers, right? So there's elegant structures in the representations of our deep learning models. So to conclude, the take-home message is that our deep learning model is and trustworthy generative AI models. Thank you so much.
Yeah, thank you, Professor Qin. So I think that the research to the role of parsimony and how do you pursue the intrinsic structure of the distribution is actually truly the kind of mathematics interpretation that we need to really understand how generative AI works, and also that also build the foundation we can do better in the future. Finally, we'd like to hear from Professor Wu Jiajun, Assistant Professor of Computer Science, and by courtesy of Psychology Department at Stanford University, he will discuss understanding visual intelligence through physical intrinsics. Please welcome.
Okay, yeah, very nice to be here, and thanks for the introduction, Professor Ma. So actually, I think it's a nice position for me to be at because it's right after Qin, and what we're going to talk about is very complementary. Because Qin just talked about the world has this, the data is not random, it has this lower dimension. And once we have the lower dimension, it really facilitates us to have generalizable learning systems. But now the question is, where is this low dimensional intrinsics coming from? Right? So it's not just not random. Then why do we have such kind of low dimensional intrinsics? So this is where what I'm going to talk about how we can build visual intelligence systems through understanding the underlying physical intelligence as well as the associated physical intrinsics. Okay, So we've been seeing a lot of pictures, and here are some more. And we understand that when we're seeing a picture, it's just not just 2D pixels. There's underlying low-dimensional intrinsics. And intrinsics include, for example, there's object geometry, there's object materials, and the object motions. And all these things are going to interact, and the process of simulating and rendering them in computer graphics is trying to produce these pixels. And for visual intelligence, we often want to revert the process, right? That's why people say vision as inverse graphics. We want to go from an image or a video, trying to de-render it so that we can discover the underlying distribution of this low-dimensional object intrinsics, including geometries, materials, and motions, and stuff like that. So how can we do that? Right, so unlike images, videos, and language, we actually have very little data on the intrinsics like geometry, and we probably have even fewer data on intrinsics like physical properties. So but if we don't have data, how can we apply data-driven methods? So we have been exploring a few different paradigms. I would say maybe 2 of them. And the first one is maybe we can use intrinsics as the inductive biases for self-supervised learning. So what is going on here is I have all these raw observations. And as I said, we want to discover the underlying distribution of object geometries, materials, aligning, camera parameters, and the things we care about. But we don't have annotations on them, right? There's no annotation on the physical properties of the line. But what we do know is how these intrinsics or physical properties are supposed to interact with each other, right? Lighting and reflectance and object geometry, they're going to produce the pictures we see. So we do have knowledge about, from physical simulation, on how these intrinsics can be recomposed into the pixels. If we can incorporate them now in a differentiable way into your learning systems, then now you're sort of like having an autoencoder, but with the inductive biases replaced with these low-dimensional physical intrinsics. And then you don't need supervision for the middle part, right? Because now you can do self-supervised learning, through reconstruction and seeing how well you can reconstruct the original pictures by learning to discover and recompose these physical object properties. So let me just show one example, or actually 2 in this paradigm. So during training, you can train in a self-supervised way on a collection of images and videos without annotations. And during testing, you can take the first half, and you can then even go from a single image and to discover the physical object properties you care about. OK, so the example I'm going to show here is here I have a bouquet of 50 beautiful roses. So we're going to ask the question that is, OK, the roses look kind of different, but we understand that is a rose. They're all roses. In contrast, this is a water bottle. That is not a rose. And this is a microphone. It's not a rose. So what makes a rose, or why do they share the same category name? And why do a rose and a water bottle to be different? Right? So we realize these roses are basically different instances from the same object category. And the fact that they form the same object category is there's a fundamental reason our observation is they actually share the underlying distribution of these intrinsics. Right? You can think about it as there's an underlying distribution to be discovered of the rose geometry and texture. And we want to sample from them. And every time we sample from it, we get a specific geometries and textures, and then we couple it. We're putting a particular pose under certain lighting conditions, and that leads to all the images we see here. So if we can discover and leverage this observation, what we can do is we can learn to sample from underlying distribution and to get, every time, maybe an instance of object geometries and albedo, which is like textures. And then we can put it together in the differentiable rendering pipeline to simulate the rendering process. And then our goal is, OK, once you sample from the underlying distribution and put the rows in a particular pose and lighting conditions, the rendered rows should look as realistic as a real rows. Right? So back then, when we did it 3 years ago, we used a discriminator like a GAN loss. But now you can use all these like pre-trained image and video diffusion pliers. And just by using that very simple inductive bias, what we can do is now we can go from a single image, and then we can render roses from different viewpoints, as you can see in the bottom row, see under different lighting conditions, as you can see in the second to bottom row. And because you're modeling the underlying distribution of the object intrinsics, you can sample from it. You can see roses in different sizes. Right? So the results here, I think they're pretty cool. They're maybe not the best, but for 2 reasons. First, we did it like 3 years ago, and now you have much better models. But second, more importantly, is we're doing everything, all the learning, just from this one single image. Right? There's no pre-training. You're not pre-training on image now. You're not pre-training on lighting. You're not doing any pre-training models. You just train everything from scratch on one single picture. And just on one single picture, you can learn so much, right? With the right inductive biases, you can discover all these. OK, so this was done by my PhD student, Rinju. Okay, and then we thought about, okay, objects are not independent. Once we have a model roses, there may be, can we model multiple object categories as well as their relations? So we look into the cases where there are animals. In this case, we have quadrupeds. And we try to build a system that learns from unannotated internet images and videos and try to discover and reconstruct as well as generate 100 different categories of quadrupeds. You can see we can model their geometries and the textures and their articulation so that you can sort of animate them in the same way. And yeah, this was done by my then postdoc, Elliot, and my PhD student, Zizhang. And once we can do that, we can use it, maybe coupled with some neural rendering methods to do object articulation modeling and animation. For example, you can have an implicit representation of this animal, a bear, and you can move it, right, by leveraging the discovered underlying low-dimensional distribution of the geometry as well as articulation. You can move it, you can scale it, make it bigger, you can remove a part to make the leg shorter, or you can even generalize and produce some of other distribution object geometries. Okay, so this is like, in short, a few examples of this first paradigm. We have a lot more work, but I'm going to highlight these two. But at the same time, I feel like we have observed that there are some issues with this paradigm. In particular, so we have to use here, I would say, a simulator as part of the system. And a simulator is great, because it gives you all the physics and you can sort of get all these things for free. But it also does come with some kind of limitations. By having a physical simulator in the loop, it comes with the constraints that is, first, it has to be differentiable, right? Because you want to do end-to-end neural network training. But not everything can be made differentiable. And even for the things you can make differentiable, maybe they're not accurate enough, but you want some level of accuracy. Or sometimes they're differentiable and accurate, but they're not very fast. And in computer graphics, you can do differentiable ray tracing, which is very accurate and differentiable, but it takes a long time. And unfortunately, if you want to have the system into this kind of end-to-end learning paradigm, then the feed-forward pass, the simulation has to be really fast. So sometimes there's a trade-off between all these factors, maybe eventually solvable in another decade. But at this moment, we cannot solve them yet. And therefore, we have the issue is you can see this idea works really well when the objects or scenes are in domain. But the domain may have some assumptions. For example, there's a single object with a clean background, there's uniform lighting, there are rigid bodies or some level of articulation and stuff like that. Okay, so how can we address that? So this is also the time that we have observed we have a lot of advances in these kind of pre-trained, very powerful foundation models, right? Image diffusion models, video diffusion models, vision language models. And because they can generate all these beautiful videos, right? Maybe by video, by Jing's work. So we wonder, they must have learned something about object geometries and intrinsics and physics we care about. So is it possible for us to distill or extract as much useful information about intrinsics as possible from them? So this led us to explore the second paradigm, that instead of having intrinsics as intermediate representations, is it possible for us to have these low-dimensional physical intrinsics as a grounding or distillation target for foundation models? So I will mostly highlight some results because I don't have time to go into the technical details. But one work we did is led by my PhD student Chen, is we look into what is the intrinsics of object like a flower. There's geometry, there's texture, there's material, sure. But another important aspect of it, what makes a flower, a rose, is its lifespan. Right? So it should grow, it should wilt. So how can we really discover and model a rose so they can see it from different viewpoints, rendering the different lighting conditions as before, but also see the growth process of the rose? And this is the results, right? You can see different types of rendering, different time step of the lifespan of the rose. And the problem is kind of extension of what we showed before. The method here is quite different. We use a lot of type of a distillation from image and video diffusion models and dynamic features and stuff like that. But I have to talk about this offline. And of course, it's not just for roses. You can model all the lifespans of different types of dynamic processes, such as baking bread. And you can see the bread being baked, and so how it changes the shape, but also under different lighting conditions from different viewpoints. Okay. So far, we've been looking into object intrinsics, including like the geometries and textures, and maybe some of its autonomous motion, right? How it may move, animals may move, flowers may grow, and stuff like that. Okay. One thing we haven't talked about is how would they respond to external actions and perturbations, right? If there's a rose, what's going to happen if I poke it, right? So now this requires you to do action condition dynamics prediction of these 3D objects. And the difference between what we did before and this work, which I'm going to talk about, is now you really have to understand the narrow definition of physical properties. So of course, geometry, textures, and materials, they're all physical properties. But maybe usually when people say physical properties, the narrow definition is things like densities or Young's modulus or stiffness. So we really have to now understand and how can we discover these actual physical properties so that we can do action condition predictions. In the case that we have a single image as input or a 3D scene as input, which can also be described, reconstructed from a single image. What you want to do here is you want to respond and simulate how this 3D scene is going to adapt and respond to external perturbations like actions, all these pokings and stuff like that. Right. Again, of course, you want to, because if it's a real simulation systems, you should be able to respond to different types of interactions, not just a single type of interaction, and these are all our results. And the main challenge, as I said, is now you want to have this narrow definition of physical properties, and how can we get physical object properties like stiffness also from these pre-trained image and video diffusion models. And unfortunately, you may thought, okay, it's just one number. What if I just randomly assign a random number? But it doesn't lead to good results. If I just randomly put some stiffness and run a simulation, you're going to get an output like this. Right, it just doesn't look as good. Or if I sample a few times, it's still not very good. Right. So why is it? Well, that's a little counterintuitive to me. But later I thought it could make sense. So just like why vision is hard, right? Because we're trying to discover this low-dimensional manifold, right? As Qing has just been talking about, which is surprisingly narrow, right? But the observation we have, if you randomly sample a picture or a video, it's almost for sure you're going to get random noise. So how can we discover this very narrow, low-dimensional manifold from almost random, very large, high-dimensional observations? And that's why vision is hard. And physical properties, it is also the same case, right? There's only a very narrow definition of physical object properties, distribution of physical object properties that makes sense. And if you just randomly sample, it's not going to give you plausible results. And the object is not homogeneous. It is a heterogeneous object, which means different parts of a flower have different physical properties. So it's just not sampling one number. So you have to sample, in some sense, a field, which is many, many numbers, a high-dimensional space. So random sampling doesn't work. Okay. Then how can we address that? And similar to, or even more so, compared with images or compared with geometries and textures, which we already have very few data. For physical properties, you have even fewer data, right? There's almost no annotations on what's the stiffness of this flower or any flowers. At the same time, as we said, the video generation model seems to be pretty good at producing realistic videos. So we wonder, is that possible for us to get a good estimation of physical properties as well, in addition to geometry, from these pre-trained models? So this is the idea behind our work called a Field Streamer. So this is done by my PhD student Colvin together with the MIT PhD student Tianyuan. So what is going on here? Assuming you already have a 3D representation like a 3D Gaussian, so you can render it into a single image, and you can send it to an image to video generation model. So you're going to get a video out of this image, and the video is supposed to look realistic, right? It's supposed to look, but then it's just a video. It doesn't give you anything about geometries and physical properties. At the same time, you can have material or physical property representations like physics field. You can put that together with the appearance field like Gaussians into a differential simulation pipeline. And here we use the differential material point methods, and as well as a differential rendering pipeline. So then you will get is another video that is conditioned on current estimation of object geometry and the current estimation of physical properties, how the flower will look like under the same viewpoint and same actions. And as I said, randomly assigning physical properties is not going to give you good results. So your reconstruction or rendering is going to look kind of weird. But now you do have a reference video. So what you can do is you can compare the two. And it turns out that the problem is surprisingly simple, that even if you just do an L2 pixel loss in a pixel space, and the loss is good enough for you to go through backpropagation to update and revise your estimation of the material field or of the physical properties, then you can get actually a pretty good estimation of the physical properties by just trying to make this output of the differential rendering and simulation pipeline match the video observations from text to image to video models. So here we have some more results. As MPM, the material point methods are very good for soft bodies, so we have a bit more results on the soft bodies like flowers. But also different types of soft bodies, like cables and stuff like that. And we can even compare to ground truth. We got the ground truth by putting a small fan next to the object, so you can see how the flowers are actually responding to the external actions. You can see our results are much closer to the ground truth compared with the baselines. Later, Colvin also thought maybe I don't want to restrict myself to soft bodies. Is it possible for us to extend the system to fluid? So in one slide, let me just show one of his recent results. You can go from a single video to reconstruct a 3D fluid field. And similarly, you're going to have a physics representation. In this case, it's for the velocity. And you have an appearance representation. In this case, it's for the radiance, so that you can reconstruct the 3D fluid fields. You can render it from different viewpoints. And you can also do action condition predictions, such as how the fluid field is going to look like if you have wind coming from the left. Okay. The real world has really complicated phenomena, and it's fluids, it's soft bodies, but it's really the interaction of all these different objects of different matters. So is that possible for us to think about extending these paradigms so that I don't have individual separate systems for different types of objects, but have one unified system that can handle all these diverse physical phenomena? So that was the motivation behind this latest work I'm going to talk about, which is also from Coben, the PhD student. But he built on earlier work that he did, which is totally separate, has nothing to do with physics though. So what he did in this work called Wonder World is you build a real-time interactive 3D scene generation system that allows users to specify where to generate what, and in close to real time, very quickly see the generated scenes. So here, what the user can do is you can upload a single image, and then you can input your control. The control can be in going forward, backward, turn left, and right, but also in terms of language prompts. So in this case, you have a picture of the Forbidden City. The system converts it to 3D, and then you can go to the left and see it from different viewpoints. And then you want to type in what I want to see. For example, I want to have an ancient courtyard on the left, or I can move to the right, and maybe on the right I want to have a future city or future library or a coffee house. Right, so you can see the system in close to real time can reconstruct, generate 3D scenes that look smooth and connected. And you can navigate, you can do interactive generation. But everything in this work is static, right? There's nothing that is dynamic. There's no movable flowers or fluids or anything. So we want to extend and bring all the dynamics into these generation systems. Right. So the problem finally we want to solve is going from a static to dynamic interactions from a single image. You may have an input image like this. And you want to generate interactive 3D scenes. You want to convert it to 3D. You can apply 3D actions to it. You can drag the rubber duck down. And you can see how the sort of rigid rubber duck is going to interact with fluids. Right? And you want everything to be in 3D so that you can see it from different viewpoints. So this is actually what he did in this latest work called Wonder Play. So let me play a pretty self-explanatory result video. You can see that you can apply different types of 3D actions. And I want to emphasize that the output is also in 3D. So it looks like a video, but it's also in 3D that you can move the camera. You can see it from the right, see it from the left. So it's not just a video generation. Okay, so the idea behind it is actually very similar to what I said before. You can have all these good simulators, but the simulators themselves may have some issues. First, if you want to simulate objects in different matters, it's maybe not accurate enough, and even with perfect state estimation, right? And second, it's actually almost impossible to get a full state estimation, right? That's why vision is hard. How can you get exactly correct geometries and physical properties and everything from a single image? We just spend all the time talking about how we can have a realistic physical property estimation from the visual data, right? So the estimation problem itself is very hard. But there's something good about physics-based simulation. That is, it does allow action condition predictions, right? Because they're based on physics, you can apply different types of actions, and the system should be able to tell you what's going to happen. At the same time, video generation models are sort of, in some sense, complementary. Because first, they're supposed to be very general, right? Any type of images, any types of language, they're going to generate a video for you. And second, they're doing these kind of implicit, scene completion, right? Because they have learned all these kind of visual priors about what a natural video or image will look like. So going from a single image, even with a lot of occlusions, I should be able to complete it. I can give you observations from different viewpoints. But the issue with video models is, at least right now, maybe in 5 years with Signing's work, this will be solved. But at least right now, they still cannot really take very good actions as input. They can take some level of actions. Maybe in Genie 3, you can go forward and backward. And you can take language as input. But there's a gap between these kind of action specifications versus the action specifications you may want, for example, in robotics. Right? For example, if I'm trying to grasp this controller, right, there could be multiple contact points between my 5 fingers and the controller. And every contact point and the magnitude of forces may matter, right, may lead to different outcomes. And these kind of very detailed action specifications is still not supported. And probably in the short term, not going to be supported by any video generation models. So they do seem to be pretty complementary. So the idea we have here is maybe we should just build these kind of hybrid visual physical generative simulators. So if we go back to the diagram I had at the very beginning, right? So we have, paradigm 1 is we have physical object intrinsics as the intermediate supervision. Paradigm 2 is I try to distill these physical object intrinsics from pre-trained video generation models or any type of foundation models. But now, in our hybrid formulation, maybe it's an integration of the two, in the sense that, on one hand, yeah, you're distilling these physical properties from pre-trained video foundation models. At the same time, you're using the same set of physical object intrinsics to guide and maybe to condition these video generation models so that they become more physically plausible, and they can take much more diverse types of actions as input. So I'll just use one slide to highlight how the system actually works in this case. So we have a single image as the input. And what I'm going to do is I want to build this kind of hybrid, right, generative simulators that has a physical simulator as well as a video generator as part of it. So what I'm going to actually do is I will first convert a single image into the 3D scenes. And as I said, it's not going to be perfect, right, because of occlusions, because of missing observations. You can get some imperfect 3D scene reconstructions. But you can still send this imperfect 3D scene reconstruction into a physical simulator, which is going to give you some kind of core simulation output. Right? In some sense, you can say this is roughly intuitive physical simulation. You can see how the fluid is supposed to interact with the shoe. But if you look very carefully, you'll realize there are a lot of artifacts, right, with the shoes and stuff like that. So it's not very high quality. But it does give you a good intuition about how physics is supposed to work in this case. And then what you can do is you can use the simulation output as conditions for your video generation method. Right? You can extract optical flows or depth map and take these as the conditions to send it to a video generation model, which is supposed to generate something that also aligns with the physics you already have, but make it much more visually realistic. Right? So you can see here, the thing looks much more visually realistic, but it becomes just a video. It doesn't have any underlying 4D representations. There's no physics and stuff out of it. So the final step is now what we can do is to refine our estimation of the physical object properties to match the video observations. Right, so that because everything here, the physical simulation is differentiable, so I can refine my underlying representation in 4D to match my video observations so that it gets the best of both worlds, in the sense that it maintains the 4D representations, right, so that it is physically plausible. You can see it from different viewpoints. But now, at the same time, it looks much more visually realistic. And you can use it now for different types of objects, right? Not just fluids or deformed objects. You can see how the rigid body is going to interact with fluids, how it's going to work. You can having wind to a different direction of the cloth. You can having the rigid shoe to interact with the fluids, but you can drag the shoe to the left and right and see how it's going to interact with the fluids. You can have rigid bodies colliding with each other and stuff like that. And because it's action condition prediction, you can go from the same scene, and you can apply different actions to it. They're going to look still pretty realistic. Again, everything here, you have a 4D underlying physical representations. This is led by my, again, PhD student, Koven, in Zhejiang. OK, so to summarize, I have 1 minute, perfect. Yeah, so to summarize, what we have been doing is we want to model, including reconstruction, but also generation of the 4D world by looking into what's the underlying lower dimensional physical intrinsics, by also thinking about how it can integrate with learning systems or foundation models and with physical simulators. So there's always this question, right? In some sense, I think Qing's entire talk was devoted to it. It's about what should we model and what are things really being learned. And so the question we want to understand is, what really needs to be modeled, or what are the underlying inductive biases needed by these learning systems? How do they help visual understanding? What's the role of physics? And what's the role of learning? And our answers to it is, we want to discover and based on discover and develop these visual understanding systems based on causal, physical, and universal object intrinsics. The nice thing about these physics-based object intrinsics is they're very universal because everything we observe, right, is an underlying process behind, like geometries and light, how they're supposed to interact with each other, physical properties, how they're supposed to impact the visual observations. So it is very universal. It is also causal. I think causal is really important because it directly allows you to apply different types of perturbations and make different types of action condition predictions, right? Because that's how physics engines works. And it allows you to leverage the preaching models, which has seen a lot of in-the-wild data, right? So you do make effective use of in-the-wild data. But at the same time, you can leverage the power of physical simulators and potentially synthetic data, right? And finally, as Qing said, I think we have exactly the same key terms, and it brings you interpretability in a slightly different ways, though, just like a physics engine, right? You can change geometries, you can change physical properties. It brings you that level of interpretability as well as physics-based controllability. Thank you.
Thank you so much, and please remain on stage. Thank you very much for sharing.
Yeah, thank you, Professor Wu. So really, I really appreciate that your approach to bridging computer vision, machine learning, and computational cognitive science, and even physical modeling, to offer a unique and profound perspective on how truly intelligence is all about, right? Do not forget, right? So the reason we develop intelligence is precisely to predict the physical world, modeling and predict for the physical world, right? I think the past few years, some empirical success of large language model gave people probably the illusion, right, that is intelligence. But as one of my colleagues I learned from said, in fact, today, just use a little bit of common sense, you'll go far, far beyond what the current large language model knows about intelligence. Okay, yeah. So. To follow up, we would like to, I believe there's a lot of questions after all the talks. I invite all the 4 speakers back to the stage for a quick panel discussion and some Q&A. And we can have a little bit more in-depth discussion for some of the topics that has been touched upon by your speeches. Thanks, please, welcome.
Yeah, may I invite our moderator, Professor Mara Yi, our panelists, including Professor Qu Jing, Professor Wu Jiajun, Professor Xie Xiainin, and also Professor Zhu Jun. And before we proceed to the panel discussion, just a warm reminder for those who have registered for the Hong Kong Science Museum Guide Tour, please gather at the reception at 3:45. So because our speakers are ready, I pass the stage to Professor Ma. Thank you.
All right, thank you for the introduction. So again, you have heard all the talks, each of the. I think I just want to let you know, right, the 4 speakers are very much the very pioneers, frontiers, the first 3 researchers, and they're very, very extremely well known in the field of artificial intelligence. We were really lucky to have them today to maybe discuss a little bit further. I'll start with the first speaker, maybe Professor Zhu Jun, right? So, I mean, I think your research really showed that from generative model that and be able to learn data such as even not just visual data, but also from the motion data, that be able to start to bridge from the the virtual to the physical world. And could you please also elaborate what would be the remaining key challenges in ensuring that those models truly generalize reliably in all the real-world physical environments and also tasks, and how we might be able to bridge some of the generalizability gap, right?
Okay, yeah, that's a very good question. So, yeah, in terms of challenges, I should say there are many. I mean, so although I showcase some progress like on the visual field, the content we generate, and also we try to transfer to the physical world. So that's just the very beginning. I mean, that just show the possibility to do. So there for technical part actually, even for the visual domain actually. So when we do for the video generation, we especially put a lot of efforts on the consistency of the subjects. So like for one single object, a single character. So that's the starting point. We like try to keep the for example the ID consistency across the firm. Then we move on to the subject, the not only human. So maybe some commercial products, for example. So also keep the whole body to be consistent. Then we move on to the multi-subjects. So that's but one impressive actually phenomenon we observe that. So when we scale up the for example diffusion model on the videos, actually they do demonstrate some emergence of such a consistency. So usually people use some plugin like LoRa or adapter on top of the model to fine tune, but we find if you have a strong, a large scale, well-trained foundation model, so all these consistent can be much easier to achieve compared to if we used to do a lot of work, try to like using LoRa fine-tuned model on top of that, but that doesn't work well. So by now we, as I show you very briefly, so they using a model can do quite well, but I think again it's not sufficient. I mean for the to fully control the generation. So especially when we move to the physical world. So I think the judge make a very good point on that. So in the physical field, actually we have a lot of constraints. So I think for the video in general, so especially we learn from the internet. So they basically imitate the common intuitive physics. I mean, so like if you draw a ball that fall down, right? So this kind of a common physics. But if you go too precise, if you want to like precise control the movement of the motion of an object, so it's not enough. So I do agree that so in order to have more physical plausible generation, so we need to go to hybrid. So to bring in more like a physical principle into the model. So that's also one point that I like a diffusion model because it's originated from physics. It's defined on the thermodynamics, but we can go from there to tend to more broad physical principles, especially represented by different equations. So that's the where I mean precise direction to work on. So also in the physical domain, so the data scarcity is much more challenging compared to the virtual field. We have for example, currently the largest the embodied data maybe like just a meeting trajectory, just a meeting human demonstrations. That's much smaller compared to the like the internet videos. So we use it to train video or Sora. So we have billions like video clips to train that. So that's a huge gap there. So that's also drive us to ask whether it's possible to transfer using the internet kind of train video foundation model. So that's why we do that experiment with we call VIDA to try to using the spatial temporal prior we learn in the virtual world to transfer to the physical world. But that's just start. I mean, so there's still a lot of work to do. So we also try to also for the model. So it's not necessarily in the pixel space. So we have to go to the internal world to learn the representation effectively in order to generalize. Yeah. So yeah, I just add a few points here. Yeah. Thank you.
Yeah. Thanks for Zujin. Yeah. Thanks. And also that now maybe move to Professor Signing, right? So your talk really mentioned that we should really focus on our future study of intelligence, which is an exciting research topic, moving from the current language-centric models to really multi-sensor, multi-model centric learning. And I completely agree, right? I mean, in the sense that language is a representation we learned about the multi-model world. And And then now, I mean, you also mentioned that the architecture is also not ready. I just wanted to follow up on that. So what do you think, right, in the future, if we do multimodal learning correct, what would be the language, the role, what kind of future architecture would it look like to integrate language to interact with the multimodal learning or perception? We learned about the multiple senses.
Yeah, it's a really great question. First of all, I think this is such a special panel because I think large language model is underrepresented here. It's like really rare to see. But I think this is really great. But this is also like very open question here, where I don't have like concrete answer. This is like our everyday research. But at a high level, I'm kind of envisioning a future type of architecture. And by the way, this is not just like my imagination. I think I can see a clear trend, like everything is converging into this, kind of like architecture, where you'll have like the representation foundation. You can call it word model, whatever, as the foundation part. And then you can talk about like whether you want to decode it back to something else. If you want to decode this back to language tokens, you'll have like a multimodal large language model. If you want to decode this back to pixels, then you have like diffusion model for image or video generation. Or if you want to decode this back to like a action model, then you have like maybe VLA, like vision language action model for robots. So I feel like right now it's like not like this architecture does not exist. Actually, we do have this architecture, right? We just have a different perspective. If you look at this multimodal large language models, at the beginning you will have this representation that look at like your visual data and then try to provide context to large language model. But if you shift your perspective and think about this, right? Right now large language model is so big and your like vision representation part is like so small. But in the future, I think the foundation part need to be more advanced, more robust, much bigger. Then the language model part will be just like a hat on top of it. So that's kind of my current take.
Yeah, I actually like your characteristic, right? So I mean, even we know a little bit history, even the evolution of our understanding of intelligence starting early days, right? Whenever we understand a little bit, we become a little bit obnoxious. Every time we have to hit the wall before we become a little bit humble and try to learn a little bit more from the nature, what we don't know. But if you look at the structure of our brain, right? The fraction of processing language is a very small area. But the visual language is very, very opposite to modern multimodal, so-called multimodal language models, right? The visual part is actually pretty tiny, and the functions are very limited. But the language, we spend the rest of the model is huge. It's actually just to memorize the language. So, which is completely opposite to our visual cortex or our cortex of our brain, right? So this is actually very interesting that I think maybe future architecture we might have to learn from how nature address physical models, learn the world models, right? And I agree. I mean, maybe the right models is still not there yet, but definitely we have a couple of lessons to learn, right? And again, I mean, thanks for your notice, right? This panel is a little bit, language model is kind of underrepresented, which actually is by design. Don't forget, this prize is for future science prize, okay? Not the past, what has done in the past. So I really like, Siding pointed out, there's just tremendously wonderful problems ahead of us for research, if you care about academia, for research, right? Rather than just chase what the industry has been doing, what's popular, and this is exactly what this panel is. And on our front, and also another job of academia is also not only to identify what are the open problems, but also what are the fundamental principles behind what we have done. I think that's touched upon by the Professor Qu Qing. He's been one of the pioneers in understanding the mathematical principles behind what is the generative model is truly doing. So the computational mechanism, right? So I think you mentioned the principle of parsimony in learning, emphasizing simplicity and structure. So of course, in the era right now, everybody's saying that every larger models and data sets, how can we practically enforce parsimony without the sacrifice in performance? Are there specific architectural and training strategy you find promising or emerging?
Yeah, thanks, Yi, for the great question. I think this question is very good and timely. But I want to put this in a broader scope. I think it's not only the architecture, but I think as a signing side, there's three aspects that we need to work on from industry to academia. How can we design our architectures? How can we curate our data for training of those models? And also, how can we evaluate our models? And I think for both, all these three aspects, we need to take the data structures into their perspective, right? So when we are collecting our data to train our model, I think we need to pay attention is that we cannot, like, nowadays we collect, we need to spend a lot of effort of cleaning our data, and even we are running out of data, we need to generate synthetic data to increasing the volume of the training data to train our model, right? So I think if we know that our data is low dimensional and has kind of parsimonious structures, so this can be guide us to cleverly to collect our data, right? We want to increasing the maximum entropy of our training data, right? As we can see more the task or more type of data by increasing entropy rather than just collecting the data arbitrarily, right? So I think recently we also have the work to study this kind of model collapse issues, where if you just, we develop a smart way to collecting and filtering the training data to grow our training data set. Actually, we, by incorporating this into the synthetic data generation for training our data, our training model, actually we can significantly boost our performance. On the other hand, when we're designing our architectures, right, there's so many ways that we can change or modify our architecture, right? And the theory actually really can help us to guide us in a more efficient and smart way to design our model. And this also emphasizes the difference between industry and academia, right? So in industry, people are believing in computation, and they are just trying to follow the empirical law to scale up our model. I think for academia, we don't have this kind of resource. That's why we want to scale our model smartly, right? We want to build a model from the first principle, following this kind of low-dimensional structure, that precisely building our model, leveraging the low-dimensional structure, right, to removing the redundancy in the model parameters, to scale a smarter and efficient model to achieve a better performance. And this creates opportunities for academia when we don't have this kind of computing resources compared to academia, industry. Thirdly, I think another challenge your signing highlighted is how can we evaluate our model, right? So I think there are so many like old-fashioned evaluation strategies. For example, in diffusion models, the classical tool to evaluate is we're using FID scores, right? We just memorize using this kind of a FID score to measure the image quality. But I think the generated model creates new challenges, whether the model is generating or is memorizing, right? We need to evaluate this kind of capabilities as well, right? So I think this is, the theory really plays a key role. How can we develop evaluation prototypes to better evaluate the new capabilities and also to evaluate the certain concerns of safety of our model, right? So in that regard, I think the parsimony and low-dimensional structures really plays a key role. And also, I think in Jia Jun's and Professor Junzhu's talk, right, this kind of low-dimensional structures really plays a key role in achieving this kind of remarkable generation capabilities.
Yes.
Thank you.
Yeah, great. Yeah, so basically we say, you know, I keep saying these days, right? Industries make things better. Academia make things right, right? So this is the way we work on different dimensions. That leads to the next question, right? We observe, right, there are people, you know, judging, you mentioned, see, one people, we can, there are two, to me, there's two approaches. One to build a sort of, you know, combining languages or to the real world physical models. One is that we start with a language model, and there's a lot of people say, let's keep labeling more data, pair the language and vision, language images, language videos, and hopefully we can ground the current language model better and better, right? There's definitely industry believes that. That's why they are labeling increasingly more and more data. Then through the making the binding better and better, clips and everything, right? Another approach, but actually you're suggesting is that more from the, directly to using physical intrinsics, right? Similar also echo is what Siding also said, right? We want from the visual data input to learn the physics, learn a model that is physical, causal, and so on. And but which approach? Of course, it may be too early, but which approach do you believe it's more scalable or fundamental to really achieving future general visual intelligence, either through continuous refining, grinding things better with more data, more scale, or start from almost from scratch, right? Learning a visual representation with the world through different learning processes. Which one, you think? What's your opinion? Yeah.
Right. Well, yeah, I think thanks Yi for the question. I think of course there is a different, maybe even more like different philosophies, but also at the same time, I think sometimes people are exaggerating by emphasizing there's a false dichotomy, because in practice, maybe it's not like there's A or B situation. There's a spectrum of approaches. And even in my talk, when I say I want to discover physics and think about how it can be integrated, or intrinsics, how it can be integrated into learning systems, I say there are two paradigms. And eventually I say, okay, there are ways to integrate the two paradigms. So it's not even just A or B situation. But specifically, to directly respond to your question, whether A or B is more popular or more promising, I feel first it's in some sense, I think it's very much dependent on the domains you care about and the applications. For example, if I work on a domain where I really require approval guarantees, like rocket science, I want to send a rocket to the space, and I have very good knowledge about the domain. I have studied all the physics and aerodynamics, and I have a lot of approval guarantees from them. Then it sounds like physics or intrinsics to play a more important role. But for other applications, if I work on entertainment, I just want and the most important is to make it fun for people to interact with, so I can make a lot of money out of it. And I don't care too much about the performance guarantee, because if I make a mistake and the person penetrate into the wall in the computer games, it's fine, right? People just laugh at it. So in that case, maybe it's fine, so that we can have a more data-driven approach, because it's true that especially let's say in games or entertainment, domains you want to tackle is very, very general, and these data-driven methods are supposed to be in some sense more general. Of course, it depends on what you mean by general. So I say, yeah, first it sort of depends on the applications and the features of these applications. But second, also, I feel there's a slightly maybe different perspective is, I think the role of having some physics. Sometimes I feel like it is not for machines in the sense I want to build better systems. It is maybe more for humans, for us to better understand the systems, and maybe eventually we'll help build better machines. But even before that, we want to understand the system better, just like why you want to have, Newton's laws, right? The physics is always there, but we discover, or Newton's discovered some of the laws there, or Einstein discovered some laws there, so that we better understand the world. In some sense, it didn't directly help in address physical problems, but by having a better understanding of the universe, or now with the AI systems, you have the understanding of the physics of the AI systems, then fundamentally, eventually, it will potentially help us to build better AI systems. And I think I should stop here, because someone is...
Okay, so. Yeah. Thanks a lot. Thanks a lot for the very insightful answers. I just want to summarize a few sentences, right? So that also in the light of the sort of the spirit of the Future Science Prize, right? Really that from today's talk, I think hopefully that we understand that despite the fact there has been tremendous technological advances about intelligence in the past few years, 10 years, but the scientific and the scientific principles and the mathematical principles behind intelligence are the truly exciting research agenda for the upcoming era, right? And really that a lot of people like here, those are the very, as you can see, they're a very young generation. They're passionate, they're excited, not because of what the past achievements, is that they see the opportunities ahead. And we barely scratch the surface about understanding intelligence. And at least I think academia, we see that now. And I really encourage many of the young generations, if you're really keen to have a career in research, in science and in mathematics, and this is, this could be a better time to study intelligence. Probably not for the reason you saw on your social medias, okay? So go a little bit deeper, and a little bit further, look ahead, and there's a wonderful, bright future. Thank you very much for your wonderful speech and answers. Thank you.
Thank you so much. And could you please step forward? We have a group photo together.
Okay, good. I will take a picture.
And then don't forget your big smile. Or may I invite one step to the left? Okay. Then we can get closer to each other. 1, 2, 3. Is it 1, 2, 3? Few more to go. 1, 2, 3. Okay, one more from our another official photographer. Okay, don't forget your big smile. Thank you so much. Thank you for insightful sharing, and please be seated. Thank you. Thank you. Just feel free to put down the microphone and then just return to your seats. Thank you so much. Celebrating a decade of Future Science Prize, we now become an unparalleled assembly of leaders behind the world's most renowned awards. They are going to share their invaluable insights and best practices for establishing a prize that truly advances scientific recognition. We are going to have a very important session. May I invite you all please be seated first? Yeah, because we are going to have more sections on stage. May I invite you all please be seated. Now we would like to introduce our moderator, Professor Mao Chung Frank Zhang, Rotating Chairman, Advisory Board of the Future Science Prize. Could you please come to the stage and thank you. Thank you. Because we are going to have a very exciting session. May I invite you all please be seated first? Yeah, and also seeing some newcomers. Just feel free to find a seat. I believe we can get so many insightful and very informative information. So now I would like to invite our panelists, Professor Chen Zhenchuan, Chief Executive Officer, 10 Prize Foundation, and also Professor Lim Kun Zhang, Chair, IEEE Medal of Honor Selection Committee. Professor Zhang, please. Professor Ingrid K. Glad, Chair of the Board, the Nobel Prize. Professor Fors Hans Hansen, former Chairman of the Nobel Physics Committee. May I invite our Professor Fors Hans Hansen to come to the stage. Wow, that's really exciting. We have so many guests from different cities. And Dr. Ehud Kainen, Council Member at the World Foundation. Last but not least, Professor Ovid J. L. Zhang, Board Member, 10 Prize Foundation. Please be seated. Now I would like to pass the stage to our moderator. Thank you.
Thank you. Hello? Yeah, let's sit down to look forward to a good panel discussion. Good afternoon, everyone. How are you doing so far? Good? Yeah, very good. Yeah, I'm Frank Chang, and I'm the rotating chair for the advisory committee for the Future Science Prize this year. It's my great honor to call for this panel, wonderful panel discussions that we gather the representative from worldwide, the well-established the prizes we call, yeah, in scientific areas together. So this is the first time with such a kind of the prizes gathering, the panels. I believe I've never seen such an arrangement in the past. Yeah. So anyway, today's special session panel discussion. We say the purpose to discuss how to run a successful prize. I think that's an important thing that we should always learn and continues to improve. We're very proud of so far we can accomplish in the past 10 years with the Future Science Prize. But into the future, we still have the long way to go, to walk. Like some of the most well-established the prizes like a Nobel, for example, is already beyond 100 years. Yeah. And some others very established, the Abel and the Wolf and the Town Prize even is at this point is older than our, actually we are pretty young, 10 years, the Future Science Prize. Yeah. So in order to do that, let me first introduce my panel members. This is a purely from the alphabetical order of the panelists' name, last name. So let me introduce the first one is Professor Chen Zhenchuan. Yeah. Welcome, Professor Chen. Yeah, he's a professor emeritus of civil engineering, National Taiwan University, academicians for the International Academy of Engineering, and also he's the chief executive officer, the Town Prize Foundation. Our second the panelist, Dr. or Professor Ling Chong, yeah. You're welcome. Yeah. Is an honorary professor at the Chinese University of Hong Kong. Actually, he also served as a chair for the IEEE Medal of the Honor, the selection committee. He's also the council member, the Hong Kong Academy of Engineering. He's also served as the board of director of the IEEE Foundation. I think many of us are IEEE members here. Yeah. So welcome, Dr. Ning Chong. Yeah. Our next panelist, Professor Ingrid Grab. Yeah. Welcome, Professor Ingrid Grab. Yeah. She's a professor of the Statistics University of Oslo. Yeah, Director, Research Center, Integrated Norwegian Center of Knowledge-Driven Machine Learning. She's a member of Norwegian Academy of Science and Letters. Also, she's a fellow of International Statistics Institute, IS, and she's a chair of the board, the Abel Prize. Abel Prize, as you know, is bestowed to the distinguished mathematicians. It's a very, very well-established prize foundation. Yeah. Thank you, Professor Ingrid, for your coming. Yeah. Our next one will be, next panelist is Saul, the Dr. and Professor Saul Hansen. Professor Hansen, welcome. Yeah. He's a professor of the theoretical physics, Stockholm University. He's also the former chairman of the Nobel Physics Committee. Yeah, I think because they recently just announced the Nobel, the laureates, the new ones, you may have some interesting questions to ask him, how to come to this conclusion every year after year with an outstanding list of the Nobel Physics laureate members. Yeah. Thank you, Professor Hansen. Yeah, welcome now. And the next one will be Professor Dr. Ehud Kanan. Yes, welcome. He's a Benno, the Gitter Professor of the Chemistry. He's a Technion, Israel. He's an AAS Fellow, ACS Fellow, also the council member at the Wolf Foundation. Yeah, Wolf Foundation, they call the precursor for the Nobel. With a very wonderful name there, reputation there. Well, we're curious how could that be achieved over the years. He's also the ICS, the president, and also the well-established IUPAC, the organization's president. Yeah, welcome, Professor. Yeah. Then our last panelist is Professor Dr. Ovid Zen. Yeah. He's an academician, Academia Sinica. He's also the chair professor of cognitive neuroscience at National Taiwan Normal University and the Taipei Medical University. He's also a board member of the Town Prize Foundation. Welcome, Professor. Yeah, Professor Chen. Yeah. Thank you for the coming to this panel to discuss this interesting topic, interesting challenges there, how to run a successful prize. In the past decade of the Future Science Prize, over the 10 years, our world has demonstrated the power of a well-designed prize to drive the discovery, inspire generation, and elevate the science on the global stage. I think that is our mission we're trying to do, and into the future, as we look into it, and we'll be very grateful if we can gain some more the insight, invaluable insight from each of the panelists here. Yeah, we warmly welcome your ideas and the proposals for us to help us to shape the next chapter of this esteemed the prize, the Future Science Prize. I have prepared 2 questions to each of our panelists. So the first question will be a common question to each of the panelists. It's the same question, actually, yeah. So let me read the first question, and I'm going to ask each of the panelists to answer that from the different angles, from their own perspective, their own, past backgrounds. So the question number 1 will be, what do you see as the most important principle and or even disciplines in running a successful prize in order to uplift the prize's the value, the credibility, the sustainability, and the global impact or global influence? So that would be the first question. So I will ask in the alphabetical order again to answer that question. So after that, then we have some very specific questions to each of the panelists to further explore their insight, for each of their prizes, So to answer the first question, please, Professor Chen Zhenguan, what will be your view in terms of what's the purpose of the town prize? Because you're CEO of that. What are the most important principles and the disciplines in running a successful? You are very successful so far.
Thank you.
So thank you very much.
Okay.
Please.
Thank you, Professor Zhang. Establishing a major international prize is a long-term undertaking. It requires a founder with clear vision and strong ideas, supported by a capable team committed to sustaining its growth and fulfilling its founding mission. A sound organization begins with its founder and the donor. Take the 10 prize as examples. Dr. Samuel Yin, through the Guanghua Educational Foundation, has supported higher education in mainland China, Taiwan, and in the US since 1989. His efforts include the Guanghua Scholarship to 37 major leading universities in mainland China, the establishment of Guanghua School of Management at the Beijing University, Law School in Zhejiang University, and others, and the long-term sponsor of Guanghua Engineering, Science, and Technology Awards of the Chinese Academy of Engineering. The founding of the 10 Prize in 2012 with a global vision was therefore an extension of his long-standing dedications, now in its 13th year. Dr. Yin is not only a distinguished entrepreneur, but also an innovator and an inventor, holding more than 700 patents. In fact, he is the major key constructor for TSMC in Taiwan, with very high, precise, and fast constructions. His deep respect for knowledge and academia has translated into unwavering support for the scholarly community. To ensure effective governance, he assembled a strong and dedicated board of directors, internationally renowned scholars serving on the selection committees, and a competent administrative team. Together, they work according to the shared principles and the discipline framework, ensuring that every task is carried out effectively. The selection committee evaluates candidates based on their innovation, contributions, and global impact, regardless of ethnicity, nationality, gender, or religion. An open, free, and academically robust environment is fundamental to guaranteeing fair, professional, and independent deliberations, free from external influence. Such integrity has earned the Temprice broader recognitions and trust, encouraging nominations and support from across the world, and therefore enhancing its value and global influence. Equally important is the focus of its award categories. In response to the challenges of the 21st century, the Temprice centers on sustainable development, encompassing 4 domains: sustainable development, exploring the relations between humanity and the environment; biopharmaceutical science, addressing human health and disease; sinology, illuminating Chinese culture and its contribution to world civilization; and rule of law, advancing justice and the common good as the foundations of social order. The Temprice thus celebrates not only achievements in natural science, but also the increasing vital fields of the social science. Thank you.
Thank you, Professor Chen. For the wonderful 13 years. So thank you for sharing of that. I would also like to point out, probably is unique from this prize to give the award to the synergy, right? You call it. It's a Chinese, we call it 汉学, yeah. It's a Chinese, the philosophy, Chinese literature, and history. Yeah, that's probably the most unique, the town prize. Yeah.
But most of the laureates came from Europe and the US as well.
Yeah. Thank you for sharing. So I would like to invite our second panelist, Dr. Ning Chong. Although the medal of the owner for the IEEE, everybody knows, this is 100-some years, right? But in a recent, the medal of the owner changed from the old, I think we're talking about maybe 40,000 US dollars in the price. This year is the first year, the up to the 2 million US dollars, the single prize, yeah. It could be shared, I assume.
They changed the rule from 1 person to 3 people.
Oh, to 3 people, yeah. Yes, please elaborate on the, what is the original purpose and what's the value to uphold? Yeah, how to assure, yeah. Thank you.
Okay, thank you, Professor Feng Cheng, for inviting me to this panel. I think it's humbling for me to be on the same panel with this group of distinguished leaders in running the world's foremost prizes. Let me say a few words about IEEE. IEEE is a non-profit organization established in the state of New York. So everything we do, we must obey the New York law, which is not that much different from the common law in Hong Kong. New York adopt the common law, whereas California is a slightly different system of laws. So it gave the first award in 1917, so it's more than 100 years old. And the first prize was awarded to Edwin Armstrong. So at that time, it was a tube during the First World War. And then the most recent prize was awarded to entrepreneur and engineer Henry Samueli, the founder of Broadcom. So their products are based in semiconductor and electro-optics. So it's a long way from the tubes to all the way to transistors. The throughout this time, we make a lot of changes based on the laws and governance and so forth. So let me say a few words about the most important principle. Actually, I can see a few more, as Frank indicated. Oh, by the way, I bring with me a summary of the 100 years of the Medal of Honor, the highest award. You can download it from the web of IEEE, so it highlights all the awards given out over the last 108 years. The principles. First of all, it must follow the vision and mission of the organization. So when you establish a prize, you have to ask why we want to have a prize, what are we celebrating, what are we honoring. So the IEEE's mission is to advance technology for humanities. And we constantly push the envelope of advanced technologies for the common good around the world. So we have 500,000 members distributed over all the continents. Second, we need to maintain the integrity and governance of the prize. IEEE has a very rigorous governance committee that updates all the rules every year or every 2 years or whenever it's necessary. And so the practice of the awards follow this kind of governance. So it's essential to have a very strong governance system to ensure the ethical ethical and integrity standards. The next item is the credibility of the selection. So again, it's important when you announce somebody win an award or a team win an award. So everybody must be think that is a good choice and is that the winner deserves to have the major award. So while the deliberation of the winners are confidential, but the practice must be transparent. So the process, how to do the nomination search, and then the deliberation, and finally the selection. We must follow all the rules, details in the governance. And then the committee members are carefully chosen. They must be the top experts in the field around the world. And then they cannot remain in the committee forever. Each person has a definite term limit. And each year, we need to bring in new members of the committee, and we cycle out the members who has been in the committee for more than 3 years. So we want to constantly maintain fresh ideas, and then not a single group of the people dominate the selection. So this is the governance situation. But of course, the award is actually, we want to inspire the people, especially young people. So the awards must be able to govern the imagination of the public, as well as the technical community. The winning topic must stand the rare test of the time and inspire a new generation of newcomers to the field. So I'm glad to report that throughout the last 100 years, people by and large agree with the selection of the committee. As a matter of fact, during the history of the award, we had about 10 Nobel Prize winners in physics, probably maybe 1 or 2 in chemistry, winning the Medal of Honor award, and vice versa. And some of the medal winners eventually move on to win the Nobel Prize. So the energize and galvanizing the people is very important. So the next topic is sustainability. And again, the organizing party must be financially and organizationally stable, so to make the prize to go forever. So we have some minor prizes that is no longer current or represent the technology that's no longer relevant. Then the Board of Governors make a decision to sunset these awards. So the currency is very important. And finally, the global influence. The award must be well publicized around the world, and to give out, let me see, the question of diversity and inclusiveness and robust must be addressed. This is an important area. So about 10 years ago, we purposely invite applicants or nominations from female scientists and so forth. And so far, we make important progress in this area. And the number of female scientists increases. And the symbolism of the prize and the totality of prize winners over the years is also important. So this group creates the branding and a sizable community. They serve mentors of the young scientists, more junior colleagues. So to maintain the perpetual influence of the awards. Thank you.
Thank you. Thank you, Nick. Yeah, glad to see the old established medal prize now gain the new momentum. Yeah, new strength. Yeah, congratulations. It's a lot of achievement. Yeah, thank you. Yeah, our next one, the panelist is Ingrid Grad. Yeah, please go ahead. Yeah.
So I would like to say, to start with saying thank you for inviting me here. It's really exciting to be here and see what you have achieved during the first 10 years. Yeah. Congratulations with the 10th anniversary. The Abel Prize, in which I'm chairing the board, soon has its 25th anniversary. Oh, 25th, yes, in 2027. So we are also a relatively young prize, but I think I can say that we're well established. The Abel Prize, for those who don't know, was established in 2002 on the occasion of the 200 years of the birth of the Norwegian mathematician Niels Henrik Abel. It's an annual prize that is given to, or can be given to, any field of mathematics, and it's state-funded, managed by the Norwegian Academy of Science and Letters, and it's awarded in May every year by the Norwegian king in a beautiful ceremony. And when it comes to the most important principle, I mean, the main principle is to have very high ambitions and focus on extremely high quality in all details connected to running a prize. But if I should choose one, it's quite similar to the IEEE choice here. It's the high quality work of the selection committee. I think that it's very important that they select laureates who, all those who know the field well, would acknowledge to be really outstanding and having really high impact in that field of mathematics. The Abel Prize has, in practice, become a lifetime achievement prize so far, but it's nothing in the statutes that says that it is like that. So it can be given across all ages and geography and fields of mathematics, of course. When it comes to the process of the selection, I think there is one thing that is different from, for instance, the Nobel Prize, and that's the nomination system. Because it's not such that there are selected organizations or persons that can nominate. Anybody can nominate anybody except themselves. That's the only rule. And it has to be somebody that is still alive. Yeah. And this, of course, makes the work of the committee larger, because they don't only have to find the best among the nominees, but the best in the whole world. So it is an extensive job to do this selection. So the members of the committee can nominate themselves, not themselves, but they can themselves nominate as well. And I also think that it's important to have a fast turnaround, as you also talked about, in the committee. So for the Abel Prize, it's actually only 2 years that people are serving. And it's an international committee, and the members are suggested by the International Mathematical Union and the European Mathematical Society. They suggest 2 members each, and then there is a chair that is nominated from the academy. So I think this is also very important in order not to cement things and have a very dynamic committee. Yeah.
Yeah. Thank you for sharing. Yeah, it's really interesting to know that. Yeah. Yeah. Okay. Oh, next panelist now the Professor Hansen from the Nobel the Physics Committee, the former chair. Yeah.
So first, also, thank you very much for the invitation. It's a very interesting group of people to discuss with. And I will not now say anything particular, about the history of the Nobel Prize. I might do on the second question. But I will concentrate on these questions that you asked. Principle and disciplines for value, credibility, sustainability, and global impact. So how do you achieve that? Because everybody wants to achieve that, of course. And I think perhaps the most important thing in the long run is to build a very credible list of recipients of the prize. Mm-hmm. And there, of course, face it, I mean, the Nobel Prize have an advantage. If you get the Nobel Prize, you are in this list which has Einstein and Bohr and Dirac, etc. But if you start a new prize, the aim, I think, should be to build up a similar list of people in the subjects that you have chosen to concentrate, be it mathematics, be it human rights, be it computer science, etc. So that's sort of an obvious point, I think. But even though the point is obvious, it's not all that easy to do this correctly. And we heard now some examples of how this is done for different prizes. For the Nobel Prize, it works a little bit differently. It's a committee of 6 to 7 people. But what I always stress when people ask me about the Nobel Prize is that it's not these 6, 7 old Swedish professors who are taking this decision. This is, in a sense, a very collective decision of the community, because first of all, we get hundreds and hundreds of nominations. And the nominations are by invitations. But that also means that we want to get nomination from well-known universities, from people in the field that we know are very good. When we got all those nominations, based on that, we ask for reports. And for each Nobel Prize, you can rest assured that there are many reports coming from the most prominent people in the field, although we try to pick the ones that won't nominate themselves, of course. And then that is processed. Usually summary reports are written by members in the committee. And this is a process that normally goes over many years. And also the whole class of physics in the academy is involved in this. And I think this is very important because I've seen during my years that there are certainly elements of groupthink. There are certainly notions of what is important and who did what. That when you start to look at the original references, is when you look at the history, etc., you will see that that is perhaps quite different from what you and many of your colleagues thought. So this thing, not to speed up too much, to take your time, take in as much information as possible, and try to process that. That, I think, is important. Now, having said that, you will make mistakes. There's no doubt that you will make mistakes. We heard today a comment on Vera Rubin. You know, there is a list of people, I usually say, who did not get the Nobel Prize. And that's not most of us. But there are some people that, in historical hindsight, people would say, why didn't she get the Nobel Prize? Because it usually is a woman, okay? If you look back historically. My favorite on that list is actually Madame Wu, who did really important work in two fields.
That probably is everyone's question to you.
So you make mistakes, but when you make mistakes, then you try not to make them again. And I think that today, I don't think it will be gender bias, but the biases that are the dangerous ones are the ones that you don't know about. So that's what you try to find out. So I think the mistakes. Now, there are two kinds of mistakes. The mistakes I mentioned now is that you pick the wrong people or not all the right people for the right result. But there is another, even more serious mistake you can make, and that is not to acknowledge the right discoveries. And that is perhaps even more important because when you have only 3 recipients, like for the Nobel Prize, you will inevitably, in many cases, not be fair to all people, but you have to be fair to science. That should be the goal. Thank you.
Thank you. Thank you for sharing the insight. I'm sure the many questions will be raised here later. But anyway, thank you. Yeah. Let's have next the panelist, Professor Keenan, to talk about the Wolf Prize.
Thank you very much. I'm very happy to be here and share my experience. In fact, I'm involved with the Wolf Prize for many years, maybe at least 20 years, but also with many other prizes in Israel and abroad. And I'd like to share the common experience. First of all, why we award prizes? First question. And my answer is simple. We would like to show the young generation define role models for them to follow. Because we want to attract the young generation to science, we want to show them here are the role models for you to follow. This is probably the single reason why we give prizes. And other things are secondary. And from this definition, there are 2 consequences. First of all, it has to be it's not only the science, but also the personal story of the winner. That's something that is becoming very important, particularly in the case of the Nobel Prize and also in the Wolf Prize. There are very interesting similarities here. The Wolf Prize is 50 years old. So we are young, but probably not too young.
Not too young, yeah.
And we have 6 disciplines. We have medicine, mathematics, chemistry, physics, agriculture, and the 6th domain rotating. This is art. This is rotating among visual art, music, and architecture.
Oh.
Every year, one of these, the 3. So going back to the consequences, the other thing that is very common to both the Nobel and the Wolf Prize is that it's not only about the science, but also about the history of science. Because the prize is given not to a specific person, but to a specific discovery.
I see.
Some conceptual advance, some discovery, something that happened and changed the world. And then you say, well, we want to signify this specific advance, and then we go to the history and say, who is responsible for that? So the person, up to 3, and in some cases there are 6, you have to choose sometime in arbitrary way. For example, the ribosome story, the structure of the ribosome, there are 6. The 6 heroes, but limited to 3, so sometimes the choice is arbitrary. But the point is that it's not for exemplary, for a role model career. It's not for a person, other prizes do that. You give to a person who published so many papers, has so many graduate students, has so many money collected, whatever, patents, metrics. No, the Nobel and the Wolf look at different angles, say, we are not interested in the career, we are not interested in any personal achievement. We were looking for the specific advance, disruptive advance that changed the world, and we owe this people for changing the world for us. So that's the main thing. Now, if I go, so there are two consequences from what I say earlier. And the last thing that I want to mention, you ask about the disciplines. Basically, we all know that there are no disciplines in science. I mean, science is a continuum. I know physicists who work with DNA, and I know people from chemistry who do drug development, etc. So science is a continuum. Why we have these disciplines? Because we teach, and we have to design teaching packages. So from here to here is biology, from here to here is chemistry, from here to here is physics, and then mathematics, etc. So basically the disciplines are those defined in high school and in first or second year college. These are the basic training or the basic educational packages that you need to have in order to specialize later. So giving prizes to something very special, so a new technology that is currently a trend, in my view, that would be a mistake. You give to the basic, very basic disciplines. So I have some other comments, but I'll keep it for later.
Thank you, thank you. Thank you for your very insightful sharing. Thank you. Yeah. Let's turn to our last panelist, Professor Ovid Chen. Is also on the board member of the Tom Prize. Yeah.
Okay.
Yeah.
Because we have 2 persons came for the Tom Prize. And the first question that has been asked is, what is the best principle that will run this prize and then see it is sustainable for the future?
That's right.
I would say, from the very beginning, you need one visionary person who decided science, any scholarship, that need to be sustained for the future. So this person decided he needed to organize this group of people to talk about it. And the second question is what kind of discipline that you need to choose? Well, for this person, he's involved in the current affairs of the society. There's a lot of complexity and everything. But you are in Taiwan. How do you vision and looking at the world? So, we thought about it. The first thing important is, of course, there are Nobel Prize. And the medical industry is coming up. And so we decided to say, well, basic research for medical discipline is important, but what is the application? Drug. Okay? And so we decided we need to choose it. Just basic, and then how to apply your knowledge to create a new industry. The second one is sustainability. It's important. At first, we thought this guy who tried to create this prize is an engineer. No, he's actually a management professor. But interestingly, he got a lot of patents on construction. I look at it. I didn't know him that well. And then I was invited to talk about it. And this guy, coming from a school of business, and had a construction pattern all over the place. I was surprised. And then we said, well, do you want to do that prize for yourself, your discipline? He said, no. I want to do it for in the future. Sustainability is very important. So that's why we have the third one, the second one. The third one, he decided to choose sinology, of course, Han. But the important point is Han is not defined well. If you look at the tomb, the Shikata, and all these people, Karakata, and the Emperor Qin, they are foreigners all over the place. So the idea is Tang Prize had to include everyone, not just for Han, but beyond Han. The other thing that's important for in the future, he thought, we need to see new into the industry coming in. Genetic study, archaeological study are not just from the book, old book. From a lot of diggings, we knew there's a lot of story in a book about Han people and how they did this. But what happened in 4,000 years ago? There are mummies from the Caucasian people in China. They are not in the book. So we said, we need to have to continue and go to the future. So genetic study, archaeological study are all coming in for sinology. The fourth one is rule for the law. These creators are very, very visionary. And he said, we are in the world, everybody talk about democracy. But behind democracy, it's important is to have the rules of law. And if you see it, not only one single person who is important, it's a whole group of people behind it that's important. So we decided to have four disciplines. And the important point is, he later point out, what will be the best principle to get the prize forever? We have to choose a good executive person like Zhenchuan Chen. He has been running this and then holding it so well. And so that's the reason that we can come up to a successful prize. You know, we are so proud because 10 of us are getting the Tang Prize and then Nobel Prize. You never thought about it. At the very beginning, we never thought about we're going to get a Tang Prize and then Nobel Prize. But we did it. So we are very proud. Thank you.
Thank you very much for sharing. Yeah, with the 13 years, the Tom Prizes, you have many things to be proud of. Yeah. Let me proceed with the second question to the panelists. This is a very specific one to each of you. Yeah. So the second question to Professor Chen would be, as a CEO of the Tom Prize Foundation, how do you see the Tom Prize and the Future Science Prize can collaborate and all play complementarily in promoting and recognizing cross-disciplinary scientific progress? Is there any place and their impact to human society? Yeah, because the time issue probably need to be concise.
To be short,
Thank you.
Yes. Yeah, in today's diverse and rapidly changing world, every field holds unique importance and deserves appropriate recognition. Yeah, even the Nobel Prize, established 125 years ago, has its boundaries. The emergence of more international prizes across a broader range of disciplines is therefore both natural and beneficial. The Future Science Prize has made a long-term contribution in the fields of life science, physical science, and mathematics and computer science, each with its own distinctive characteristics. I have also noticed that although engineering representing a very large community in academia, there are relatively few major international awards dedicated to this field. But today I hear that IEEE announced a big award. Yeah, that's good news. Yeah. As society continues to evolve, the TEM Prize, by virtue of its unique award categories, has demonstrated greater diversity, with 28% of its laureates being women, compared to only 6% for the Nobel Prize, highlighting a more inclusive and diversified recognitions of global contributions. The TEM Prize has actively engaged with peer institutions such as the Japan Prize and also Kyoto Prize. Likewise, collaborations with the Future Science Prize would further enhance credibility and social impact. We recognize the complementary strengths among these prizes and welcome opportunities for meaningful cooperation, such as mutual exchanges and visits, participation in the TEM Prize Award Ceremony and TEM Prize Week, and co-hosting targeted academic or outreach initiatives. Yeah, let's join hands to make the world a better place. Thank you.
Thank you. Thank you for all the good suggestions. I think the Taiwan and the Hong Kong is not that far away. Only 1 hour away. We have many things that we can work together. Thank you. Yeah, for your inputs. Yeah. I'd like to ask the Professor Ning Chong a specific question. As a chair of the IEEE Medal of the Honor Selection Committee, you have a very global view of scientific excellence. Where do you see the unique position of the Future Science Prize, since you're here, experienced with us in the international landscape of prizes? Yeah, and how can you collaborate or co-work with established institutes like IEEE to amplify its global influence? Yeah, please. Yeah.
Thank you. This is the first time I attended the Future Prize Award. So I found that it's well run. The talks are very good and it's inspiring. And so even though the number of people involved is relatively small, but I think the Future Prize has a potential to make it important and also work with many other organizations that's represented here. I want to cite two specific examples. So IEEE Medal on even though it's the top prize, but under the top prize, we have less than 20 medals. I think now it's 18 or 19 medals are the major awards representing different fields. And then underneath there are 30 TFA awards, technical field awards, representing the 30 more detailed disciplines in our field of interest. So there are plenty of rooms to work with the other prizes and other organizations. So one example is the James Clerk Maxwell Medal, which we consider one of the most important medals. As a matter of fact, Professor Frank Chang was the winner of that a few years ago. So we work with the Royal Society of Edinburgh to run this prize. And it is well received because the prize is given in the US and then around the same time also given in Scotland, Edinburgh, which is a very important place in the history of technology. So this is one example. And secondly, we have joint collaboration agreements with different countries, like France, Germany, Chile, and Korea. I'm not sure whether that we have one with Japan, but so in other words, with these countries, so we actually held joint awards on topics of current interest. So of course, we also want to take advantage of the Future Science Awards, for example, like the talks this morning in the physics area. So I found this as very inspiring as an old physicist myself. So I would like to publicize this and share this good work with other groups, other communities.
That's right.
So I think there are plenty of rooms for us to collaborate.
Yeah, thank you. I suppose he has a lot of good and new ideas. Well, it's old society, actually, 100-year society, but with a lot of new momentums in recent years. It's really a wonderful sign. Yeah, thank you for sharing. Yeah. Next one is Professor Ingrid Grant. Yeah. I have one specific question for you. Is drawing from your involvement with the Abel Prize or Abel Prize, which honors mathematicians, and the Future Science Prize. What roles do you believe the prizes can help inspire young generation? I think that's the generation we will always try to influence, yeah, and to pursue the STEM, we call the STEM, the career. Yeah. Thank you. Yeah.
Thank you. Yeah, it has already been mentioned here that the main objective of science prizes is to present young researchers for role models and to put spotlight on research and science at least 1 week a year when it is weeks like this, prize weeks. And I was very happy to see all the young students that was yesterday and today in the aula here today, asking brilliant questions, and I see that you really focus on involving young people. Also tomorrow you have the dialogue with the youth.
That's right.
With the laureates. And I think these are events that can be life-changing for young researchers. The Abel Prize is also focused on young researchers, but we also have a specific responsibility for even younger persons. So we have a dual purpose that is actually formulated in our statutes, and that is that, well, we should award a prize for pioneering scientific achievements in mathematics, but we should also boost the status of the field of mathematics in society and stimulate children and young people to become interested in mathematics.
Yes.
So we stimulate and fund a lot of activities that is focused towards school and children and youths. And these are things like competitions that we have the Abel competition in high school, where the winners will continue to the IMO, the Olympics of mathematics, International Olympics, that China won this year. Congratulations. And we have team competitions for junior high school pupils. We have a teacher prize. We arrange mentoring and support the development of tools and web pages and conferences for teachers and so on. And this is, of course, going on during the whole year. So this is a special task that the prize has been given from the Norwegian government. That was some of the reason the prize was finally established in 2002. Norwegian mathematicians had tried to get funding for a mathematics prize in the honor of Niels Henrik Abel for more than 100 years. But at that point, the Norwegian pupils had dropped on the PISA ranking considerably, and so this was sort of used as an occasion to make a prize in mathematics that would also have this other objective towards children.
Yeah. Thank you for sharing. It's a very interesting view. Thank you. Yeah. Next question to Professor Hansen. The Nobel has, for over a century, set a global standard for the scientific prize. Yeah, your tenure with the Nobel Committee gives you a deep understanding of what defines a paradigm-shifting discovery. Yeah. So, as a new prize with a global ambition at this point, yeah, we'd like to hear your advice and your view on how can the Future Science Prize build its unique identity and credibility. And what's a new dimension can it add to the global celebration of sciences? Yeah, thank you. Yeah.
So I think that in my previous answer, I sort of outlined how we try to identify these breakthroughs. So I already said that, but I would like to make a couple of other comments. And that has to do with some specific features of the Nobel Prize. You might know that it's based on a donation and a testimony by Alfred Nobel. And he lays out there the principles, and one of the key sentences is that it should be given for discoveries or inventions during the year. We don't care about that with the year, but it should be for the greatest benefit of mankind. Okay. So, you know, already we heard from Professor Nam and Professor Glad about the importance of inspiring the youth. And Nobel Foundation does quite a bit on that also. So I won't elaborate more on that. And we also heard on this stress that both Wolf Prize and Nobel Prize have of discoveries, not lifetime awards.
Yeah.
So I won't elaborate that either. But I would like to make a comment on this thing in the testimony that says discovery or invention, because that's related to what you said about paradigm-changing discoveries. So sometimes I meet people who said, you know, you gave a Nobel Prize to a guy who made a diode, a light diode, and my beautiful brain string theory of everything didn't get a Nobel Prize. How come? And that is related to this thing in the will of Alfred Nobel, and it's something that I think we should all reflect upon when it comes to invention, and that is that for the general public, the belief in science, the acceptance of science, the authority of science is to a very great extent based on technology. It's based on that, based on science, we can actually do things that work. Then there are parts of science that do not produce things that can work, like, you know, elementary particle physics, the very subnuclear, or what happened at the beginning of the universe or the end of the universe. But by telling a story where we forge those discoveries into a general scientific structure that also produce things that can be understood and that can be useful, I think that that is important for the acceptance of science.
Yes.
So, so yes, that's, yes, and then is one more thing, and that is that Nobel Prizes are only given for discoveries or observations that are actually made, experiments. Just the theory, however interesting, will not render you a Nobel Prize. It has to be backed up by experiments or observations. And by keeping to that principle, I think we have kept, you know, a sanity in the prize, which I think is very important.
Yes, yes. Thank you, thank you. Thanks for that clarification. I think that's a very important, very unique point. Thank you. Yeah. My question then to the Professor Ehu Kenan. Yeah. In your role with the World Foundation and IUPAC, you have served the highest level in supporting both fundamental and mission-oriented scientific endeavors. In your opinion, how can the Future Science Prize strengthen its global partnership with other institutes and enterprises to create a more cohesive and powerful force for promoting the sciences worldwide?
Well, I'll start from the cooperation or collaboration with the other prizes. I'm not sure this is very relevant because prizes or foundation of prizes compete with one another. So I don't think it's very relevant. I want to focus on a few things. First of all, I forgot to mention about the sustainability of the World Prize. It's based on the endowment, of course, but it is based on a law of the Israeli parliament. So no matter if there's money or not money, it's going forever because it's a law. It's a state law. So it has been awarded by the president of the state of Israel. Okay. Now, related to the young generation, we have, when we have the ceremony, we have a week. We call it the Wolf Week, where all the laureates come, and at least one day they meet with, there are several organizations and schools that have a gifted student programs. So all these gifted students come and they meet a whole day with the laureate, and they discuss with them and get the inspiration from them. That's something that is working very well for us, and I really recommend that for other prizes. Now, how to make the prize successful? This is extremely most important thing. And I follow what Professor Hansen said, that everybody makes mistakes. We make mistakes, the Nobel Prize makes mistakes, everybody. If the level of mistakes is maybe 15 or 20%, we should be happy. And I'm talking about false positive and false negative. That was mentioned already. Now, how you maximize the chances for a successful selection. And I can give you my World Prize and other prizes that I personally established. There are three phases. The first phase is the nomination of good people for the prize, number one. Number two is the selection process. And number three is all the ceremony and public relation, etc. And I think the most important thing, at least for us, is the second. It's the selection process. And we do it in a very special way. It's very confidential. Nobody knows the identity of the jury. I'm responsible for chemistry, okay? But we don't take part in the selection. We have about 100 files of nominee every year. And it's very difficult to choose the right one. And so what we do is, and we consider this successful action on our part, is the selection of the jury. Now, you'd be surprised to know how small is the jury. Before my time, the jury was only 3 people.
Wow.
One from Israel, one from United States, one from Europe. And I suggested to increase it to 5 people.
I see.
And right now, only chemistry and medicine are doing that. Others are still 3. But that jury meets and they do a very serious job. When I served in a jury many years ago, we convened. We are 3 people. We convened in a place in California. There were 3 people for 48 hours. We were not allowed to go to restaurant. They brought us sandwiches. We were isolated from the rest of the world for 48 hours.
That's so interesting.
I lost 3 kilograms of my body weight on that on that experience. And I think we did a good job. Okay. And when we do a good job, most World Prize laureates or nominees, they know there's a sort of a slogan that the road to Stockholm goes through Jerusalem.
I see.
So you have to go first to Jerusalem if you want to go to Stockholm. So, and I think we are pretty much correct. It's like 30 or 40% of the World Prize later received the Nobel Prize. So I think that's about what I wanted to say. The last thing is about the money. I don't think the money is the primary motivation to achieve the World Prize or the Nobel Prize. The World Prize, you may be surprised to know, the World Prize check is very small. It's only $100,000 US. Okay, but what is important, and what Professor Hansen mentioned already, is the club of previous laureates. So you want to be a member of that club.
I see.
That's the main motivation, not the money. The money is not an issue. It can be 100, it can be 3 million. Like
that's an interesting concept. Yeah.
So it's not the money. The money is secondary. Yeah.
Thank you for good sharing. Yeah. My question to the last panelist, the Professor Ovid Zheng, will be, with your distinguished background in cognitive neuroscience as a former Ministry of Education, how can we better integrate the cutting-edge scientific knowledge into educational system to inspire and prepare next generation of scientists? What role can the future science play in this mission? Yeah.
Thank you.
Yeah.
I was one of the Ministers of Education that has been in great trouble.
In great trouble.
I also serve as a Minister of Culture in Taiwan. But anyway, this question is about education.
Right.
One aspect of Town Prize is very important, that each recipient get a very generous grant for cultivating the next generation. So they have to come out with a proposal. How do you train and to get your second generation in your discipline or related discipline? So that's a very important aspect of Town Prize in terms of education for the next generation. And in general, if you ask me about the kind of future education program that people are thinking about, and I'm now chairman of 18 university in a private alliance. So we have 5 in Malaysia, 2 in Singapore, 4 in Hong Kong, and 8 in Taiwan. They're all the top research universities. And what we are talking about, first of all, I define AI, BI, CI, DI, and EI as the final purpose. What's AI? We need to have the young kids aware of the arithmetic is important. That's very important. And at the same time, artificial intelligence is nothing but tools and simulation. We need to have that kind of ideas behind it. And then BI, biological intelligence, is important. Bioecological. That leads to your understanding of we have to care about your own life and the animal life, the Earth's life, and everything, every life. So, and the other thing, BI all involve business intelligence. Our kids need to know about not just their own work and how to be the businessman in the future. CI is a kind of a creative intelligence based upon a lot of coding scheme, okay? And also, you live in a cyber world. You need a cyber knowledge, CI. And also, we're talking about computation. And the most important thing in CI is you need to have a collective intelligence to talk about cooperation.
Teamwork, yeah.
Yeah, and then DI is data science. That everybody know about it. Digital intelligence, and important thing is the discipline and discipline. Not only integration, but synergy. Talking about, in our Chinese word, 凑合, 组合, 整合, 然后最后要到融合, synergy. That's the most important part of we're talking about the DI. The other thing, finally, we come to EI. It's an educated intelligence. Educated, you have to have a humanized concern for a balanced and ecologically balanced world. And that's, in the future industry, it's very important society for us to keep. So we need to teach the kids this AI, BI, CI, DI, and EI.
Thank you. Okay. Thank you for the wonderful. Thank you for all panelists. But we do promise you, give 10 minutes for Q&As. Now I think the panel now is open for questions. Any questions? Yes. Let's keep the questions short.
Sure. Thank you.
In 10 minutes, we have to conclude.
Thank you. My name is Anderson Shum. I'm the president of the Hong Kong Young Academy of Sciences. So thank you very much for your inspiring sharing. I learned a lot. So my question is, should a successful prize focus on picking topics that will make a big impact in the future, or topics that have already made a big impact in the past, because this will affect how the prizes should be run? For example, if the focus is on discoveries that have already made an impact, there may be a case that the prizes should also be awarded to those discoveries whose founders may have already passed away by the time the impact are felt. Alternatively, if the focus is on the impacts in the future, then in Professor Henson's and Professor K9's term, there may be more mistakes, more false positives. So how should the balance be made? And also, if the focus is on future impacts, this prize may also play a role in catalyzing the future impacts, something that the Future Science Prize may wish to do as well. So that's my question. Thank you.
Okay, thank you. Yeah. Professor Henson, you'd like to answer that?
Well, I can make some comments. I mean, if you look at the Nobel Prize winners, many of them are pretty old, And so something that you can imagine doing when you give out prizes is that you say, we put an age limit. So we give it to young researchers, and we have these prizes for young researchers. And as you very well point out, then, yeah, it's presumably a bit more risky because you tend perhaps to give it for things that are more ideas, something that might materialize experimentally in the future, experiments that are not completely verified, etc. So that's one possibility to do that. When it comes to giving prizes to deceased people, I don't think it's workable. I mean, you know, you start 1 year it's Archimedes, next year it is, you know, Newton, and you have Faraday, etc. So it will take you a long time to catch up. And in addition to that, you know, if you want a living role model to talk to the students, that's going to be pretty difficult.
Thank you for the feedback. Yeah, I think.
Anderson. I don't know about the other prizes, but for the IEEE, the rules are very strict. The deceased person is not eligible to receive the award. And then secondly, besides again, the number of people receiving the award. So for example, it took us many years to increase one person award to 3 people in a team. So why do we do that? Because of the legal impact, as I alluded to. No matter what you do, people will sue you or whatever.
I see.
Right. So that's a law and governance is very important. Everything must be written down carefully, so there's no argument. So if you want to make changes, then go through the governance change.
Yeah. Thank you, Professor Kennan.
Yeah. I want to relate to the age issue and also to the common characteristics of Nobel and World Prize laureates. There is a common characteristic, okay? First of all, it takes about 10 years on the average for discovery to be recognized as a discovery. Right. Okay, it is not well received on the first day. Many people push back, etc. It takes about 10 years to understand the consequence of that, say, oh, that was a real breakthrough. Okay, so that's an age issue. But I want to, there's a common denominator, and you see 6 Israeli scientists received the Nobel Prize in chemistry within 10 years, within 1 decade. And all of them are my friend, because we are about the same age level, it's a small country. And I can say that all of them, and I know about maybe 30 or 40 others, personally, I know Nobel Prize laureates, okay, from various occasions. And there's something common to all of them. All of them are troublemakers. All of them are very independent, very argumentative. The world is going in this direction, and they go the opposite direction. Okay, and I can say it, Adeyonat, for example, with the ribosome. She was fired from the Weizmann Institute because she didn't have enough papers, but she got the Nobel Prize. Aaron Chekhanove, etc., Hershko. The world was studying protein synthesis. They went to the other side, the protein destruction, okay? Everything like this. Not to say Danny Shechtman, that he was just, everybody said he's not, there's no quasi, Linus Pauling said no quasi-crystals, they're quasi-scientists. And they said this is quasi-scientist, it's not a real one. And all of them are like this. So what I'm saying is, in order to, and this is good for the education of the next generation, if you want to win the Nobel Prize or the World Prize, you have to be extremely original. So you have to take a very significant risk. You cannot do the same thing that other people are doing. You have to go to a different way. This is also good for business world, okay?
Yeah, that's right.
And so that's the recommendation to the young generation. If you want to make your way, be original, take a risk, and protect, or you have to defend your decision. That's a common denominator. So that's my contribution from.
On the other hand, we probably should say, you know, as a society, we tend to less tolerant to troublemakers. We have to rethink about that. Yeah, thank you for the insight. Oh, one more question, the last question. Yeah. Any last question from our young generations? No? Okay.
你好，我是想请教张念坤教授一个问题，就是您认为该奖项在设立和运行中如何平衡对已有的重大成就的认可和对未来前沿科学方向的前瞻引导？ 另一个问题是，是否有具体的机制鼓励科研人员探索更具颠覆性的技术领域？谢谢。
哇。
对不起，
我的普通话不translate to the English. The main thing is there any mechanism that we can establish to encourage the researchers to do the paradigm shifting work? What mechanism is behind? If we keep on evaluating our young faculty or young researchers with a number of papers and nature papers, science paper, we're not going to get anywhere. That's probably the question.
Thank you. Excellent question. In Hong Kong, besides, I've been involved in many local awards.
Yeah.
And then one thing that bothers me is that people count that they are the top 1%, 0.5%, or
that's right.
1%.
Yeah.
And
each index.
They also what they call the impact factor.
Impact factor.
The number here. Yeah. So when you are the first one to do that, you are probably okay. When you are the 50 people to do that, I think that's not the way to go. And secondly, even more important is that my view is that when I was young, I am a diligent student of the Nobel history in physics or chemistry. And so my recommendation is that you study the history, who made the award and who did not.
That's right.
Then you learn a lot. And actually, the third recommendation, I have a look at Josephson. So he won the Nobel Prize in Physics.
That's right.
With one paper.
That's right.
At the age of 21. So these are the the examples that one has to study carefully in order to make a big impact. Thank you.
I think it's listen to your own heart. I think that's more important. Your passion, your interest. Yeah. Less important is about the so-called performance index. Those things. Yeah. Don't worry about that too much. Yeah. If that's the infrastructure, try to worry. But I think our time is done. Let's. Can we allow one more questions? I don't know. Do we have time to do that? Okay. One question. Yeah.
Okay, thank you. Here's a question from Shenzhen TV. What do science awards focus on most when backing young scientists? How can award rules break seniority norms to highlight more new talents? I want to ask Thomas Hansen. Thank you.
Oh,
I missed the second part of the question.
Yeah, can you repeat the second part of the question?
Okay, the second question is, how can award rules break seniority norms?
Seniority? What's seniority? Because in the awarding process, there is no age or anything. What do you mean the seniority? You mean the scientist's seniority? Is that what you're talking about?
Maybe some older scientists and younger scientists.
Oh.
Yeah.
You probably misunderstood a little bit. Here, the award we're doing here is about the scientific discovery. Nothing to do with the age. Yeah, please.
Yeah. No, of course, what you are asking, I guess, is related to what we already said, this seeming overrepresentation of older people. Even though for both the Wolf Prize and the Nobel Prize, you say that it's not a lifetime award. So if you look at this year's Nobel Prize, was given for 2 experiments that were made in the 80s. I don't remember what year, but it's pretty old. But it's given explicitly for those 2 experiments. And then, of course, you ask, how come? Why did you wait for so long time? And the answer to that question is that it took a long time before it was realized that this was very important. And that had to do with the thing that I said earlier. It had to do with the technological development. If it wasn't for the development now towards quantum sensing, quantum computation, etc., I'm not so sure that this would have been considered as a very interesting and slightly esoteric results that was, achieved in the 80s. But now, suddenly people see this was really important, it was a breakthrough, and it took time.
Yeah, thank you, Professor Kennard. Yeah, please.
Yeah, I want to refer to the seniority issue, etc. If you are doing a good PhD thesis, which is extremely original and disrupting, you're going to get a Nobel Prize together with your boss. There are many, advisor. There are many cases of the Wolf and Nobel Prizes, and just the one I mentioned, Hershko was the supervisor of Chekhanover. He was the PhD. That was his PhD thesis. And he got a Nobel Prize for his PhD thesis. And there are many cases. There's a long list of Wolf and in all specific, in all disciplines, a student together with the advisor getting the Nobel Prize and the Wolf Prize together. So there's a possibility.
That's and right. This year, it was actually also a postdoc. It was the supervisor, the postdoc, and the student.
Yes.
Yeah. Thank you, thank you.
Well, thank you very much for both our panelists and our audience. Your participation here is just excellent for all of us and the celebration of the event. Thank you very much. And we are all on the news. Yeah, this is the TV broadcasting right now, ongoing. Yeah. Thank you, thank you.
Thank you so much. May we invite you to have a video together? Wow, that's really like a brainstorming and a very insightful sharing. I believe all of us learn more about how to run a successful prize. So now let's get closer and then have a look. Oh, yeah, to have a better... Yeah, I really like the strive for the best spirit. Maybe we can just take out the badge, then we can have either